Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the next part of R-PYQ series. So till now we have covered a lot of things, like we have covered the network theory AC part. In R-PYQ we have covered the linear algebra, the differential calculus, integral calculus, and also differential equations. So today we will be covering two chapters: vector calculus and complex variables. So we will be covering basics of vector calculus as well, like a vector. What is vector algebra? Basics of vector algebra. What is the dot product, the cross product? Because they have asked you questions from basics. So we will cover vector algebra first. Then we will cover gradient. Then we will start with vector calculus, gradient. We will go to divergence. We'll go to curl. We'll understand those things. We'll understand directional derivative. We'll of course do the questions. Then of course we'll do the integral vector calculus, where we will integrate the vector functions. So we will use, we'll mainly use theorems. We'll use Green's theorem, we'll use Stokes theorem, and we'll use Gauss divergence theorem. And trust me, just go through the video once. Don't go through the notes, go through the video. I've explained few things so that you don't have to remember the formulas. So I've told you the techniques which you can use to not memorize the formulas. Without memorizing any formulas, how to apply the Green's theorem. In Green's theorem, they will always say I have m dx plus n dy. So which one shall I differentiate with respect to x, and which one shall I differentiate with respect to y? I know this is always the confusion. In this lecture, this confusion will not be there. After watching this lecture, this confusion will not be there. Do I have to write dm upon dy minus, or do I have to write dm upon dy plus? Do you have to write minus here plus? Which one shall I write first? Because there is a minus sign, right? There is a minus sign. So should I write dm upon dy first, or should I write dn upon dy first? So all those things I have told you a technique, a trick. So without remembering, how you can directly keep this in your head and directly solve. So for that you have to watch the video patiently, because in the previous video I am saying the differential calculus you guys have watched, but the integral calculus you guys have not watched. So if you don't watch the videos, simply you will not be able to do it, because if you just go through the notes, you'll not understand what am I telling there, how to remember the things. If you just go through the notes, you'll not do anything. It will be just harmful to you. Okay. And after that, after covering vector calculus, we'll start with complex. Again, in complex we will start with basics of complex number, because they have asked you questions from basics of complex number as well. Then we will go to the differential complex variables. There we will mainly use the CR equations. Only the CR equations you have to remember. Other things I have told you in such a manner that you don't need to mug up. You can understand conceptually. And then of course we'll use the Cauchy residue theorem or Cauchy integral theorem to solve closed line integration. So we will cover all these things in a 11.5 hour marathon. So if you are enjoying, please hit the like button to the video, and of course comment down below if you are understanding a particular concept. Just go through the video, you'll understand in Green's theorem how I have explained. Trust me, you just watch the Green's theorem part, there you'll understand. Without even memorizing a single thing, you can directly write the Green's theorem. So yeah, there are many things, because they can change the direction of the curve. They can make it anti-clockwise. If the curve is anti-clockwise, then how can you solve? So all those things I've explained there. So please make sure you watch that part. That part is the most important one. So with that, we'll start with the vector calculus. Let's begin with vector calculus. So vector calculus has two words, right? Vector and calculus. We have already conquered, right? What is calculus? We have done in differential calculus, we have done integral calculus, right? So now we have to do the same calculus on vector quantities. So for understanding vector calculus, first of all, we have to understand what is a vector. Vector is nothing but a quantity that has both magnitude and direction. I hope you already know this definition. By now, if you don't know, now you know. What do I mean by magnitude and direction? So there are two quantities, right? One is distance, one is displacement. Okay. So distance is basically the amount of a length between 2 points. Okay. Now if I convert this, right, into displacement, so what I can say, let's say I started from point A and I again went to B and then again came back to E. Okay. Then what is the distance covered? Distance covered will be this. Let's assume this length is L. It will be L, and then again coming back to L, that will be 2L. Okay. Now what is the displacement covered by A? It will be 0. Why? Because now let's assume that this direction is some random AB AB cap direction. Okay, AB cap is just a direction vector, that's it. So initially I went from A to B. So I went in the, let's assume that this direction is plus AB cap. Next I am going from B to A. So that is opposite basically, right? So this direction will be negative of AB, that will be minus AB cap. So overall net, right, I went plus AB cap then minus AB cap. So overall the direction change is 0. So that's why that displacement will be 0. Okay. So displacement is a vector quantity because it includes the direction in which direction I went, right? So because what will happen is, let's say I have a triangle like this, AB, okay, and C. Let's say I move from A to C and then I move from C to B. So let's assume that this distance is D, this distance is D, and this, let's assume that this is a right angle. So this will be under root 2D, right? So the distance moved from A to B, right, for this for person, random person, right, will be 2D. But the displacement would be under root 2D because displacement always takes into account the minimum distance from the 2 points, the initial and the end point. So it only takes into account that how much direction. It also, like, this represents the direction as well, right? 2 to D, this represents the minimum distance, also direction. But in distance there is no information about the direction. Okay, so that is a like, I hope you have understood what is a uh, like a scalar quantity. So a quantity that has no direction, right, is called as a scalar quantity. That is what we have been studying till now, right? In linear algebra also we discuss about all scalar quantities. Vector quantities are those quantities which will have both magnitude and direction. Okay, you can see the force, right? Force is applied at an angle. So force has a angle, direction. So 4 Newton, like if I am applying a overall a 5 Newton of force at 37.13 degree from this straight line. So that means that 4 Newton is getting applied in the I cap direction and 3 Newton is getting applied in the J cap direction. Okay, so I hope that part is clear. So yeah, that's why force is a vector quantity. Now there is another thing known as tensor quantity. It is like current quantity with magnitude and direction that follows algebraic law of addition. Okay, scalar quantities follow algebraic law of addition. Current has a magnitude and direction because uh, current can go in this direction, right hand side, or it can come out of the node, right? So then I say negative, but distance can never be negative. Okay, distance can never be negative. So current has a direction, but the direction of a current is defined by the wire basically. It does not have a physical direction per se, right? Because if I place the wire like this, then current will flow along the wire. Okay, so that's why it follows algebraic, because it follows KCL. So it follows algebraic law of addition. So those kind of quantities which has a direction, right, but which follow algebraic law of addition, those kind of quantities are called as tensor quantities. Okay, so these are this is how we represent a vector. Okay, there will be a basically also with the arrow. Okay, you see the arrow. So this is called as the tail. This is the initial point, and the terminal, like terminal point, also called as the final point. This is called as the head of the vector, and this is called as the tail of the vector. Okay, that's it basically. Okay, now yeah, uh, representation of a vector. So as I have said that a vector has both magnitude and direction. So this mod of A represents the magnitude of A vector, and this A cap of A represents the direction of A vector. Okay, so unit vector in the direction of A basically. Okay, so yeah, direction, like that's how we represent direction in mathematical terms. How can I represent direction? We represent it with the help of unit vector. Now there are many kinds of vector. I will not go through every one of them, right? You can, like, you can get the idea. Null vector will be basically nothing but the vector which has zero magnitude, although it can have infinite direction, right? It has no magnitude, so it is called as a null vector. It doesn't matter whatever direction it is pointing to because its magnitude is null, right? So it is just a dot, it is just a point. Okay, then we have unit vector. So unit vector are also called as direction vectors. They define the direction of any vector. So let's say a bar is there, right? A vector. Okay, so if I am able to write the unit vector of A, that unit vector will represent the direction of A. That's it, because its magnitude is 1. vector with unity magnitude. Okay. Now one more thing is there, if I'm multiplying a scalar with a vector, right, it will just scale the vector, it will not change its direction. Only exception is you don't multiply with 0. If you multiply with 0, basically the vector will become a null vector, right? So we will not be able to recover the information regarding the direction. Okay, so just be sure that you're not multiplying scalar, your multiplication scalar is not 0. That's it. Okay, so that is the thing basically. Now multiplication of scalar with vector. So what I can do is I can multiply any scalar, let's say half, 1, 2, 3, 4, 5, 6. Okay, it can like there is no ability for it to change the direction except opposite. So if I'm multiplying a scalar, the first statement was wrong actually, that I told you that it does not change the direction. It can change the direction, but only in the opposite direction. So if initially my direction was like this, right? If I multiply -1, direction will be reversed. That's it. Basically, it will be 180° from the initial direction. Okay, but I cannot change the direction to here. No, that is not possible with a scalar multiplication. With a vector multiplication, definitely it is possible. With a scalar multiplication, no, sorry, it is not possible. Okay, so scalar multiplication can either keep the same direction or it can make the vector totally opposite. So these are the only two possible cases that the scalar can do. And remember, your scalar must not be equal to 0. Okay, so these are the unit vectors along each axis. So along z axis we define the unit vector to be k cap, along x axis we define it to be I cap, along y axis we define it to be j cap. Sometimes it is also defined as az cap, az cap, ay cap and ax cap. Okay, these are the definitions basically, that also we say both are same thing only. So how to remember all these things? So how to draw the coordinate system, right? 3D coordinate. So if I say x and y is this, how to understand that z will be this one on the top, y z will not be on the bottom? So they have to simply follow the right hand rule. Okay, so what you will do, first of all you will draw your x and y, plot your x. I plotted my x and y. Now I will place my right hand right along x axis and curl it towards the y axis, and I see the thumb is pointing towards me. That means your z axis will be pointing towards me. Okay, so that's how you can find out the direction of the z axis. Okay, so they will simply follow a clockwise rule. X after x, y will come, after z, after y, z will come in the clockwise direction. Correct? Okay, so I hope that part is clear. Now how do I define a position vector in 2D? Okay, in two dimensional space. So basically, right, any vector, right, if I want to write the position vector or the direction of the vectors AB, let's say I have 2 points in the 3-dimensional space, I want to write the direction AB. It will be final minus initial. What is the final value here? It will be OB vector minus OA vector. Final vector minus initial vector. That's it. Okay. Final vector minus initial vector. OB vector minus AB. So what is OB? OB is basically the position vector with respect to origin. It is xi cap plus yj cap plus zk cap in three dimension. Okay. X basically is the x coordinate, y is with the y coordinate, z is the z coordinate. That's it. So this will be equals to what is OB? So what is B basically? Yeah, it will be minus I cap plus j 0 into j cap plus k cap. Okay, so that is what my OB vector is. Now minus OA vector, right? OA vector is I cap plus 2j cap plus k cap. Okay, so yeah, this would be equals to yeah, minus 2 I cap and minus 2 Jacob and 0. So yeah, this is the direction. So what is the calculate the direction? If they are asking me to calculate the direction, so I have to actually find out the unit vector. So how do I find out the unit vector? So we simply, to find out the unit vector, right, you just simply have to divide by the magnitude of that vector and you will get the unit vector, because the magnitude of a unit vector is 1. That's why I will divide by the magnitude. So this magnitude will become 1 basically. So what is the magnitude here? It is 2 square plus 2 square under root. So magnitude of any vector is basically under root a square plus, like, x square plus y square plus z square. Magnitude basically means the distance from the origin of this particular point. Okay, so this is nothing but like a triangle, right? So there is one triangle here, okay, one triangle here, and of course in the 3D, in the z axis also there is another triangle. Okay, so we can use the Pythagorean's theorem basically. So this would be like, I'm not going into the proof right now because that is not of our concern. So this will be basically minus 2i minus 2j upon under root 4 plus 4, that is 8. Okay, that is 2 root 2. So that would be I minus j upon root 2. That's it. This is the unit vector direction. Okay. Now similarly you can do BA. BA would be nothing but, what is the final value? Final value is A, right? So it will be OA final destination minus the initial destination, and then again you can divide by the magnitude. Whatever you want to do, you can do. Okay, that is totally fine. But one thing, one special thing you'll observe, that your BA vector, right, will come out to be negative of AB vector, because that is intuitive, because in the formula itself, right, I'm writing the opposite, so it has to come negative. So your direction of BA vector would be basically opposite. So it will be I plus j upon root 2. You can derive it, you'll get the this value. It will just be the opposite of initial AB vector. Okay, so that's the case over here. Now again there are many vectors. One such vector is equal vector. Okay, you can read all these vectors, right? Free flowing vector. So free flowing vector are any vectors that uh, can have any direction. Okay, coordinates are not written, hence they are free flowing. So sorry, they have a direction, right? They have a magnitude, but their coordinates are not written, so they can be anywhere. They can be placed anywhere in the xyz plane, xyz coordinate system. Okay, they don't have any proper coordinates. This, right, if this has a coordinate, right, I can find out this coordinate. If I have the information about this vector, I can find out this final coordinate. Okay, that is possible from this formula, right, from this formula. Okay, but here, right, both the head and tail of the vector are not like, they have not told me the coordinate, right? So these are basically free flowing vectors. Okay, then we have parallel vectors, basically means whose direction are same. Okay, vectors with same direction, right, then they are called as parallel. Anti-parallel vectors with opposite direction, so exactly 180 degrees. Okay, there is a shortcut way to find out whether vectors are parallel or anti-parallel by taking the dot product. Okay, we can take the dot product, and from there we can say, so dot product or cross product. uh, uh, Actually cross product. Yeah, cross product. Then we have collinear vectors that lie basically in the same plane. So same plane basically means that, let's say I have my uh, x, hold on a second, this will be x, this will be y, this will be z. Okay, so I have this plane over here, right? I have this plane over here. Now uh, all the vectors, right, if one vector is lying in this plane here, other vector is lying in this plane here, so if they are in the same plane, then they are called as collinear vectors. They lie in the same plane. Okay, so for two vectors we call them collinear. For three vectors we call the same thing as coplanar. Same plane. Coplanar basically means same plane, right? Okay, collinear also can be told as like in a two-dimensional space, right? Sorry, yeah, that, yeah, that is what collinear basically means. Yeah, for two vectors. Now concurrent vectors, what are concurrent vectors? That have their tails lying at the same point, okay? Their tails are tight. Those vectors are called concurrent. Orthogonal, the angle between the two vectors is 90. Like there is a way to check orthogonality by taking the dot product. Okay, so yeah, that's the next topic basically, the dot product of a vector. Okay, it is not also called as the scalar product. So what do we mean by dot product? If I am taking the dot product of two vectors, it will be nothing but the magnitude of A into magnitude of V into the cos of the cosine of the angle between the two vectors. It is similar to the power, like power factor, right? So let's say I have two vectors here, A and B. Okay. Now let's assume the angle between those two vectors is given as 195 degrees. Okay. So what will be the dot product of A and B? Let's assume that magnitude of A is equals to 1, magnitude of B is equals to 1. So the dot product of A and B would be, you will say that it is magnitude of A into magnitude of V into cosine of angle between them, that is 195 degrees. Okay, and you will be, so this will be cos of 195 degrees, and this will be absolutely wrong. So this angle, right, actually is the what do you call, it is the obtuse angle. Okay, obtuse angle meaning the angle must lie in this range 0 to 180. But here you have told 195. How can you say that it has to lie between 0 to 180? So if this angle is 195, right, this whole thing will be 360. So how much will be this angle? It is 360 minus 195 degrees. Okay, 360 minus 195 degrees. So this will be 360 minus 195, that is 165. So now you will write, it will be magnitude of A, magnitude of B into cos of 165 degrees. That's it. Okay, very simple. So uh, so you will write the lower angle, right? This is also an angle between these two, right? So you will always write the obtuse angle between them. Okay, you will write the obtuse angle between them. I hope that is clear. Now few more important points are there. Let's say I have vector like this, arranged like this, right, and this angle is 60. So will you say that angle between them is 60 degrees? So always whenever we compare the angle, right, we always compare with tail to tail, the tail to tail angle. We never compare the head to head angle, right? Always connected from the tail to tail. Angle between vectors which are connected from tail to tail. So what we can do is we can shift my vector, right, in the same direction. That is always allowed. Shifting of vectors in the same direction is always, sorry about that, is always allowed. Okay, that is totally allowed. So just give me 1 second. Yeah, now just I will just move the mic once. Yeah, so what I will do, let's say this vector is A and this vector is B. I will shift the vector, both of them, right? So we'll shift both the vectors. So one vector will go here and other vector will go here. So this will be A, this will be B. Shifting is totally allowed. Now what is this angle? This angle is still 60. So this angle also will be still 60. So the angle between them is 60, no problem. But always you will compare the tail to tail. Sometimes what will happen is they will connect like this. Okay, and they will give you this angle. Now you have to actually shift your vector in this side, right? You have to compare the tail to tail angle. So now things will be a bit different. Your A vector will be in the bottom direction, correct? So this angle is 60 and this whole angle is 180. So the angle between your A and B would be 120, right? So even though they had provided you this angle, right, between A and B, they provided you this angle, right? They're not like connected between tail and head, right? They're just quite opposite. So this will be 120. Now you will connect them tail to tail, and then you can ideally say what is the angle between these two. Okay. So if that is clear, now what is the geometric meaning of dot product? So geometric meaning, like as we can see that if I am, let's say, applying a force to this box, right? So how much of the force is actually useful, that is getting used to move the box on the right hand side, and how much of the force is not getting used? So whatever force that is getting used, that we can find using dot product. So dot product is nothing but the projection along the uh, A vector. So let's say I have two vectors, right, A and B. Dot product would be the projection of B on A, or the opposite, projection of A on B or B on A. It is the what quantity of B vector is along A. So that is what quantity is the magnitude. Let's say if the magnitude is B, it will be mod of B cos theta. Okay. Then what I can do is I can multiply by so I can multiply by mod of A and divide by mod of A. So this will be nothing but A dot B, this quantity. Okay. So yeah, that's how the dot product actually came into existence. Okay, that's how the dot product was defined. Basically, we have to define a quantity that represents the projection. Although you might say, sir, it does not exactly represent the projection because there is a division of magnitude of A. Yes, you are correct, right? But that's how we defined it basically. So A dot B will be equals to magnitude of A into magnitude of B cos theta. Okay, that's how the dot product came into existence. There are a few properties. If I'm doing A dot B or B dot A, both are absolutely same, no difference. If I multiply any scalar to any vector, right, ultimately the scalar will come outside. Okay, I can do A dot B separately. Okay, no problem. Scalar product is distributive with respect to vector addition. So let's say I'm doing dot product, right, with addition of B vector plus C vector. It will be A dot B plus A dot C. Okay. Product of a vector with itself. If I'm taking the dot product of a vector with itself, it will be nothing but the magnitude whole square. Okay. So vector square is nothing but the dot product of the vector itself. How? So when I'm taking the dot product of a vector with itself, that means the theta is 0, right? If theta is 0, it will be like this will be magnitude of A into magnitude of A, that is magnitude of A square. So A dot A, that is A square, A dot A is equals to magnitude of A square. Okay. So whenever you see any magnitude whole square, right, of a vector, that means it can be represented as dot product with itself. Okay. uh, okay, magnitude of resultant vector. Okay, so let's say I have a vector R that is the addition of two vectors. So I hope you remember, like you understand how to add two vectors. So I can add two vectors like this. So let's say B vector is here, right? I have to add A vector. So I can shift the A vector here, and this A plus B would be this vector. Okay, that's how you can do the vector addition. So they are telling me that if I want to calculate the magnitude of this resultant vector, that will be what? It will be magnitude of A plus B vector. Okay, or what I can do, I can take square root and then square, like it's just the same thing, right? Square root and square, they will cancel. So ultimately it's the same thing, but this will actually help me in doing one thing. So I know that magnitude whole square is nothing but the dot product, right? So then if I break it down, so your resultant vector, right, comes out to be magnitude of A square plus magnitude of B square plus 2 A dot B. This quantity is A dot B. Also your resultant vector R2, which is the which is the subtraction, like A minus B, it will be magnitude of A square plus magnitude of B square minus 2 A dot B. Okay, that is what your dot product would be equals to. Okay, I hope that part is clear. So yes, so dot product of vectors, this is the thing. So now there are few things. Dot product of two vectors is maximum if and only if the angle between them is 0, because cos 0 is 1. So dot product will be maximum when the angle between the vectors will be 0. It will be uh, 0. The dot product between two vectors is 0 if and only if the angle between them is 90. So that's how we can check whether the two vectors are orthogonal or not. If I'm taking the dot product of two vectors and the resultant is coming out to be 0, that means the vectors are orthogonal, because cos 90 is 0, that's why they will be orthogonal. Okay, and dot product of two vectors will come out to be like negative. It will come out to be negative when they have some like opposite direction. When they have opposite direction, it will come out to be negative. Basically, if the dot product, right, of two vectors is just coming out to be their product of their magnitudes, that means their directions are same. Okay, that means their angle between them is 0. Okay, that is what it means basically. If their dot product is coming out to be the product of their magnitudes, that means their direction is same. If the dot product is coming out to be 0, that means they are orthogonal. That means the vectors are orthogonal. If their dot products are coming out to be negative of their product of magnitudes, that means they are anti-parallel. They are opposite to each other. Okay, I hope these points are clear. So similarly, I dot I, that is any unit vector along x cap direction, or j dot j or k dot k, all these values will be simply 1. Okay, I dot j, j dot k, I dot k, this dot product also will be simply 0, because these are orthogonal. These are set of mutually orthogonal vectors. Remember, I cap, j cap, k cap, all are set of mutually orthogonal vectors. That's it. Okay, so I hope that part is clear. uh yeah, so how can you simply do the scalar, like scalar product or dot product of two vectors? Simply, right, let's say I have a vector here, 3 I cap plus 4 j cap plus 5 k cap, and then I cap plus j cap plus 2 k cap, right? So I'm just writing in rough how to do the dot product between these two. So we know that, like, you can break it down. This will be I cap into j cap, I cap into I cap dot k cap. So I cap dot I cap is nothing but 1 simply, because it is nothing but magnitude of I whole squared, which is 1. Magnitude of I is 1. So this is fine. What about I cap j cap, right? I dot j would be simply 0, because they are set of mutually perpendicular vectors. So this multiplication will be 0, this multiplication also will be 0. Similarly, this multiplication will be 0, this multiplication will be 0. Similarly, this multiplication will be 0. So I will only get 3 terms. That is this term, 3 into 1, that is 1. Sorry, that is 3, plus 4 into 1, that is 4, plus 5 into 2, that is 10. Okay, so it would be, hold on a second, one second, simply 17. So 17 would be your answer. Okay, that's how you do take the dot product between two vectors. Now we'll come to a very important formula, how to find out the angle between two vectors. Remember, this angle is nothing but the obtuse angle, because that's how we derive the dot product, right? You always take the obtuse angle. So whatever angle you will calculate, this will be the obtuse angle between them. Okay, just be careful regarding this. This will be the obtuse angle. Okay, so angle between two vectors, right? So if I have a vector A, I have a vector B. Okay, so cos theta will be equals to A dot B by magnitude of A into B. So basically, A dot B is what? Magnitude of A into magnitude of B into cos of angle between them. So I can flip the formula, I can find out the angle between the two vectors. Okay, so that's how you can find out the angle. So here, right, this is a good example. So let's solve this basically. So let me actually try this question. Okay, so if the addition of two unit vectors is also a unit vector, then find the angle between the vectors. Already you know the answer, but let's try to solve it. Okay, if the addition of two unit vectors, let's say A plus B, is also a unit vector, then find the angle between those two. So uh, all of them are unit vectors. So the magnitude of A plus B would be also 1, because the addition is a unit vector, and magnitude of A is also a1, magnitude of B is also a1. So if this magnitude of AB is 1, right, so what I can do, I can write this in square format, correct? So this would be nothing but magnitude of AB whole square under root equals to 1, right? So I can say that then this would be what? This will be nothing but the dot product between itself, right? That will be A plus B dot A plus B, okay, equals to 1. So this would be just give me 1 second. Magnitude of A squared plus magnitude of B squared, and this will be plus 2A dot B, right? 2A dot B, and this is equals to 1, correct? So I can square it again, right? So if I square it again, the square root will go away, and I know what is magnitude of A, that is 1. What is magnitude of B? That is 1. So A dot B actually comes out to be minus 1 by 2 actually, okay? And what is A dot B? It is magnitude of A into magnitude of B into cos of theta. So cos theta actually is equals to 1 by 2 because magnitude of A and magnitude of B are 1. And when does cos theta becomes minus half? When it is greater than 90, right? When your theta is equals to 120, then your cos theta becomes negative, okay? So yeah, your vectors are actually somewhat like this. This is your A, this is your A, this is your B, and the angle between the vectors are 120. So basically what happens, the resultant is somewhere in the perpendicular bisector is a C vector. That also magnitude is 1, but its like direction will be somewhat in the middle, okay? That will be a C vector, and all of them will have the same magnitude, that is 1, okay? That is the beauty. Okay, so we learned about dot product. Okay, you don't have to worry about this component. Anyways, you can go through this, but mostly this will not be asked, but like very simple concept. Okay, now we will discuss about the cross product of vectors. So cross product again, right? Like for now we are just doing basis of vector algebra. We have not yet started vector calculus. Okay, we have not started vector calculus, just doing basis of vector algebra, that's it. So cross product is basically the similar thing, only A cross B. It is also called as the vector product, right? Previously dot product was called as the scalar product. This is called as the vector product, which is basically magnitude of A into magnitude of B into sine of theta with a direction. That's why it is called as vector product. What is the direction? It is a vector, it is a unit vector that is normal both to A vector and B vector. It is a unit vector that is normal to both A vector and B vector. So how to find out the direction of A cross B, right? Very simple. Like it is just like dot product, but instead of cos I have sine and I have a vector now. It is a vector quantity. It is not a scalar quantity anymore. That's why this is called as a vector product. Okay. So cross product of vectors, there are two things. First of all, magnitude and sine theta are there. Also, there is the direction of A cross B. So how to find out the direction of A cross B? Let's say I have A vector here and B vector here. So what I'll do, I will place my fingers along the A bar direction. Now I will curl my fingers towards B. As soon as I will curl my fingers towards B, I see that a vector is coming towards me, right? I see the thumb that is pointing towards me. That means it is coming towards me. So we represent it with a dot. So the direction of A10 vector will be coming out of the screen, that is dot outside. Now if I am doing B cross A, so whichever is first, right, in that direction I will place my fingers. So now I will place my fingers along B direction. Okay, I place my fingers along B direction. Now I will curl it along A. Okay, so I cannot actually, you can do it this as well. You can keep your like fingers along direction B, and now you will curl it towards A. If I curl it towards A, it is going into the screen. It is going into the screen. If it is going into the screen, it will be cross. If it is going into the screen, it will be cross. Okay. So that's how you find out the direction of cross product. So cross product actually came if when we tried to find out the area of a parallelogram with like vectors A and B. Due to that reason, cross product came. Okay, we are not getting into that for now. But interesting thing is there that you can find out the area of a parallelogram with cross. So what you can do? Let's say I have a vector OA and OB, right? These are the two sides of the parallelogram. So the area would be simply OA cross OB magnitude. Okay, because area does not have any direction, obviously, it is just a scalar value. So the same thing, right? Same thing is there basically. What is the area of a parallelogram formula? It is AB sin theta. The area of a parallelogram is nothing but AB sin theta, right? So that's how the this vector product came into intuition. Okay, so that's like that is the reason how this vector product was derived. Okay, so also you can find out the area of a triangle. So area of a triangle is what? Area of a triangle is half into base, magnitude of base into altitude h, right? So h, right, h can be written like this. So this b, let's assume that this b has a magnitude of b, mod of b. So along a, what is the component? Mod of b cos theta. Along its perpendicular, right? If I make a triangle, what is the component? It is mod of b sin theta, right? So the area of the triangle would be half mod of a into mod of b sin theta. So basically I can say that this will be half into a cross b, mod of a cross b, because magnitude, right? This a n cap is just a directional vector, it will go away, right? Magnitude will be 1. So that's how simple you can calculate the cross product. Okay, that's as simple you can calculate the cross product. So like this, these are the reasons why cross product was invented. Okay, dot product was invented to find the component, and cross product was invented to find out the area. But of course, with time we had found more important properties of cross product, and we use cross product in different uh, use cases, right? In different like areas. Okay, so there are few properties of cross product, like like dot product, right? It is not commutative. Previously, if I do a dot b and if I did b dot a, both were the same thing because there was no direction involved, right? But now direction is involved, because if I'm doing a cross b, so I will place my fingers along a and curl. If I'm doing b cross a, I will place my fingers along b and then curl. So the direction is getting involved. If the direction is getting involved, then that is a problem. That is a problem. Okay, so yeah, that is the thing over here. It will be opposite, it will be negative basically. So a cross b would be negative of b cross a. Okay, so yeah, that's it basically. So vector product is distributive just like its scalar counterpart with respect to vector addition. Okay, so a cross b plus c will be equals to a cross b plus a cross c. Okay, so and product of vector with itself will be 0, null vector, although it will have some direction, right? But I am doing like a cross a, that is magnitude of a into magnitude of a into sine of angle between a and a, that is 0. Sine 0 is 0, so magnitude of this vector is 0, but of course it will have some direction. Okay, the direction would be normal to a vector. So to define it, because we define this as a scalar quantity, right? Because ultimately if I'm doing cross product, we will get a scalar, although it's null vector, it is 0, it will not change anything, but still we have to represent it. To represent it, we say it is a null vector basically. Okay, that's it. So yeah, now few more important points. If I do cross with I cross I, that will be 0. If I do cross with j cross j, k cross k, all these are taking the cross product with itself, so those will be null vector. I cross j will be k. Now I will again follow the right hand rule. Okay, so I j k, or you can say x y z. So if I am doing ax cross ay, I will get az vector. How? So let's say this x vector is here, y vector is in this direction. So if I'm doing x cross y, if I curl my fingers from x to y, right, I'm getting the same direction as the z coordinate axis. So this is another way to understand the cross product. Okay. So if I have two vectors a cross b, right, instead of doing all this, right, that will be very hectic for you. We have a simple formula. If I have two vectors and I'm doing a cross b, then the a cross b will be nothing but the determinant of this particular matrix, I cap, j cap, k cap, and the a vector components and the b vector components. Okay, this will be the cross product. So if I want to find out the angle between two vectors, right, we can use cross product as well, but we have to put the magnitude sign. We have to put the magnitude sign. Now this will be a bit difficult because finding out the cross product is not simple. You will get a vector quantity here because I will have, if I break this mat determinant, this will be I cap into a2 b3 minus b2 a3 and so on, right? You can break this determinant according to you, minus j cap into something. Okay, so cross product will not be a cakewalk for you. It will be a bit difficult. Dot product was very simple, very easy to calculate, right? It was simply a1 b1 plus a2 b2 plus a3 b3. That was your dot product, if you remember. Okay, your cross product will not be cakewalk. So only use this formula if they have given you the cross product already. Then finding the angle between the two vectors will be much simpler for you. Okay. So a unit vector perpendicular, if they are asking you, let's say in the question they are asking you to find a unit vector perpendicular to the plane a and b vector, right, or to the vector a and b, what you will do, you will simply find out a cross b and then you will divide by the magnitude of a cross b, and that will be a unit vector that is perpendicular. So because unit vector is the direction vector, so they are just asking you a vector, a directional vector that is perpendicular to both a and b, and that information is hidden in the cross product, right? That was the definition of cross product. Okay, last few more things are left for vector algebra, then we will move on to our coordinate systems. Okay, so this is one thing that was there, scalar triple product. So if they are talking about scalar triple product, that means they are doing a dot b cross c, or you can flip it actually, this can be also written as a cross b dot c, or I can say a hold on a second but like the sequence should be same. Okay, sequence should be same, or if I change the sequence here, right, this will be, if I say it is a dot c cross b, then of course if I'm swapping the values, right, the sign will be reverse. Why? Because if I'm doing c cross b, right, then this rows will be swapped, and whenever we swap rows in a determinant, the value is negative. Basically the value is simply negative. Okay, so that's why this will be negative. Okay, this matter, this will be negative. So yeah, this also can be written as a cross c dot b. Okay, so like this kind of format is known as scalar triple product. So one way is to first you find out the cross product, then you take the dot with that, right? That is a way, definitely that is a way to solve, but there is a shortcut. Simply if they are asking you scalar triple product, what do, you just simply take the determinant of all the components, right, and you will get the result. It will be a scalar result because ultimately you are doing the scalar product, right? So this will be a vector product, this also is a vector. So vector dot product with vector would be simply a scalar. Here also vector dot product with vector would be simply a scalar. That's it. Okay, so I hope that part is clear. So that is a shortcut, that is the shortcut. Now the magnitude of the scalar triple product is gives the volume of a parallelepiped. Okay, magnitude of the scalar triple product gives the volume of a parallelepiped. This kind of shape is known as like parallelepiped, which is like a 3D parallelogram. 3D parallelogram, right? So just like the advanced version of square is parallelogram, then the advanced version of cube is parallelepiped. Okay, So yeah, then we have another last operation, that is vector triple product. What is vector triple product? So vector triple product is basically here, it is written here. So if I have three vectors and I'm taking the cross with all of them, right, that will be first, what you will do, vector triple product, like of course you can first of all do A cross C, then again you can do the whatever resultant vector you will get, you'll take the cross product, that you can do, right? But there is a easier way to solve it. There is a easier way to solve it, right? So what you do, if I have A cross B cross C, right, so first I will take the dot product with the far vector, so A dot C, and then I will multiply, I'll simply place the B vector here. So how to solve it? So basically, let's say I have to do uh, uh, let's say uh, I plus j cross k or I minus k cross k uh, j plus I, sorry, j plus k. Okay, these are all vectors basically. So what you will do, first of all, I will take the dot product of these two and I will place this as coefficient. So how will I place it? So this will be I dot j is simply 0 because it is 90. J dot j is 1. J dot k is also 0. So this will be 1, right? 1 will be here. Okay. Then I will just place the b vector as the coefficient. B vector as the coefficient, that is I minus k cap. That's it. I cap minus k cap. That's it. Okay. Then minus this uh, c vector. Again, I will place the c vector, right? C vector is the last vector, just as the coefficient. J cap plus k cap. And then I will take the dot product of the nearest vector. So first of all, I did the operation on the furthest vector, then I will do the operation on the nearest vector, that is A dot B. So A dot B will be this dot this, that would be 1. Okay. So now ultimately you can combine your result. This will be I minus k minus j. So I minus j minus 2k. Okay. So that's how simple it is. Otherwise, what you have to do, you have to take the cross product of these two vectors, then again you have to take the cross product of this. Like cross product is a very lengthy transaction, it takes some time, right? So to avoid all that, we have defined a simple formula, so you don't have to remember this, right? It's very simple and easy to remember, right? First you choose the furthest one and you keep the other one as the coefficient, and then you choose the nearest one, you take the dot product with the nearest one, and then you keep the other one as the coefficient. That's it. And of course there will be a negative sign, there has to be a negative sign. Remember, we'll get a vector quantity in a scalar triple product. We got a scalar quantity because it was A cross B, that is a vector, then dot C. So two vectors I'm doing dot product, I will always get a scalar quantity. Here I'm doing A cross B cross C, so this is also a vector quantity, then I'm taking the cross product, that means ultimately I will get a vector quantity. That's why I was getting a vector quantity. Okay, so now we will discuss about coordinate systems. So basically, right, why do we need to understand coordinate transformations? So if, let's say I have a line integration, okay, and this line integration is just not a normal line integration, I'm integrating along a path, I'm integrating along a path, along the curve. Okay, let's assume that that curve is nothing but the curve of circle. Okay, I have this function and I want to integrate this function along this curve. Okay, for this we will need the vector calculus. Okay, and more importantly we have to understand coordinate systems. So whenever a curve is given, right, that is circular in nature, so the best way to solve that particular question would be in the cylindrical coordinate system. Okay, if that particular curve is a two-dimensional curve, right, here we have all two-dimensional curve, then we can simply solve it in cylindrical coordinate system, or also called as polar coordinate system. Okay, if it was some spherical, right, three-dimensional spherical, then we will solve this using spherical coordinate system. Okay, So always remember one more thing, by default, right, if they're telling you to find out the integration along a curve, right, so this curve I can follow in two directions. One will be in the clockwise direction, other one will be in the anti-clockwise direction. Okay, so there are two directions, one is in the clockwise direction, other one is in the anti-clockwise direction, correct? So yeah, how will I solve it? That is the important question. How will I solve it basically? So by default, always assume the anti-clockwise direction unless and until specified. If it is clockwise, they will specify clockwise. Okay, now what is your polar coordinate? So polar coordinate, right, so my Cartesian coordinate consists of three variables, x, y and z. Polar is also similar, it also consists of three variables, that is rho, what is it, rho, phi and z. So z is z, z is not changing. What about rho? Rho and phi. So I can actually, rho, phi, right, are just a extension of my xy plane. So because we are considering a disk like structure, so let's assume that the radius of the disk is rho and the angle from the positive x axis is phi. So yeah, this is my rho. So rho is basically the distance from the center to the point. Let's say a point is lying here on the xy plane. Okay, so let's say the point is lying somewhere around here. Okay, so I'll project that point about the xy plane, and the distance from the origin of that projection in the xy plane is actually rho, and the angle from the positive x-axis towards that point is actually phi. Okay, and this distance from the xy plane of the projection and the point is actually z. That is not changing, that is same. Okay, so why is it useful? This is extremely useful if I want to solve like symmetry questions, right, wherever circular symmetry is given. Okay, we will see that. So basically your uh, definition of rho, definition of phi is given, you can read this. So phi will always be between 0 to 2 pi, rho can be anything between 0 to infinity. Okay, so if we move in the clockwise direction, then phi will vary from 0 to minus 2 pi, because minus 2 pi meaning I'll go in this direction, minus meaning in the clockwise direction, right? So if you remember, this was my angle, this is my x, this is my y, right? So if I go in this direction, angle is positive. If I go in this direction, angle is negative, right? Simple coordinate system. So similarly, if I go in the clockwise direction, angle is negative. If I go in the anti-clockwise direction, angle would be positive. That's it. Okay, so that's it, right? Now yeah, so now we can actually, so we can break down our x and y. So what would be x? So x would be, if this is rho, right, and this is a phi, so x would be basically rho cos phi. X would be my rho cos phi, and your y would be what? Y would be rho sin phi. Y would be rho sin phi. That's why, that's what I have defined over here. Okay, now what will be your dx and dy? What will be your dx and dy? So let's say I am integrating around this circle, right? So this circle, for this circle, right, for our case, the radius of the circle is fixed. So rho is fixed, so rho is not changing. Then the solution is even more simpler. If I want to solve this particular question, it will be even more simpler. Okay, so okay, any example? We don't have any example here. Interesting. Okay, let's say I will take an example, right? Let's say here, let me find out this value, integration of closed line integration of x y dx plus yz dy. Okay, yz dy. So along the curve, let's say curve is basically x square plus y square equals to 2 square. Okay, what you will do, you will write your x equals to 2 cos phi, you will write your y equals to 2 sin phi, right? You will write your because like now my it is not a like rho is not variable, only phi is varying, so the integration will be even simpler. Okay, you can find because this closed curve, right, basically means that my I can only say my phi is varying from 0 to 2 pi. Why, like, could we have solved this in Cartesian coordinate system? Definitely. So what is this? So then, right, it is very difficult to solve. Why? You have to find out the limits of your x and limits of your y. Okay, here both x and y both are varying, both x and y both are varying in this case, right? X and y both are varying, but if I choose circular coordinate system, only a single thing is varying, so that becomes much simpler for us to solve. That's why we solve it always in the polar coordinate or the cylindrical coordinate system. Okay, so dx would be 2 of minus sin phi cos 2 of minus sin phi into d phi. Okay, so I'm differentiating with respect to phi basically, and dy would be 2 of cos phi into d phi. You will replace those values over here, right, and you'll integrate your phi from 0 to 2 pi, so it will be going from 0 to 2 pi. Your x, what will be your x? 2 cos phi. Your y will be 2 sin phi, so this will be basically 4 or 2 sin 2 phi d phi. Okay, plus this, plus again dy is nothing but 2 cos phi, sorry, don't forget here dx is there, right? So you have to replace your dx as well, which is minus 2 sin phi d phi. Okay, and your here also this will be 4 or 2 sin phi, what is this? Sorry, this is not z, sorry, cannot keep it z, right? Well, let's say this is y square, so this will be basically 4 sin square phi into d phi, correct? 4 sin square phi into 2 cos phi d phi. Okay, and it will go from 0 to 2 pi. Now you can solve this integration. Okay, much simpler. Now let's say if it was not in yx, if it was dz dx, now will you use the same transformation as the cylindrical coordinate system? Sorry, as a, yeah, no, what you'll do, right, you'll follow this formula. So again you'll break your, so because it is in the xz plane, right, you'll break your xz plane into again rho and phi, because your circle is also along the xz plane. Okay, but what will be your x and z? So will your x be again rho cos phi and z be rho sin phi, or will it be the other way around? How can you decide? So this thing is decided by this, correct? So after x we follow y, after y follow z, after z we follow x, right? So when xy was there, x was with rho cos phi and y was with rho sin phi. Similarly, if I have y z, then y will be with rho cos phi, z will be with rho sin phi. Similarly, if I have zx, z will be with rho cos phi and x will be with rho sin phi. That's it. Other things will remain same as it is. Okay, they will not change. Like there are few more transformations, right? Polar transformations like this. Let's say the curve is not exactly at the origin. The center of the circle is not or at origin, right? Then how will you transform? So then you will say that your x, right? Your x will not be rho cos phi anymore. It will not be rho cos phi. Your x would be x naught plus rho cos phi. So all these will help you in solving questions. Okay, just like we have a very basic question here. Okay, like mostly they will give the center 0. If they don't give you the center 0, then how will you solve these kind of questions, right? Then you have to replace with your x with rho cos phi plus the center, whatever. Here the center is x naught y naught. So for the x coordinate you replace with x naught, for the y coordinate you replace with y naught. Okay, if y naught is 0, then it will be just rho sin phi or phi for y. Okay, that's it. The dx and dy will be same. Dx dy will not change, right? Those will be same. Okay, let's solve this question. This y dx plus x dy, circle with radius 2 and center 0 comma 0. Okay, so here, like because it is in the xy plane, so I'll replace my x with rho cos phi. Rho is 2 cos phi, and I will replace my y with rho sin phi, that is 2 sin phi. Okay, center is 0 comma 0, so it will be like easy for us to solve. Now I will replace my, so what will be my dx? Dx would be 2 sin phi d phi, minus will be there also, and your dy would be 2 cos phi d phi. Okay, so yeah, if I replace these things over here, 0 to 2 pi y give me 1 second, this will be yeah, y is 2 sin phi into dx is again minus 2 sin phi into d phi plus 0 to 2 pi x is 2 cos phi into dy, that is d phi. So this will be 4 minus 4 cos square plus 4 sin square, right? I can like take this integrations together, so this will be, so minus 4 cos square minus 4 sin square. So cos square phi minus sin square phi, so that is basically cos of 2 phi, right? Cos of 2 phi, cos square phi minus sin square phi is nothing but cos of 2 phi, and I have to integrate this from 0 to 2 pi, and don't forget that you have 4 right outside t phi. So integration of like basically it is a periodic function with period pi, but I'm integrating uh, till the twice the period, right? So integration will be 0. Now let's discuss why is this so important, why is this conversion so important. So if you do the same operation, right, if you do the same integration in Cartesian coordinate system, how will you solve in Cartesian coordinate? So what you can do is, first of all, what was your integration? Your integration was here it was y dx plus x dy, y dx plus x dy. So I can convert my all variables into a single variable. I can convert my all of the variables. Yeah. Oh, okay. So because it is a y dx, right? Here I have to write a function of x. Then only I can integrate this. Here it is x dy. Correct. So this is a function of so x dy. So I cannot integrate this, right? Because I don't know what is x in terms of y. So I will write my x in terms of y. How can I write it? So the curve is given, right? That is x square plus y square plus equals to 2 square. So from that I can say that y is equals to plus minus under root 4 minus x square, or x is equals to plus minus under root 4 minus y square. Both are true, right? And you have to choose both positive and the negative solution, because if I square this, this equation will be satisfied. Here also if I square this, this equation will be again satisfied. No problem. Okay. So that's it basically. Now, yeah. So how to integrate this? So what is y dx? So y value I know. Y value is plus minus 4 minus x square. But when shall I choose plus and when shall I choose negative? How shall I determine that? It's very simple. So I have to integrate over this whole circle, right? So what I can do is, let's say from this point to this point I'm moving. In the by default I will assume clockwise. So from this point to this point I will move. So what is the change in x? It is from x equal to 2 to x equal to minus 2. So in this whole region, what is my y? My y is always positive, correct? So here in this whole region I will replace my y with plus 4 minus x square, and I will go from x equal to 2 to x equal to minus 2. That's it. Okay. Now in this whole region, again in the bottom part, I will again, because I have to complete a whole circle, because I have to integrate over the closed curve, right? Over the closed curve. That means over this whole circle. So I have finished the integration of the first half of the circle. I have to finish the integration of the second half of the circle. Correct. So in the second half, right, I will start from minus 2 to plus 2. Okay. I will start from minus 2 to plus 2. So I started from minus 2 to plus 2. So yeah, minus 2 to plus 2, and in this region, what is my y? My y is negative. Okay, in this region my y is negative. That's it. So y value is negative, minus 2 to plus 2. That's it. Okay, and again plus, similarly what for x dy, x is equals to plus minus 4 minus y square. So again I can start from here, the region where my x is always positive and the region where my x is always negative. Again you can repeat the same experiment, right? Ultimately what you will see, these are just dummy variables, right? These are just dummy variables. The integration value is same actually. These are just dummy variable, integration value will be same. So ultimately all of them will cancel out. So your overall integration would be 0. Otherwise solving this manually will be a bit of task. You have to again do that sin theta cos theta conversion. Okay, that's why this kind of coordinate transformation is actually very helpful to us. Okay. Similarly, if I have double integration, okay, if I have double integration, right, then the coordinate transformation is bit different. Okay. So if I want to for changing from dx to whatever, like in this case our phi was varying, our rho was constant. It was very simple, right? We just have written dx was equals to this. We can easily write what is my dx in terms of d phi. That is very easy. But in double integration sometimes it is very difficult. Okay. So there is a like fixed method. So let's say I have a function x and y dx dy. Now it is easier for me to integrate that in the polar coordinate system. Okay. Let's say x and y, now both x and y are varying. Okay. So here if two variables are varying, in the other coordinate system two variables will be varying. So rho and phi. Now it is not that simple like this one, right? It is not that simple. Now we have a fixed formula for this. Okay, because you see x equals to rho cos phi, y equals to rho sin phi. Both my rho and phi are variable. Okay, so then we replace our dx dy with the other two variables d rho d phi with a determinant or magnitude of j. With a magnitude of j. What is magnitude of j? J is basically the determinant of the Jacobian matrix formed using this basic formula. So do you have to remember it? You can put this in your short notes. Okay, it's very easy to remember. What is the Jacobian matrix? So from which variables you are transforming? Xy. So xy will be at the top. To which variables you are transferring? Rho phi. So that, because you see, I have to write here basically this j will be a function of rho and phi, correct? J will be a function of rho and phi. So definitely x and y will not be at the bottom, right? Because I will not differentiate these things with respect to x and y, right? I will differentiate these things with respect to rho and phi, so that I get this Jacobian matrix here. Like there is a reason as well, right? So if I say you that, let's say this is a simple xy coordinate system, okay, and in the Cartesian coordinate, your two-dimensional structure, right, strip is basically this one is dx and this one is, sorry, this one is dy and this one is dx basically, right? So the area of a small strip, any small strip that I take, right, it will be dx into dy. That's very simple, rectangular strip. But in polar, if let's say I want to consider a small area, right, how will I consider a small area? So what I have to do is I have to choose, let's say, a row, and then I have to move by d row. Okay, this is the yeah, then I have to move. So hold on a second. So this will be my row, correct? And let's say I want to choose a very small area. So I can increase this arrow by a d row length. Okay, so let's say I moved by a uh, small angle d phi. Okay, so this distance also, let's say, is d row only. Okay, so what will be this length? Basically this length will be nothing, because this distance is very small, right? So this length will be basically, okay, this is not properly visible. This angle is d row. Okay, so this length will be the arc length basically, that will be whatever is the radius here, rho d phi, correct? Rho d phi. So what will be the area of this particular section? It is nothing but a just area, because it is nothing but a rectangle, because this distance is very small. So this I can assume to be almost a straight line, because d phi is a very small angle. Okay, so the area would be simply rho d phi into, sorry, yeah, rho d phi into d rho, right? This length is d rho, this length is rho d phi. So your area would be rho d phi into d rho. So basically your dx dy, right, small area in x and y coordinate system is converted like this. Okay, so there is a method to this. You don't have to every time remember it, just remember this one, that's it. Okay, for three dimensional as well, the matrix will be not that difficult to remember, right? It will be d of x y z, write in according to the sequence, d of rho phi z, that's it. Okay, so yeah, so the right hand side matrix, right, your z part will be always, just hold on, if I am able to, if I have space, I don't have space. So your matrix, right, where shall I do it? Okay, let me do it here only. This will be dx d rho delta, like dx d rho dx d phi dx dz dx, this will be dy d rho dy d phi and dy dz. One second. dz0 dy sorry, this will be dz d5 dz that will be basically 1, right? This will be 1, dz will be 1, right? So that's how you can solve. Of course, in this case, what is my x? X is rho cos phi and y is rho sin phi, right? That is the conversion between coordinates. So simply you can directly write dx d rho would be with respect to rho. I will integrate. This will be cos phi. Okay, this will be cos phi here in two dimensional. This will be uh, simply rho minus sin phi. This will be sin phi. This will be rho cos phi. Okay, so if you multiply, you will see you will get out to be rho. So basically your dx dy will be converted into rho d rho d phi. That is what we have anyways proven with a example, right? So similarly, like here I am doing few double integrations. Okay, this is one of the double integrations that you can do. Okay, I'm leaving it up to you, that you can do as a homework. That you, if you have been given this function and if you have to do double integration along the curve disk, right? If they are always giving you disk, or if they are giving you some circular structure, then it is always recommended that you do this conversion. Okay, so I can do it, right? So simply how to do it? So first of all, you will replace your dx dy with rho d rho d phi. That is one thing. And you replace your y with, remember this is in the xy coordinate, so I will replace my y with rho sin phi, and I will replace my x with rho cos phi. Okay, that's it basically. So yeah, that's how you can solve it basically. So yeah, you can go through the solution. You can see like it's a lengthy one. I will not be solving it, but uh, yeah, like there is another question as well. If the centers are different, right? If the centers are different, then you have to replace your x with -2 with the center location. X naught plus rho cos phi and y naught plus rho sin phi. Then you have to further solve it. Okay. So yeah, that's how you solve basically. There are more integrations like this we have already learned in double integration. Like you have to plot the surface, then you have to put the strips. Sometimes plotting this is very difficult, so we can use our polar transformations to simply use this, right? So yeah, uh, here we are doing the same thing with polar transformations, but one thing is different here, that I cannot, because the curve, right, this is not exactly a equation of circle. Okay, so you cannot just put a equation because these are the limits of y. Okay, these are the limits of y. So basically this first one is the limit of y, right? The last one is the limit of x because it is a function of x. So here I need y equals to 0 to y equals to 4x minus x square. Anyways, you can understand from the integration order. So here, right, so for the upper limit, how can I plot? So it will go from y equal to 0 to y equal to this value. Okay, so if I square both sides, like I will see that my y, I can get to this equation. Okay, this is the, now this is the equation of a disk, but I cannot simply blindly just uh, replace my x equal to rho cos phi and y equal to rho sin phi, because this disk is not centered at the origin. So we replace x with rho cos phi and y with rho sin phi only when my disk is centered at origin. But here the disk is not centered at origin. The location of the center of the disk is 2 comma 0. That's it. The location of the disk is 2 comma 0. Okay, so yeah, you will replace your x with x naught plus rho cos phi and your y with rho sin phi. That's it. So your like your rho will vary from, but rho will vary, it's the equation of a disk. Rho will vary from 0 to 2 and your phi will vary from 0 to 5. So whenever it's a 2D structure, you will have two variables that will be varying. That is what happened, that we have learned in the previous integral calculus portion. Okay, so that's it basically. So yeah, you can solve it and you can definitely get to the solution. Now again in the triple integration, Like triple integration, again you can do the same like changes, right? Whatever I've discussed, you can do the same changes. Like again, there are few plots. Uh, like you can take help of the cylindrical symmetry. If there is some cylindrical structure symmetry, then again you will use the cylindrical coordinate system, or the pole, also known as the polar. Polar actually is mainly discussed when it is a 2D structure. Okay, when my rho and phi are variable, like I don't have another third dimension, that is z axis. I only have rho and phi. Okay, now it is called a cylindrical coordinate system when I have three variables that are varying, right? Rho, phi and z. That's it. Rho, phi and z. Okay. If I have a structure that is cylindrical or parallelepiped or cone, right? The cone like structure. Okay, then I will use the transformation, that is cylindrical coordinate transformation. If it's a sphere, then I will take help of the spherical coordinate transformation. And if it's some other shape, cuboid or something, then we will solve in Cartesian only, mostly. Okay. So like this equation, right, is very, I hope, like easy to understand. Like it's the cylindrical coordinate system. It is used to represent a basic cylinder. That's how the name came, cylindrical. Okay. So in cylindrical coordinate system, we have three coordinates: rho, phi and z. Okay, so rho is the distance from the this along the xy plane to the point. Okay, and phi is the angle from the x axis, positive x axis, and z is the basically height, right? So if I want to convert from cylindrical to uh, sorry, if I want to convert from Cartesian to cylindrical, how can I convert it, right? Transformation. So this is the transformation, right? X will be rho cos phi, y will be rho sin phi, and z will be same. Z will not change basically. Okay. So what will be this matrix? So this I had already, like this became rho d rho d phi dz, right? So it's again very easy to understand here, right? Even if you don't remember the formula, this formula, right? Without that also you can prove it. So this area, this small area is rho d rho d phi. Now if I take this into the 3D structure xy, so I am able to get this small area, right? This small area was rho d rho d phi. Okay. Now again, if I add another dimension, okay. Now I added another dimension. This will be just like the shape of a cuboid, and this length will be dz. So the overall volume, now it will not be area anymore. Volume would be rho d rho into dz. That's it. Okay, that is what it is written over here. Your dx dy dz, right? Volume in the small volume in the Cartesian coordinate system gets converted into rho d rho d phi dz. Okay. So yeah. So that is the conversion, or you can use the Jacobian determinant. Like remember also there has to be a mod sign. This will be with mod sign. Okay, mod. So you have to choose the positive value. Okay, don't choose the negative one. Mod sign is there. Yeah. So you can get a uh, paraboloid as well. Okay. So it is a 3D parabola, similar to 3D parabola. Then also you can do the conversion. Okay. Your x will be like what is the equation? So equation for a cylinder was this, right? This was the equation for a cylinder. Very simple. Okay, I hope you remember, like just your x will be exactly equals to x square plus y square will be exactly equals to a square, and your z will vary from 0 to h. Okay, all this I have taught in the previous integral calculus. So please make sure you watch the integral calculus, otherwise you will not be able to understand how to plot this. I have taught you curve tracing in the previous video, integral calculus. So please make sure you watch the integral calculus video. Okay, so to trace a paraboloid, your x square plus y square will be z. It will not, it will be equals to z. It will not be a constant value. It will be z. So this shape will be of a paraboloid. Okay. So again, you can do the same conversion. That is fine. Now there are few more things as well regarding the projection. Okay. I think if I solve a question, this will be more clear. Yeah. here. Let's say I have this question here, find the volume V. Okay, V is this and this. So volume, right? What is the formula for volume? Formula for volume is nothing but 1 dx dy dz. Similarly, formula for area is what? 1 dx dy. Okay, 1 dx dy. So that is the formula for area and volume. So yeah, that's it basically. So now so along the curve, whatever volume they have given me, volumetric surface. So this is my surface. Y square plus z square equals to 9 square. So it is a constant, right? I am in the yz plane and this is a constant and my x is varying from 0 to 2. So this is nothing but the volume of a simple cylinder. Okay, like we can easily solve it, right? So what is the radius of the cylinder? It is 3 square, so it will be 3, and the height of the cylinder is 2. So volume would be 2 pi r square into h, which is 2 pi into r square, that is 9 into h is 2, right? So this will be 36 pi. That is very easy. I think we have, yeah, okay. Sorry, what I'm doing, why 2 pi? It will be pi r square. That was for the perimeter, right? Yeah, pi r square into h, this will be 18 pi. Okay, very simple. Volume I can find out, but what if I want to use this formula? Because ultimately at the end these kind of simple structure will not be a given to you, right? It will be a difficult structure. So how to solve? So here if I see that I have to integrate dx dy dz. Okay, now the equation of the curve is somewhat like this. It is in the yz plane, right? So in the yz plane, what is my relation? X, y, z, then I have my x again, right? So first I have chosen x equals to rho cos phi, right? Then y rho sin phi. Otherwise, if it's a yz plane, I will choose my y to be rho cos phi and z to be my rho sin phi. Okay, that's the order basically. Okay. So now, yeah. So my y is equals to rho cos phi and my z is equals to rho sin phi. Although all these actually does not matter because ultimately your dx, dy, dz will be converted into rho, d rho, d phi, dz. But actually, yeah, this time, right, you will assume that your x to be z. Like previously your x, y, z was there, right? And you used to write your x to be rho cos phi, y to be rho sin phi, and z to be z. But now I will use bit of trick. So I will write my y to be rho cos phi, z to be rho sin phi, and my x to be x. Okay. So here still x will be there. Okay, it will be d rho, d phi, and dx. That is the trickery that I will do because my x is the range of x is very simple, right? It is varying from 0 to 2. Okay, it is range of x is very simple. I will write at the end it is varying from 0 to 2. What about rho and d phi? So technically, right, for the first one actually your rho is not varying. Your rho square equals to 9. That is rho equals to 3. Right, rho is always a positive number. It is just the distance, okay, uh, from that particular axis. In our case it will be from y axis. Okay. So actually technically I was wrong. This volume, right, is valid for this particular V. It is not valid for this, but because here it is just a cylinder, it is a hollow cylinder, right? And for a hollow cylinder the volume covered by the hollow cylinder, volume inside the hollow cylinder is definitely 18 pi, but volume by the hollow cylinder, it is not 18, it is 0, right? Okay. Because like then what is this? This is a solid cylinder. So the volume covered by the solid cylinder would be 18 pi. That's definitely correct. But by the hollow cylinder, it will not be 18 pi, right? Because it is not actually covering any volume. Like I can calculate the surface area. It is like how do I show you? So I have this particular box, right? So let's say this box is from inside, it was hollow, nothing was there. So this has a surface area. This has a surface area, right? But this does not have a volume unless and until it's inside particles, everything is filled up. Okay. So that is what I try to explain. So it has a surface area. Okay. So yeah, it is just like a sheet. Okay, it is just like a cylinder, hollow cylinder. Okay, hollow cylinder. Volume inside a hollow cylinder would be same. Volume inside a hollow cylinder and a solid cylinder would be same. Okay, that is for sure. But they have asked me how much volume V. So this V is 0 actually. This is not covering any volume because its rho is constant. That's why d rho would be 0, and if d rho is 0, there is no change in rho, right? Rho is not a variable, rho is constant. So this will be 0 for the case 1. For the case 2, we can definitely solve. For the case 2, your y will be rho cos phi, z will be rho sin phi. So your rho square, rho would be less than 3. Okay, rho would be less than 3. So yeah, here my rho is variable. Rho is less than c. Obviously, rho has to be greater than 0. So rho is varying from 0 to 3. And what is your phi varying to? Phi is going from 0 to 2 pi because it's just covering a whole circle. Remember, your phi is with respect to the y axis this time, right? YZ. Your phi is with respect to the y axis. Okay. So phi will go from 0 to 2 pi. Now you can simply solve it. So if I solve it, right, so this will be rho square by 2, and it will go from 0 to 3. Okay. Then d phi would be like, it is not a function of rho, so I can directly write it. It would be, just give me 1 second if I'm able to delete it. For some weird reason I'm not able to delete it. No problem. No problem. Still I will not be able to delete it for some reason. Okay, no issues. Recently this is lagging too much. That's too bad. This will be into 2 pi 2 pi into your dx is varying from 0 to 2, right? So it will be 2. Okay, so this will be basically 3 square by 2, that is 9 into 2, that is 18 pi. So you will get the same answer basically. So this time the surface was very easy. Okay, what if the surface was a difficult surface? Then it would be very difficult for you to solve. Like we will come to those difficult surfaces. Okay, now there is a third method to solving it. Okay, first one was very basic, it's simple, like volume formula. Second one was with this changing coordinate system. Third one is using strips. Okay, this one will seem very like it will just seem very similar to the previous method, but once I will show you the next question, it will not be similar. So here what we do is, first of all, we identify the axis of symmetry. Okay, I see about x axis, right? My cylinder is symmetrical, right? Because about x axis, like the center is at the x axis, the axis of cylinder is at the x axis. Okay, so I will place a sun, on the axis of symmetry. Okay, then I will take two strips. First strip would be along the axis of symmetry. Okay, that will find the condition for the upper limit and lower limit of x. Okay, I got one condition. And then if I take the projection of this particular surface, what will I see? So if I place a sun on the axis of symmetry of a cylinder, so let's say this cylinder is here, right, and I place a sun. So what will be its shadow? Basically its shadow will be all of these particles, right? All of these particles will come in the xy plane and it will form basically a circle. That's it. All of these particles will come here and it will form a disk, not a circle, sorry, it will form a disk. Okay, like this. Now basically, right, your triple integration, what I'm doing, I'm converting my triple integration into double integration, and we know how to solve double integration. We know how to solve double integration. That has been taught to you in the previous lecture, previous class. Okay, here I'm just telling you how to convert a triple integration into double integration. So first I will take a strip, right, that will take out this condition x equal to, like, my lower limit and upper limit of x I have got, x equal to 0 to x equal to 2. Okay, I've got that, right. uh yeah, so I have got that. Now so I can write my dx, right. So this dx dy, I can simply replace my dx with x equal to 0 to x equal to 2. So this now has been converted into a double integration problem. Okay, this is a disk. Now you can take your strip and simply solve it. That's up to you. I'm leaving this part up to you, right. This will 2 will come outside. Now we can solve it. Okay, so again I can solve another integration like this, right. So here let's say I have to find the volume bounded by the cylinder x square plus y square equal to 4 and the planes y plus z equals to 4. So y plus z equal to 4 would be this plane. Okay, you can plot basically your x is varying from minus infinity to plus infinity. So your x is going from minus infinity to plus infinity. So there are infinite lines like this. Okay, z equals to 4 minus y, z equals to 4 minus y is just a line like this. Okay, so I can have infinite lines like this, right, because my x is varying from plus infinity to minus infinity. So it will form a plane basically. So my cylinder is this, right, this one is my cylinder. Okay, this one is my cylinder, but they are asking me what is the volume bounded by the cylinder and the plane this, and z equal to 0. Z equal to 0 would be this xy plane basically. Okay, so basically they are asking me the volume of this particular curved section. Okay, how will I find it? Again, what is the axis of symmetry? This time the axis of symmetry is z axis, right. So first of all I will draw a strip along the z axis. So from that I see the lower limit of that strip is z equal to 0, the upper limit is z equals to, because this is the equation of a plane, that is equals to 4 minus y. So this is equals to z equals to 4 minus y. Okay, so if I have to find volume is what, 1 dx dy dz. It is not that simple, right. I cannot use my transformations. This is because this particular volume is not cylindrical, it is not spherical, so it is something weird, curved surface area, right. So I have to use basic formula 1 dx dy. So what I can do, first of all I can integrate my with respect to dz. So I know the limits of z, that is equal to z equals to 0 to z equals to 4 minus y. So this will be converted into 4 minus y into dx dy, and again I will place my sun along the axis of symmetry, that is z axis. Okay, if I place my sun along the axis of symmetry, if I have a curved surface like this, right, if I just place a sun, I will just get a square, right. If I just place a sun, the shadow will be just a square, because this curve, all these things will not be shown. Okay, so if I place a sun, right, all these particles will just join here, right, and this will be just like a circle, this will be just like a disk. Okay, this will be just like a disk. That's it. So its structure would be disk. Now again it's up to you, right, you can solve this. you have to find out the double integration 4 minus y dx dy, and you're along about the disk. So I hope you can take the steps and solve the equation further. This part was new to you. This part has been covered in the previous R-PYQ series, previous video, integral calculus. So I will not cover it over again. Okay. So that's how you can solve. You can arrive at the final solution 16 pi. Of course, it will be somewhat less than this value because it is somewhat curved, right? Bit of volume is lost. So it will be 16 pi. That's it. Okay. So yeah, that's how you can solve. Now I will come to the spherical coordinate system. Spherical coordinate system is basically a sphere, right? Where your x, y, and z, right? This is my distance from the x axis, along the x axis, along the y axis, along the z axis. So a point can be defined like this. I can walk x units along the x axis. I can walk y units along the y axis. I can walk z units along the z axis. So I will arrive at my three-dimensional point. So how is a point defined in the same spherical coordinate system? So there are three variables here: r, x, and sorry, r, rho, r, theta, and rho. Okay, there are three variables: r, theta, and rho. So first, what I will do, I will draw a sphere of radius r. Okay, then I'll move an angle theta from z axis along the sphere. Okay, then I'll move a angle phi from the x axis along the sphere. So that if I move these many locations, then I will reach my same point as this. Okay. So what is the conversion? Basically, the conversion is your r would be x square plus y square plus z square. Okay, it is the distance from the origin. Theta is the angle measured from the positive z axis. Okay, and rho is the angle measured from the positive x axis. So if theta is the angle measured from the positive z axis, so if I write this is, let's say this distance is r, right? So what will be r cos theta? R cos theta would be equals to your z, correct? And your r sin theta would be equals to your r sin theta, right, will be the resultant of my x coordinate and my y coordinate. Okay, x and y basically. So this can be written. So what is the x? So this part is the resultant, right? R sin theta. So if I and this angle is phi. So if I multiply r sin theta with cos phi, I will get the x component. If I multiply r sin theta with sin phi, I will get the y component. That's it. You don't have to remember anything, right? That's how the conversion works basically. So I hope it is not difficult. And how to identify whether it is a sphere? So the equation of a sphere is its radius will be fixed. That is x square plus y square plus z square will be equals to a. And if this is the equation of a hollow sphere, right? If its radius is fixed, x square plus y square plus z square equals to a. Okay, I don't think this is required. This is not required. Only this much is required, right? X square plus y square plus z square is equals to a square. Then this will be a equation of hollow sphere, because I will only cover the outside surface, right? X square plus y square plus z square less than equals to a square. This will be the equation of a. This will be the equation of a solid sphere. Okay, this will be the equation of a solid sphere. That's it. So because I am covering the inside portion as well. Okay, so these are the transformations. I hope you know understand. So let's say you have been given a volume, okay, that is a sphere, x square plus y square plus z square less than some random value 3 square. Okay, so it's a like solid sphere, right? So how will you vary basically? So what you will do is, let's say I have to find out this volume 1 dx dy dz, correct? So you can say that your y is less than 3 square plus minus, or I can say like it is y, like if I just like equate with the corner case, so y would be equals to plus minus under root 9 minus x square minus z square. Okay, so this would be basically, so I can say that my y is varying from negative, so if it's a solid sphere, right, I can say it will vary from negative 9 minus x square minus z square to positive 9 under root 9 minus x square minus z square. Okay, and of course dy I will write first, then dx, and then dz. So what is my x varying to, right? So now again you have to put a projection. So if I put a projection, right, let's say about the z axis, because it is symmetrical about both z, x and y, any axis you can place, because I'm comfortable with x and y, I'm placing it about z axis here, right? I had first used y, dy, right? So the strip that I took was about the dy axis, so I have to take the projection on the y surface only, right? If I take a projection on the y surface, sorry, on the y axis, then I will get a circle. I will simply get a, so if I take the projection about the y axis, right, I will simply get a circle on the xz plane. I will get a circle on the xz plane. So on the xz plane, I will have it, not a circle actually, so a disk, right? I will have a disk. That's it on the xz plane. Okay, and then you can easily solve using whatever double integration technique, this next double integration, right? I was just telling you how can you convert your triple integration into double integration. That's it. So your task would be convert your triple integration into double integration, and after that you know how to solve double integration. That has been covered in the previous lecture. Okay, so there are many types of scenarios. First one is simply you have to find out the overall area throughout the sphere. Second type can be that you have to find the area in the first octane. So in 3 dimension, right, like basically in 2 dimension, each axis is called quadrant, 1 2 3 4. Okay, in 3 dimension, your each axis x, y and z, each particular area is called an octane, because I can divide it into 8 parts. So first part would be where both x, y, where all x, y, z are positive. Second part would be x, y positive, z is negative. X, y, x is positive, y is negative, z is positive. X is positive, y is positive. Sorry, x is positive. What I can say, x is negative, y is negative, z is negative. So there can be 8 combinations basically. Correct. That's why it is called. It can be divided into octants. So let's say if they are asking you to find out the area covered by this sphere, x square plus y square equals x square plus y square plus z square less than 3 square in the first octant. First octant basically means where all my x, y and z are positive. Okay, that is what my first octant means. Okay, so then you have to also take this into account. So then your lower limit, right, your lower limit will not be minus 9 minus x square minus z square. Your lower limit will be 0, because the lowest value of y would be 0, because it is in the first octant. So y has to be greater than 0, right? So your lower limit of y will change. So that is the difference if they're, let's say they're asking you to find out the area in the first octant. Okay, this I have already discussed. Like if this is the normal format where they will give you the v will be covered by a sphere, but sometimes what they do, they don't tell you what is v, they directly write this integration. So you have to identify this, they are talking about the volume of a sphere. Basically they are discussing about the volume of a sphere, because once you solve this triple integration, right, you will see that these will be the limits. So you will solve the, this is the limit for breaking the triple integration, and this part is for the breaking the double integration. So in the double integration, right, again you can take a strip, right, again like this is nothing but x square plus z square equals to, again this radius would be same as the sphere radius. Okay, if I am taking the projection Okay, if I'm taking the projection, right, this radius will be same as this sphere radius. Okay, so this will be basically, in our case, because this was 3 square, this will be also 3 square. Okay, x square plus z square plus 3 square. Okay, so that is the scenario basically. Yeah, so now you can solve this, right? So your, what will be the limits of z? Limits of z will be uh, so, oh, sorry, I'm solving about the x axis, right? So x would be equals to plus minus 3 square, that is 9, minus x square. Okay, 9 minus x square. So basically your limits will be, your y limit will be this, that is already fixed, right? I'm not writing the y limit. Okay, not writing the y limit. Your x limit will be, x will go from minus 9 minus x square to plus 9 minus x square, and of course your z limit will be z, the, like I am taking this strip from z equals to what, minus a, right, minus 3 to plus 3, that's it. I'm moving this strip, right? I hope you can solve the double integration. Okay, so that is what this format tells me. Okay, so this format is nothing but that telling me that you have to find out the volume of a sphere. Okay, basically your volume, your curved surface area is a sphere. Okay, that's it. And this particular format is nothing but, if your lower limits are all 0, that means they're discussing the surface, right, or the volume is a sphere in the first octant. Okay, sphere in the first octant, they're only considering the first octant. And remember, if I place here 1 dy dx dz, then this will be volume integration, but instead of 1 there can be a function of x, y and z. Okay, then this will not be a volume, this will be just a triple integration. So how to solve a triple integration? Just find the axis of symmetry, then write about the axis of symmetry, take a strip, write the lower and upper limits about the axis of symmetry, and then you take the projection about that axis of symmetry and you convert the triple integration into double integration, and then you can solve your double integration. Okay, that is how you solve it. So let me, if I have any question, like these are fine, these are all fine. Like you can find this J matrix, you can convert your dy dz dx into one magnitude of j dr d theta d phi using this formula. Okay, that is totally fine. This will come out to be, your j will come out to be r square sin theta. Okay, yeah, I don't think there is an example. Like we can take a very short example about the spherical symmetry. Let me take a very simple example. Let's say I have to find out this integration, 0 to under root 9 minus x y square, or let me say this x square minus y square, and this will go from 0 to 9 minus let's say x square, and this is going from 0 to 2. Okay, and here let's say I have x plus y plus z dy d dx dy dz. Okay, so that's about this topic. Okay, don't worry regarding this end stuff. Okay, they will not ask you much difficult questions from this. Like there's a separate chapter in vector algebra that will be covered in EMFT for EC guys. So you don't have to learn that much of coordinate system. This much is enough. Okay, I will tell you a few other things later on as we will come along. But for now, just understanding this much is enough. Now we will like, don't worry if few things are confusing, because they will not ask you any difficult questions from here. This was the prerequisite of vector calculus. Now we will understand, like we will actually start our vector calculus. So let's start with few basic terms of vector calculus. The first one being a scalar uh, point function. Okay, so scalar point functions are those functions which does not have any directions involved, like f of x, y, z, x plus y plus z, x square plus 2y plus 2z, x square plus z square plus y, whatever, right? Example, temperature, work done, potential energy, all these things. Now, vector point functions are those which have a direction as well, which are functions of x, y, and z, as well as they have a direction, like electric field, magnetic field, right? Electric field has a direction, also it's a function of x, y, and z, correct? So yeah, example, electric field, magnetic field, position has a direction and a magnitude, right? Distance, velocity, acceleration, all these are vector point functions. Okay, so this is one very basic example of vector point function. Let's say f of x comma y comma z equals to x j cap. So if I move along x axis, okay, so at x equal to 0, what is the value? 0, j cap. So it's a null vector. At x equal to 1, what is the value? J plus j cap, right? So plus j cap will be along y direction, correct? So that's why it is like the arrow is drawn like this. At x equal to 2, it will be plus 2 j cap. Direction is along y, so it is plus 2 j cap. Similarly 3, 4, like this, right? So these are basically all the directions. Okay, not only at integer values, integral values, they will be at like no like non-integer value as well, right? I've just drawn it just for showing you, but like they will be everywhere basically. When x is negative, okay, this will be, when x is -1, this will be minus j cap, and minus j cap is in the opposite direction of y axis, right? That's why you see the arrow direction also has changed. So that's how you draw basically vector field. So this is also called as a vector field. Okay, that's why you see the name electric field, magnetic field, right? These are called as vector field lines. Okay, now there is a operator known as del operator. This is known as delta or del operator. Okay, this is a vector quantity. Okay, similarly like the differential operator ddx, right? If I include ddx with I cap plus ddy with j cap plus ddz with k cap, then it becomes a vector quantity. Okay, it becomes a vector quantity, and this is called as the del operator. And this one, if I take the dot product of del with itself, it will be what? This dot with the same thing, right? ddx of I cap plus dty of j cap plus dtz of k cap. Okay, so yeah, if I take the dot product, so if I take the dot product, this will be this ddx whole square, that is nothing but d square dx square. Okay, and similarly like the I dot j cap component will be 0, so it does not matter. J dot j will be d square dy square plus d square dz square. This operator is called as a Laplacian operator, which is a scalar. Okay, so there are two operators, one is the Laplacian operator, another one is a del. Del is the most important one. Okay, Laplacian is also pretty important. So with this del operator, right, we can perform many operations. Okay, one is called as, if I am performing a scalar operation with the gradient, that is called as grad of phi. Sorry, with the del operator. Okay, if I am applying scalar product, if I am, this is also called an operator, just like multiplication. Multiplication is called as multiplication operation, right? Plus addition operation. So similarly, if I am performing del with f, that is also an operation. Just like if I am differentiating a function, right, dd of f of x, so I am performing the differentiation operation. Okay, so all these are operations. So this is also a operator basically. If I am performing delta or del with a scalar point function, then that operation is called as gradient. Similarly, like this is called as differentiation, this is called as a gradient, right? I'm doing gradient of phi of a scalar point function. Okay, now what will be the result? The result would be a vector point function. I can show you a very simple example. Let's say I have a function z plus y square plus x cube, okay, and I'm performing gradient on this. What is this del operator? It is d dx of I cap plus d dy of j cap plus d dz of k cap. Okay, and of course the function is there. Function will not obviously stay hidden. Z plus y plus x cube. Okay, so yeah, now if I perform, right, simply I will multiply. It is just like simple multiplication, that's it, simple multiplication. So I will multiply the I cap component here, right? With I cap I have this ddx, so I will do the partial differentiation of this function with respect to x, and in the coefficient I will have also I cap, that's it. Okay, so if I partially differentiate this function with respect to x, this will be 3x square, and I will have I cap. Then again I'll perform this multiplication, right? So I partially differentiate this function with respect to y, that is 2y, and I will multiply j cap. So this will be 2y j cap. Okay, then I will partially differentiate this function with respect to z, and I will multiply k cap, right? So this will be only one, right? So this will be only one k cap. So whenever we are operating our del operator with a scalar point function, then we will get a vector. Okay, that is what is written over here. So this is also called as the gradient operation. It has a physical significance, right? This actually this vector, right, gives me the normal vector. Okay, we will discuss about the significance of gradient. For now I have just told you how to calculate the gradient, that's it. Okay, now we have this vector point function, right? If I'm performing my del operator, if I'm performing an operation with a scalar using del operator, then that will be only that, like there is only a one possibility, that is a gradient. Okay, but if it's a vector point function, right, there can be two things. Either like with a vector, right, what is possible? With a scalar only simple scalar multiplication is possible. With a vector, either I can take the dot product of two vectors, or I can take a cross product. There are two kinds of products in vector, right? That is what we have learned in today's R-PYQ video only, right? So there are two possible ways. So that's why there are two possible outcomes here. One is known as the divergence, other one is known as the curl. So curl is the vector product between the del operator and the vector point function, and divergence is the scalar product or the dot product between the two vectors. Okay, all of them have their physical significance. We will discuss about the physical significance, don't worry. Okay, how to calculate divergence? Calculating divergence is pretty simple, right? Let's say if I want to calculate the divergence of the same function, okay, but to calculate divergence, this function should be vector. It cannot be a scalar point function, it has to be a vector point function. So I will convert this into a vector point function. So what we can do is I can write this as, let's say, pretty simple, I cap j cap and k cap. Okay, I cap, j cap and k cap, that's it. So now just give me 1 second. Yeah, so if I want to perform the divergence, so I will break it down. This will be I cap, j cap, k cap. This also will be I cap, j cap, k cap. Now things are a bit different here. Okay, so I will multiply the I cap component. So I cap dot I cap is simply 1, I cap dot j cap is 0. So all these components are gone. Only I have to find out the derivative of this particular I cap component, that's it. Okay, so derivative of this is simply 0, right? Again the same thing, j cap dot I cap is 0. I have to only perform this multiplication. So j cap dot j cap is 1. So d dy of y square, that is 2y basically. So this will be 2y. I cap dot j cap is 1. So that is fine. Then again k cap dot k cap, right? K cap dot k cap, and then differentiating this function with respect to z, that is 0. So this will be 0. Okay. So overall this will be equals to 2y. Okay, overall this will be equals to 2y. So yeah, that will be the divergence. So divergence, like if I'm performing divergence, right, then the result that we'll get is a scalar. Okay, if I'm performing curl, the result that we'll get is curl, sorry, vector. How to find out the curl, that will be discussed later. For now I've just shown you how to calculate the divergence and how to calculate the gradient. Okay, curl will be discussed later. So I'm taking an example, this function x square plus y square plus z square at 1 comma 1 comma 1, they're asking me to find out the gradient. Okay, you can simply perform this operation, you can find out the gradient, which comes out to be 2I cap plus 2j cap plus 2k cap. Now this thing is something significant. Okay, this thing is something significant, right? So if I plot the function, it is a sphere, right? This function is simply a sphere, that's it. Okay, and this vector is nothing but a vector that is pointing outwards. Okay, outwards of the sphere, like I cap, j cap, k cap would be somewhere here when all my values are positive. Okay, so basically, right, the gradient gives me a vector that is normal to my surface. That is the significance. All these things I have explained here, I will not explain because that is like not important for like this batch. Okay, but you can go through this. Ultimately the conclusion is your gradient would give you the vector that is normal to the surface. But let's say you only wanted to find the direction of the normal vector. Okay, then what you have to do, your gradient, right, it will give you a g vector that is a normal vector to the surface, but it is not a unit normal vector, because let's say you only want the direction, then you have to actually divide by the magnitude as well. Okay, if I divide by the magnitude, okay, then this, right, you this vector a rho p, that will be what, a delta of rho, sorry, cap would be equals to a delta of rho cap will be equals to your vector that is normal. Okay, so basically it will be grad of phi upon magnitude of grad of phi, that's it. Okay, that will be the unit normal vector. Okay, so yeah, that's how you find out the unit normal vector. Now this magnitude also has a significance, right? This magnitude of grad of phi, right, is the rate of change of the surface in the normal direction. If they, in the question they ask you find out the rate of change of the surface in the normal direction, then what they are asking you is just finding out the gradient of that scalar point function and putting the values. Okay, we can, I think, yeah, I have taken, like, these are examples how to find out the gradient. You will see that it is coming out to be normal function. Okay, or let's say if they are asking you to find a normal plane to the surface, this, okay, if they are asking you to find a normal unit vector, you have to simply find out the gradient. Okay, you have to simply find out the gradient. So here if I find out the gradient, right, what will be the gradient? The gradient would be del x, that is 2 I cap, plus del y 2y j cap, so 2x I cap 2y j cap plus 2z k cap. Okay, yeah, at point 1 comma 1, this is my grad of phi basically. Now one more thing is this constant is there. This constant also has a significance actually. Like what we do originally, actually what we do is we, like, let's say I have a function f of xyz. So what we do is we either write it like this. So I convert my function x square plus y square plus z square equals to 4 to this. My, I can take the 4 on the other side and I can write this equals to f of x comma y comma z. Okay, now if I find out the gradient, right, it will give me a normal vector in the direction of this, increasing in the increasing direction. Okay, if I like here that the same thing I have proven here, right? Let's say my function is x, okay, x equal to c, some function x equal to c, right? It will be just a plane in the yz axis, right? X equal to c, x equal to c is constant, it will just cover the plane. So now if I find out the gradient, right, if I take the c on the other side, c is just a constant, the grad of phi comes out to be I cap, which is basically, if I keep on increasing the value of c, right, if I keep on increasing the value of c, then I will go away from the x. So and I cap is also in this direction, right? The grad of phi is also in this direction, and if I keep on increasing my c, that is also going in, the planes are also going in the same direction. So basically this grad of phi represents where the curve along c increases. Okay, now I could have changed this, I could have made this c minus x. If I would have made this c minus x, then again if I would have calculated, like this time instead of putting c on the other side, I could have taken x on the other side and then named that function phi. Okay, so then if I find out grad of phi, it will come out to be negative. It comes out to be negative, okay, minus I. And what is your function now? Your function is phi equals to c minus x. That is what your function is. Your grad of phi always gives you the direction phi greater than 0, along the direction where phi is increasing. Here my phi was equals to what? X minus c, and when phi is greater than 0, that means x is greater than c. That means, let's say if c is here, right, let's see, c is 2. Okay, so x greater than 2 would be on the right hand side, x will keep on increasing. Here again I'll always get, like, the direction of my grad of phi would be increasing along phi. So phi greater than 0, what is my phi? Phi is this time c minus x, so c will be greater than x. Okay, so 2 is, let's say c is 2, so 2 is greater than x, right? That means x cannot be more than 2, x has to be less than 2. So x has to be less than 2, that means I have to go on the other side, right? It can be minus 2, it can be minus 3, minus 4, like so on. So I will go on the other side. Okay, so yeah, so if I go on the other side, so yeah, this will be on the other side, and that is the direction of my grad of phi that I have calculated. So grad of phi, you can say, gives me the direction where my function phi is increasing. Okay, and your function phi is not x, because this is not nothing but the equation of a surface. They will always give you a surface, right? And if you have to find out the normal vector of this surface, there are two possible outcomes. Either you can take the 4 on the left hand side, or you can take this whole function on the right hand side and then write that equals to phi. Whatever you write, it will not matter ultimately. There are two normal vectors, right? Whenever I have a, let's say, a surface, let's say I have this surface, right, rectangular surface. There are two normal vectors. One is on this side, if you see, other one is on my side, right? On my side there are two surfaces, right? One is this normal vector, another one is this normal vector. There, to this surface there are two normal vectors, this and this. Similarly, for a sphere, right, one normal vector will be coming outwards, pointing outwards. Okay, another normal vector would be pointing inwards. Okay, there are two normal vectors. So that is the thing over here. Now yeah, so now similarly for a sphere as well, right? If I take this 4 here, so what is the, if I have this xyz axis, x y z axis, okay, not this actually, x y z, yeah. If I take this function, let's say my phi is equals to x square plus y square plus z square minus 4. Now can you tell me where in which direction is my phi increasing? If phi is greater than 0, that means this function is greater than 0, that means your x square plus y square plus z square greater than 2 square basically. That means what? It includes all those spheres whose radius is bigger than 2. So it will include all these surfaces, correct? So my grad of phi in this case will give me a vector that is normal, which is pointing outwards of the sphere. Similarly, if I would have done it opposite, what I could have done? I could have done that my phi is equals to 4 minus x square plus y square plus z square. Okay. So my grad of phi would be what? What is my grad of phi basically? So my grad of phi, like what is the direction of the surface now? X, y, z. So it basically it includes all the spheres whose radius is less than 2. That means this spheres, right? So my grad of phi would be a normal vector to my original surface, which is pointing inwards. Okay. So just be careful what does your grad of phi give. So trust me, no one will tell you all these things, right? They will just tell you the formula of gradient, and they will tell you that gradient is just basically a normal to the surface. That's it. And everywhere else, they will not explain you all these things. Okay. But here I'm giving you the visualization. In a revision course, in a crash course, I'm telling you what even in their full course they don't tell you. Okay. All these things they don't explain in their full course. Okay. But in the crash course, I'm explaining all this. I could have skipped all this, right? Because it is anyways for solving the question. Maybe most of most of the cases this concept will not be used. Okay. Simply you will find out the gradient. It is just a mathematical tool, and you will get to a result. Okay. But one day, if IIT professors ask something conceptual, that day you will be able to solve from gradient, right? Because you actually know the meaning, you actually know the physical significance of gradient. Okay. What does gradient actually tell you? Okay, so you convert your f of xyz into phi. Either it can be 4 can go on the left hand side, or this function can go on the right hand side. Either way, your gradient will always give you the normal vector along the direction where your phi is increasing. Where your phi is increasing. Okay, so remember that thing. And if you have understood gradient, put a thumbs up in the video, and obviously comment down below that yes sir, I have understood gradient properly. Okay. So yeah, now there are a few properties of gradient basically. So this you can solve, right? You can this gradient of your surface at the point 1 comma 1 comma 1, you can put 1 comma 1 comma 1, and if they're asking you unit normal vector, then you will divide by the magnitude of that particular vector. That's it. Okay. So that is how you find out the gradient basically. Now these are the few very basic properties of del operator. If I'm performing gradient with sum of two scalar functions, simply I can individually find out the gradient plus minus. Simple. If I'm multiplying two scalar point functions and then finding out the gradient, then for that we have a rule. It is just like the chain rule, right? Let's say I am differentiating f of x into g of x, right? Then we say what we can do, we can break it down. We can keep f of x constant and you can differentiate g of x, so that will be g dash of x, plus we can keep g of x constant and we can keep f dash of x. Okay, so yeah, it is similar to the chain rule basically. Okay, and this one is similar to the quotient rule. Okay, f of x upon g of x. If I am differentiating f of x upon g of x, right, then again gradient, like gradient, if I'm applying it on scalar function, it is similar to differentiation basically. Okay, not gradient, sorry, del operator. Now the next thing is the directional derivative. Okay, it is the directional derivative. Okay, sorry, one, I think previously this was the divergence. Okay, divergence is a different thing, directional derivative is a different thing. What is directional derivative? So directional derivative is nothing but if I am calculating the gradient of a scalar point function at a particular point, and then uh, if some other vector is given, a directional vector m vector is given, and if I take the dot product of these two results, then this gives me the directional derivative. Okay, so directional derivative is the maximum rate of change along the given direction. Let us do example. Find the directional derivative of f equals to 3xyz at 2 1 comma 0 in the direction this. So basically what they're asking is find out the maximum rate of change of my scalar point function in the direction, in this direction. In this particular direction, what will be the maximum rate of change of my scalar point function? There is a physical significance. I am currently avoiding that because this is a crash course. Okay, I cannot obviously cover everything. Okay, so I'll just tell you like that this much is important. That's it. Okay, whatever is important, I'm telling you. Simply, first of all, if you have to calculate directional derivative, first of all, you find out the gradient of the scalar point function. So this time you don't have any constant, your function phi equals to f equals to 3xyz. So what will be the gradient? Gradient would be, I'll differentiate with respect to x, that will be 3yz I cap plus uh, 3xz j cap plus 3xy k cap. Okay, so yeah, this is my gradient basically about the point P, right? So the point is given 2 comma 1 comma 0, so x is 2, z is 0, so this will be 0 basically, x is 2, z is 0, this also will be 0 basically. Now this will be 2 into 1, 6 k cap, that's it, 6 k cap. Okay, so this will be 6 k cap, that's it. Okay, now I have got my gradient. I will just do the dot product with the direction given, right? So okay, so if they have given you this direction, right, first of all you have to find out the unit vector, because here, right, the formula for directional derivative, this is am cap. Okay, so you have to, like, if they have given you this direction, you will convert this direction into whatever vector they have given you, along which you have to calculate the directional derivative. You will convert that into unit vector. Okay, so unit vector for this will be simple, this will be 2 I cap plus 2 j cap minus k cap upon 3. Okay, so yeah, this will be 2 I cap plus 2 j cap plus k minus k cap upon 3. Only k cap component I will consider, other components are not there obviously, dot product. So this will be minus 2. So what does this minus 2 signify? This minus 2 signifies whatever is my scalar point function, right, x, y, z, whatever is my scalar point function, this minus 2 is the maximum rate of change along this direction at this particular point. Okay, this you have to unfortunately remember. There is a geometrical understanding, I'm not going into that right now. Okay, this is my function basically, scalar function at a particular point along this particular direction. What is the maximum rate of change of my function? That is what directional derivative tells me. So what you have to do, first of all, you have to find out the gradient of the scalar point function, then you will put the value of the point, you got your grad of phi, then you will find out the unit direction vector. Okay, and then you will simply take the dot product of the two vectors and you will get your directional derivative. That's how you solve for directional derivative. Okay, So another question, this question is here, right? So yeah, so we will find the directional derivative. Actually, somewhere I told you the definition of directional derivative bit wrong. Actually, directional derivative gives me the rate of change of the scalar point function along the direction. Okay, directional derivative gives me the rate of change of a scalar point function along the given direction. Okay, that is what directional derivative gives me. Now there is a very interesting fact that if I am doing the directional derivative along the normal direction of the scalar point function, right? That is what, if my am cap vector is equals to a grad of phi cap. So basically the direction vector is nothing but the normal vector along that particular point of the surface. Then if I compute the directional derivative, right, that gives me the maximum rate of change at that point of the scalar point function. Why? Because what is grad of phi dot am? Grad of phi dot am will be, because it will be magnitude of grad of phi into magnitude of am, that is simply 1, it is a unit vector, into cos of theta. Now when will this be maximum? When theta is 0. So if I just simply take the dot product with itself, with the same function itself, that will give me the maximum value of directional derivative. What is directional derivative? It is the rate of change of a scalar point function at a particular point along the given direction. So if I am getting the maximum value of directional derivative, that means I am getting the maximum rate of change of the scalar point function at a particular point P, because direction is fixed now, direction is along the normal direction. So a scalar point function will always increase maximum along its normal direction. That is a conclusion. So if they're asking you, find out the direction along which the scalar point function will increase maximum at a point P equals to xyz, then what you will do, you will find out the gradient, you will divide by the, you will make it unit vector, okay, and then you will put the value point, you will put the points, right, that is x equals to y equal to z, whatever the points is that direction is basically the direction along which the scalar point function will increase maximum. Okay, so a rho a uh, del of phi cap gives me the direction about which the function increases fastest. Okay, phi scalar point function phi increases fastest. So like this is an example. Let's say a given function f equals to xy plus yz plus zx. Find the following maximum value of the rational derivative. Maximum value of the rational derivative would be what? First of all, I find out the gradient of phi, that is basically equals to uh, y plus z I cap plus uh, yeah, this will be x plus z j cap plus y plus x k cap. Okay, so now they are asking me the maximum value of the directional derivative. What is the maximum value of the directional derivative? That would be this. What is the, like this is grad of phi. What is the direction vector? E rho phi. I have to divide by the magnitude. That will be simply y plus x plus z plus y plus, this will be, yeah, y plus x divided by magnitude of this whole square. So okay, this will be a task, y plus z I cap, let me copy this, this will be y plus z I cap plus x plus z j cap plus y plus x k cap divided by under root of y plus z whole square plus x plus z whole square plus y plus z whole square. Okay, so that's the thing basically. So here, right, if you uh, say like this is the direction vector, right? So what is your directional derivative? I have to take the dot product. If I take the dot product, it will be basically y plus z whole square plus x plus z whole square plus y plus z whole square. So ultimately, right, your dd maximum comes out to be under root of y plus z whole square plus x plus z whole square plus y plus z whole square. That's it. That is what your dd maximum comes out to be, right? So same thing I think I have, yeah, here also I derive the same thing. So what will be the value of the maximum directional derivative? This is the directional derivative maximum, or this is the maximum rate of change of the function, okay, of the scalar point function. Now what will be the value at a particular point? You will just put the value of x, y and z, then you will find out the directional derivative at a particular point. That's it. Okay, that's how you solve these kind of questions. So how to write a position vector in 3D? This simple thing, right? This I think you can follow along. This is not that difficult to write the position vector in 3D. Okay, I hope I don't have to explain all these things. So here, like, because this will be used here, find the directional derivative of the function at 2 1 comma 0 in the direction of acceleration vector whose position vector components are x of t equals to t, y of t equals to t square, z of t equals to t cube. Okay, so basically that's, I have to find out the directional derivative of this function along the acceleration vector. So what is the acceleration vector? It is basically its x component is t, so t I cap, its y component is t square j cap. Okay, its z component is t cube k cap. Okay, now at 1 second they are asking, so acceleration vector at 1 second would be I cap plus j cap plus k cap. Simply you have to find out the directional derivative about the direction of the acceleration vector. So let me find out the direction of the acceleration vector. Okay, a cap, that would be equals to I cap plus j cap plus k cap upon under root 3. Okay, so that is the direction of the acceleration vector. Now I have to find out the directional derivative. So for that I have to find out the gradient of this function, right? Gradient of this function. So gradient would be this will be 2xy plus z square I cap plus x square plus 2yz j cap plus 2zx k cap. Okay, so at this point, so I'll put the value of x1 and z, right? So this will be del grad of phi equals to 2xy, so this will be 4 I cap plus 4 j cap plus y square y is 1, so k cap. Okay, so now we will just take the dot product. If I take the dot product, right, this will be 4 into 1. Okay, somewhere I have made a mess up. So x is 2. Okay, direction of the, oh sorry, sir, I'm extremely sorry. So here, right, they have given you the position vector coordinates, right? So we know this thing, right? So basically your acceleration is d square x upon dt square, right? Double derivative of the position. So yeah, I'm extremely sorry, I was doing this blindly. So we actually have to differentiate. So your let's say your x component, right, of the acceleration vector would be differentiation of the x component twice with respect to time. So in this case this will be simply 0. So your acceleration vector does not have any x component. What about your y component? Y component would be d square y upon dt square. Okay, so yeah, this will be basically, I will differentiate the y component twice, right? So initially first term if I differentiate, that will be 2t, and second time if I differentiate, this will be simply 2. That's it. Okay, and similarly az, right, if I differentiate this function twice with respect to time, this would be 6t. Okay, and at t equal to 1, this will be simply 6. So your acceleration vector will be 2 j cap plus 6 k cap. I was wrong, extremely sorry. So this will be 2 plus 6 k cap, so divide by the magnitude, that is under root 40. Okay, under root 40. So now if I take the dot product, right, this will be actually here there should be a, okay, we can, what we can do, we can take the 2 common, right? If I take the 2 common, this will be actually j cap plus 3 k cap upon under root 10. So now if I take the dot product, this will be 4 into j cap, that is 4, 3 into k cap, that is 3 only, upon under root 10. So this will be the directional derivative. Okay, so simply I hope you remember, like, what is your acceleration vector? It is the differentiation of velocity, or it is the double differentiation of the position vector r. So basically here, what is the position vector? Position vector r of t is basically equals to t I cap plus t square j cap plus t cube k cap, right? And your acceleration vector would be equals to double derivative of your position vector, right? Or we can say it will be with respect to time, right? It will be double derivative with respect to time of my position vector. That's it. That's how you can find out the acceleration vector. Okay, that's how you can solve the direction derivative. Now one thing is there simply is how to write the equation of a line that is parallel to a particular vector. Let's say I have a vector I plus j plus 2k. How to write the equation of a line in the xyz coordinate? So what we do is, about, like, if it's passing through a point, let's say 1 comma 2 comma 3, right? So this you have to remember. Unfortunately you have to remember, but it is not that difficult to remember, right? It will, the equation of the line, right, passing through a particular point 1 comma 2 comma 3 parallel to this vector would be x minus 1 upon the coefficient of this component, I cap component, that is 1, equals to y minus this point 2 upon the coefficient of this component j cap, that is 1, equals to z minus 3 upon the coefficient of this component, that is 2, equals to any random constant k. Okay, that's it. So this you have to remember basically. So your x component will be proportional to the x component of the vector. That's how you remember. Your y component will be proportional to the y component of the vector. Your z component will be proportional to the z component of the vector or k cap. Okay, so you have to remember this because this can be used in directional derivative, because they can ask you this: find the directional derivative of the function at this point in a direction that is parallel to the line this. So they have given you this, right? So you have to find out which vector is parallel to this line, right? Okay, because they are asking you direction parallel to this line. So I can observe that it is passing. Okay, here this is it passing through 2 comma 1 comma 0. So if I put here x equal to 2, this is 1 by 2, right? If I put here 1, this is minus 1. That is not actually satisfying. That is interesting. Okay, x equal to 2. Something is wrong, I guess. Huh. Okay, okay. No, no. What is the equation? Actually, this is something different, right? This is just for this. This point is we have to find out the directional derivative at this point. But this is a equation of line. Okay. If you have studied 3D geometry, you will remember this is a equation of line. Now, what is this equation telling me? That this is a equation of line passing through the point 1 comma 0 comma 1 and parallel to the vector 2 I cap minus j cap plus 2 k cap. Okay, 2 I cap minus j cap plus 2 k cap. That's it. That is what the direction vector is. I have to first of all find out the direction, right? So I will divide by the magnitude, that will be 3 in this case. Okay, then I will find out the gradient of the function, and then I will just find out the directional derivative. That's it. Okay, if they would have asked you the maximum rate of change of the function, right, at the point this, then you don't need the direction. Even if they give you the direction, then this will not be the maximum rate of change. Maximum rate of change will be along the normal direction. That is simply a of grad of phi. That's it. I hope you understand these things. So please keep this in your mind, and of course I will give you notes. From that note also you can revise. Okay, I will give you the notes later on, you can revise. Now this gradient also sometimes can help us finding out the angle between two surfaces. How? So let's say I have this mobile phone and this mobile phone, right? I want to find out the angle between these two mobile phones. If you see, right, this angle between these two mobile phones. So what I can do is I can just give me 1 second. Let me see if I can hold this. So yeah, like this. So what I can do, I can find out the normal vector to this particular surface. I can find out the normal vector to this particular surface, right? So that normal vector, and if I am able to find out the angle between those two normal vectors, that also will be enough, right? So sometimes directly writing the equation and finding out the angle between the surfaces is difficult. So what we do, we find out the normal vectors between the two surfaces and then take the dot product, as you can see from here. Okay, and then if I divide by the magnitudes, right, I will get the angle. So theta would be angle between the two surfaces. Remember, theta will always be the obtuse angle, because there can be two angles here, right? This also is angle, correct? That will be the acute angle. Your theta will always be the obtuse angle between the two surfaces. There can be two angles between the surface. One is this one is this one. This one is 360 minus theta, this one will be theta. So always whatever outcome we will get from the gradient, right, we'll always get the obtuse angle. So we can take an example. We have to calculate the angle between two surfaces. How can I calculate? About this point 1 comma 1 comma 1. So what I can do, I can simply calculate the gradient. So I'll find out the normal vector to this surface. I will find out the normal vector to this surface. Okay. Then I will take the dot product. Then I will do the cos inverse, and I will get the angle between the two surfaces. So do you need to remember the formula? No. Understand conceptually, right? Angle between two surfaces. If I can find a vector that is normal to this surface, another vector that is normal to the other surface, I know I have got two vectors. How to find out the angle between two vectors? Using dot product. Okay, that's why basics are the most important one, right? So what is the normal vector to this surface? that is 3x square plus 3y square plus 3z square. Sorry, don't forget the I cap, j cap, k cap. Okay, and yeah, then I will put the point, that is at point 1 comma 1 comma 1, this will be 3 I cap plus 3 j cap plus 3 k cap, right? And okay, this is the vector 1, vector 2, right? Normal to the surface would be 2x I cap plus 2y j cap plus 2z k cap. Okay, then if I put the value of x, y and z, 2 I cap plus 2 j cap plus 2 k cap. Okay, now I have to simply do this operation. I have to find out the angle between these two vectors. How to calculate? I will take the dot product g1 dot g2, and of course don't forget to divide by the magnitude, right? g1 magnitude of g2 will be equals to cos theta basically. So these are the same vectors, right? Correct? Oh no, these are not the same vectors, sorry. So this will be basically 6 plus 6 plus 6, that is 3 into 6, divided by the magnitude. Magnitude would be, this will be 3 root 3 into 2 root 3. So this will be equals to 6 root 3 will be cancelled, which will be, this will be basically 3 root, yeah, sorry, 6 and 3 also, this will be 1. Okay, so when is cos theta 1? When theta is 0. So basically the angle between the surface is 0. Both their surface, both the normal vectors are pointing in the same direction. Okay, so they don't have any angle between them. Similarly this one is there, right? So first of all, one thing you have to remember, right, that if they're giving you some point, okay, if they're already giving you that point, then that means this point exists both in this surface and this surface, right? Then only like you can calculate the angle, because the angle will be there when they have a common point where they are intersecting. Otherwise, let's say this one surface is here, other surface is here, how will I calculate the angle between them? No, that does not make sense, right? You will calculate the angle between two surfaces only if they are intersecting. Otherwise, you will not calculate the angle. Okay, so here also, before calculating the angle between the two surfaces, always make sure that uh, this point, right, exists both in this surface and in this surface, surface 1 and surface 2. So if I check the point 1 comma minus 2 comma 1 on both the surfaces, you will see that it is satisfying the equations, right? Here also, if I put x equal to 1, y equal to 1, z equals to 1, so the left hand side is satisfying the right hand side, that is 3 equal to 3, so totally fine. Here also, if I put x equal to 1, y equals to 1, z equals to 1, the LHS is satisfying the RHS, so again it is absolutely correct. Okay, it is absolutely correct. So yeah, that's the thing basically here. So here they are asking us to calculate the acute angle. Acute angle is the angle that is less than 90. Okay, so let me, if I calculate the same, if I follow the same procedure, right, if I find out the gradient of surface 1, I think surface 2 is also here, yes, then if I take the cos theta 1, your theta 1, right, would come out to be like because this will come out to be negative, your dot product will come out to be negative, this will come out to be 100. But as they have asked you to calculate the acute angle, obtuse angle is the angle between 90 and 180, they are asking you to calculate the acute. So what you will do is you will this will be the correct hold on a second. This will be 100 degrees, but why do you do the yeah, okay. Yeah, so basically, right, as I have told you, this angle between the two surfaces can be this as well. Okay, it can be this angle as well, right? Sometimes it can be this angle as well, or the angle between this also can be the angle between the two surface, correct? Right. So like it can, sorry, I previously mentioned wrong. If I told you that that will be 360 minus theta, that is wrong actually. Here it is wrong. No, sorry, I was wrong. So angle between the two surfaces, right? Either can be this angle between the two normal vectors, okay, which is basically this angle, right? This angle, nothing but this angle. That's it. Or it can be this angle as well, correct? Or it can be this angle as well, right? Okay. So if this is theta and this is nothing but a normal vector, right? So uh, it is a normal vector of the this curve. Okay. So so how are they? This is also theta. Okay. But how is it doing 180 minus theta? That is wrong, right? Yeah. I guess this part is wrong. Cannot. This is, they're telling this is 180. They're extending this. Okay. This is kind of wrong. There I did it wrong actually. No, this is not correct. Because I will not be able to comment about this angle, right? I will not be able to comment because like this particular surface and this is different, right? These two are different things. No. So this part is wrong here actually. Uh, this part is wrong. This angle is the angle. Other angle I will not be able to comment actually. No, I will not be able to comment the other angle. So actually I will not be able to find out the acute angle. That is not possible. This question is wrong. Because here, right, if I basically, right, they're telling how will I calculate this angle? If I extend this particular line, they're saying this line and this line are same. No, they are not the same actually. Because this is the vector that is normal to this particular plane or surface. Okay, there is no relation between this particular surface and this particular line. So I cannot comment about this line, although visually it seems that this is the angle theta, but that is wrong. Simply if they're asking you the angle, you will just decode the angle. This question is wrong. I will modify this question. This question was wrong previously. Okay, so yeah, you cannot write it like this. This is wrong actually. So this question would be just finding out the angle. That's it. Okay, find out the angle. That's it. The angle will be 100 degrees. That is the answer. Okay, because 180 minus theta is wrong actually, because there is no relation between this extension and this surface. Okay, so the angle, like you will just find out the angle, that is 100 degrees. Angle between the normal of the surface, that will be this angle. That's it. Okay, now there are few properties on the position vector. What is the position vector? It is xi cap, yj cap, z k cap. Okay, so we will use the properties basically. So your r vector, that is also called as the position vector, is xi cap plus yj cap plus zk cap. Your magnitude r is nothing but the like magnitude x square plus y square plus z square. Your r is equals to under root of x square plus y square plus z square. That's it. Okay, so if I want to find out the gradient of r, right, it is nothing but r vector upon r. How you can solve it actually? So what will be my gradient of r? Gradient of r is basically, like there is a proof, like I will just show you a bit. Okay, so your r vector is this, right? You have to find out the gradient of r. R is this value. So gradient of under root of x square plus y square plus z square. If you calculate the gradient, it will come out to be xi cap plus yj cap plus zk cap upon this same function under root x square plus y square plus z square, right? So which is nothing but this value is r and this also is r vector, right? So your answer would be r vector upon r. Okay, r vector upon r. So this is a shortcut. If you want to remember it, good. If you don't want to remember it, you have to solve it. That's the only thing. Okay. So one more thing is there. Let's say I have a function of r. Let's say r square plus r plus 1. Okay, where r is this value, right? R is equals to x square plus y square plus z square. If I want to find out the gradient of this, and gradient is what? ddx I cap, ddy j cap plus ddz k cap. So if I want to find out the gradient of this, correct? This will be basically like you can use something similar to chain rule. You can use something similar to chain rule. So this will be f dash of r into r vector upon r. What is it? It is nothing but the differentiation of this function with respect to r. That will be 2r plus 1. And then simply I will put r vector upon r. That will be your answer. Okay. Yes, you can solve it simply. Like what is r square? R square is x square plus y square plus z square. What is r? R is under root x square y square z square plus 1, whatever it is. Then you calculate the gradient. Ultimately, then if you rewrite everything in terms of r, you will get back to this value. Okay. So this is a shortcut that you can use, and this is a very good shortcut. Very good shortcut. So make sure you use this shortcut. Okay. So unfortunately, this you have to remember. Okay, this is a very good shortcut. This you have to remember. This thing you have to remember no matter what. Okay, you have to remember it no matter what. Similarly, here if I'm performing the Laplacian operator, right, then this will be like again you will apply the chain rule but twice. So first I will double differentiate my function with respect to r plus, then I will have this 2 by r in outside into f dash of r. Okay. So yeah, these two things you have to remember actually. So this 2 by r comes by if I am differentiating like this delta square. So some 2r comes, right, like that. So yeah, these two things actually you have to remember, unfortunately. Or what you can do is, because so what you do, you remember this one. Okay. So your del gradient of f of r is this value, right? This value. So what if I take the gradient again? Right, that is what? That is nothing but del square, correct? And let's assume that this function is a g of r. What is your g of r? G of r is this value. Okay, but okay, sorry, I will not be able to take the gradient. I have to take the dot product because gradient is with respect to, okay, this, right? Don't worry, we will come to this. Once we will study divergence, I'll come to the proof. Okay, you don't have to remember this, right? Without even remembering this, I'll come to the proof in the divergence. Okay, don't worry. So just remember this one. This one is the most important one. Remember this one. Okay, Laplacian, I'll come to the proof. If you remember this one, you can derive it with the help of divergence. That's it. Once you study divergence, right, you will be able to solve it. Don't worry. Okay. So like basic examples in the exam, sometimes they have asked you to find out the gradient of ln of r. R is the position vector. So instead of solving it manually, writing r under root x square plus y square plus z square, then solving it manually, you can directly solve in one go. So what is your f of r? F of r is equals to ln of r. So your gradient of ln of r would be simply, I will differentiate this function with respect to r, that is 1 by r. Okay, then it is r vector upon magnitude of r basically, or r. So this answer will be your r square, like r vector upon r square. Okay, that's your answer basically. So that's how you can solve in one line. Otherwise it will take a huge time if you want to break it down. Sin r, your f of r is sine of r. So your gradient of f of r would be basically differentiation of this sine of r, that is cos of r into r vector upon r. Similarly, sine of ln of r, like I hope you get the point, right? Now we can, like, what will be the derivative with respect to r? This will be cos of ln of r into by r into r vector upon r. Okay, what about this function? It will be r raised to the power n by n minus 1 into n into r upon r. So this will be actually n r raised to the power n minus 2 into r vector. That's it. Okay, so these are a way to solve this basically. Like there is another way, like you have to find out the find and if the Laplacian of the function is 0. Okay, for now you can use the formula, this formula. Otherwise, like let me try to derive it actually. Let me try to derive it. So if I am calculating the divergence of this particular function, okay, so if I'm calculating the divergence of this particular function, right? So let's say this f dash of r has few components. This is equals to uh, no, let me keep f dash of r only. So f dash of r upon r into x I cap, f dash of r upon r into y j cap, plus f dash of r upon r into uh, z k cap. So if I'm taking the dot with this, right, divergence is nothing but the dot product. So uh, so I will differentiate this particular part with respect to x. Okay, there can be two things. Yeah, I can apply the chain rule here, right? If I apply the chain rule here, so it is a product of two functions. First I can differentiate this part and keep this as a constant. So that would be f dash of r upon r, and that's it. That's it, right? And the next time I can differentiate this function, right, and keep this as constant. So that would be basically plus x into del of del x f dash of r upon r. Similarly, I will have uh, other things as well. Okay, I'm just thinking, we are running out of space. We are running out of space. Wait, we have space here. Yeah. Just trying to prove it actually. So this would be, give me 1 second, f dash of r upon r plus x del x f dash of r upon r. Yeah. Similarly, I will have f dash of r upon r plus y into del y f dash of r upon r. Okay. This will be z into t dz. Okay. So this I can take common. This will be 3 into f dash of r upon r. But why is there a 2? There should be 3. That is what I'm thinking. Okay, I have 3 into f dash of r upon r. But what will I do of this particular thing? Okay, I have to differentiate with respect to x. Partially differentiate with respect to x. So what I can do is I can again break this function. So I can write d of dr into dr dx. So here I can replace my ddx with ddr into dr by del x. Okay, that's it basically. So now what is del r by del x? So what is r? R is under root x square plus y square plus z square. So if I differentiate my r with respect to x, what will be it? It will be basically, this will go on the downside. The overall result will be x upon r. Okay, you can solve it. It will be x upon r. Basically, it will be like this whole, if I differentiate this with respect to x, this will go like, what is the power? Half. So half will come outside. Then I will decrease the power by 1. So this will be minus half. So that will be in the bottom. So this is r. And of course, x is there because I have to then differentiate the inside function. X square plus y square plus z square, that will be 2x. So I hope you know the differentiation of this function with respect to x. That's it. Okay. So this is the value, right? This del, I can convert this del r by del x to this. So this x by r can be outside basically. This x by r can be outside. So overall this will be what? X by x into x by r, right? That is x square by r. Now don't forget I have this thing still lying around, right? Del r of f dash of r upon r. Okay. So what will be this differentiation? Okay, I'm differentiating this function with respect to r. Now it is very simple. Now it is very simple. So this will be f double dash of r minus f dash of r, like I hope you know what is the quotient rule, and upon r square. That's it. Okay, this value is this one. Okay, and of course x square by r is at the outside. X square by r is at the outside. So overall this would be x square, hold on a second, differentiating with respect to r. Yes, correct. So x square upon r cube into f double dash of r minus f dash of r. Now similarly for this particular term I will have plus y square by r cube. Okay, so what I can do, I can take all these things in common. So this will be always present in all the terms. I will have x square plus y square plus z square, that will be present. I hope I am correct. If I differentiate this one, yeah, this 1 by r will become outside, and hold on a second, half will be at the outside, half into 2x, that 2 will be cancelled, this will go bottom, this will be x upon x square by r. If I differentiate this particular function, I will have, yeah, yes, correct, f double dash by r. That's it. Now yeah, for the other ones as well, this will be there. This was only due to this term, correct? What was the result? So everywhere I had f dash by r, f dash by r. 3 plus f dash by r also will be there. 3 plus f dash by r also will be there. Now what I can say, what is x square plus y square plus z square? It is nothing but r square. nothing but r square. Okay, so this is r square, so this r cube and r square will be cancelled, this will be 1 by r. So 1 by r minus f dash by r plus 3 f dash by r, which is basically nothing but 2 f dash by r. So I have 2 f dash by r minus f double dash by r, sorry not minus, sorry, plus f double dash r by r. So if I whatever formula we have derived, okay, there is a 1 by r as well, so something is going wrong. Why is my f double dash, oh sorry, I missed a part, right? So whenever I'm differentiating this function, if I'm differentiating this function, it will be the denominator into differentiation of the numerator, that is f double dash of f double dash of r, minus differentiation of the denominator into the numerator, that is f dash of r. So sorry, I missed a r here, there should be r. So like I'm doing this in a hurry, but I hope you are able to understand. This will be r, so actually there will be r also, so this will be only f double dash of r. Now why am I saying you, trust me, in any books, any place, any textbook, you will not find this proof. Okay, I have just done this in rough, but you can do this in fair manner, okay, by yourself, because this video, right, these videos are meant for you to do the task, not for me. Okay, so try to do it, you will get back to this result. And if you don't want to remember this, right, just solve this, just remember this part. Okay, you have to remember this one, unfortunately you have to remember this one. If you remember this one, right, you can derive this, how I have told you. Okay, so trust me, in no books, nowhere this proof will be given, nowhere. Okay, so please go through it again, you will realize what kind of proof I have done. Just one trick I have used, that I have replaced my del x to del r into del r del x, that's it. That is the one single thing. Actually properly I should have written it outside, yeah, that's the proper way, because otherwise you will be confused that this should be inside here. No, this is on the outside. Okay, so that is only thing that I have done. Other than that, I have not done any manipulation, I have just simply proved. So of course you will say, sir, in exam hall, do I have this much amount of time to solve, do the proof? Of course you don't have. Okay, but if you don't want to remember the formulae, this is the only option that is left. If you don't want to remember the formula, this is the only option that is left, that you have to prove in the exam. That's a uh, uh, that's like a, what do you call, a adjustment that you have to make. Either you remember the formula or you prove in the exam hall, that's it. So if find n if the Laplacian of the function is 0 and n is not equal to 0, r is not equal to 0. If Laplacian of the function is 0, that means I will apply the Laplacian operator. So if I apply the Laplacian operator, this will be del square into r raised to the power n. So first of all I will write f double dash of r. F double dash of r would be n into n minus 1 into r n minus 2 plus f dash of r upon r. F dash of r is n into r minus 1 upon r. So I can take common my r raised to the power n minus 2. This will be n into n minus 1, that is n square minus n plus n. Hold on a second, n square, yeah, minus n minus n plus 1, so not n, so yeah, plus n only. This will be n, right? Yeah, n. So this will be n square equal to 0. Okay, now r is not 0, n is not 0. What will be the valid answer? Hold on a second, I'm differentiating this once. This n minus 2 I can take common. Sorry, don't forget this. That's why I also tend to forget the formula. 2 by r, right? This is 2 by r. 2 by r. Don't forget the 2. This will be 2. So this will be minus n square plus 1. Sorry, I can take n common as well. Sorry. I can take n common. So n into r raised to the power n minus 2 n minus, this will be n minus 1 plus 2, that is n plus 1 equal to 0. Because the Laplacian is 0, they have told me. So of course this cannot be 0, so your n plus 1 has to be 0, so your n has to be minus 1. That is the proper solution. The value of n would be minus 1, then only the Laplacian would be 0. Let's now come to the like questions, from where questions will be asked. Like gradient they can ask question, Laplacian they can ask question, they can ask next question from divergence. Divergence, like I have already discussed, it is the dot product with the del operator, that's it. Okay, very simple. Let's compute the divergence for these functions. So this will be, right, del dot r vector, that is 3, because I hope you remember the del operator. I'm taking the dot product, I will only consider the I component, I cap component. So just give me 1 second, something is okay, that is, I will only consider the I cap component. So this first, due to I cap, I will differentiate this with respect to x, that will be 1. Then I will differentiate this with respect to y, that will be 1. Then I will differentiate this with respect to z, that also will be 1. So this will be equals to 3. Similarly, for the second part, if I differentiate this with respect to x, this will be 3x square. 3x square plus 3y square plus 3z square. It's very simple. I hope you remember what is my del. ddx I cap ddy j cap plus ddz k cap, and then you will take the dot product. So only you will consider the I cap component and you will differentiate with respect to x. You will consider the j cap component, you will differentiate with respect to y, and similarly. Okay, so there is physical significance of gradient. You can understand that with the help of flux. So whatever flux lines comes in, right, and whatever goes out, your your divergence tells you the what is the overall like total increment or decrement of flux that goes through the surface. So your divergence tells the total increment or decrement in the flow of fluid or any flux lines throughout the whole surface. Okay, so yeah, that is what, because you see what is the divergence, it is the differentiation of the x component with respect to x, it is the differentiation of the y component with respect to y, and differentiation of the z component with respect to z. So it tells you the rate of loss or gain of fluid per unit volume. Okay, actually volume is not considered, per unit volume it tells us. So not that important, this much is, knowing this much is only important. Okay, now if the divergence is set to be 0, that means whatever flux that is coming in and whatever flux that is going out are same, because there is no net increment or decrement in the flux in the volume, closed volume. Then it is called to be, if for civil guys, it is said to be the surface is incompressible. Okay, now if the divergence is greater than 0, so it behaves as a source. Okay, so it is similar to elliptic flux lines, right? In elliptic flux lines we see that divergence is not equal to 0, because if I take a positive charge, then the elliptic flux lines will always come out. Okay, if I choose a negative charge, then the elliptic flux lines will always come in. So for this particular case, the divergence will be positive. For this particular case, divergence would be negative, because all the flux lines are coming towards me, so we assume it to be negative. Okay, that is the thing. Yeah, also one more thing is there, that if the electric flux density increases, right, then also the divergence would be positive. If the electric flux density decreases, strength of electric flux density, the number of flux lines decreases, then we say the divergence to be negative. Okay, if the electric flux density does not change, we say divergence to be 0, it is not changing. Similarly here, right, here you can see that light source, the divergence of a light source would be positive, because it is acting as a source, it is providing light. So from everywhere the field lines are outwards, so we say divergence is positive. And everywhere the sink point, the divergence is negative, so it is basically absorbing all the light. So a black hole, the divergence would be 0. Okay, like the example, I'm just taking the example, for a black hole the divergence would be 0, because it absorbs everything. Black hole absorbs all the lights, correct? So yeah, that's it. Now one more thing is there regarding solenoidal field. So what are solenoidal field? The field whose divergence is 0. Sometimes in civil they tell you that if the uh, surface or the function is whose divergence is 0, then we say that it is incompressible. And in electrical we say that a field is divergence free if its divergence is 0, and a field can be a magnetic field if its divergence is 0, right? So in a magnetic field, right, we know that magnetic field lines always exist in a closed loop. Magnetic field lines always exist in a closed loop. So let's say if I have a surface over here and some magnetic field lines are passing by, right? So because they will again have to come back, right? So whatever field lines that will pass through this surface, the same field lines that will come outside the other surface. So overall there is no net increment or decrement through the surface. So that's why we say that magnetic fields are always divergence free, or also called as solenoidal fields whose divergence will be 0. We can take an example here. So to calculate the value of lambda if A is said to be divergence free, simply what you have to do, you have to compute the value of divergence and equate equal to 0, and you will find out the value of lambda for that particular condition. Okay, let's solve it. So if I find out the divergence, this will be lambda 2x y plus four y minus 2 of xy. This will be equals to 0. So what I can do is I can take 2xy common. This will be lambda plus 1 equal to 0. So from this I get, for any value of x and y, if ever my lambda is minus 1, then the divergence will always be 0 no matter what. Okay, so it will always satisfy this condition for any value of x and y. Just hold on a second, let this noise pass. Yeah, lambda will be equals to minus 1. That will be the answer. So now we will come to curl. So curl also has a physical significance. How can you compute the curl? Curl is bit different. For curl, you have to find out the determinant of this particular matrix. So you will have x component, y component, z component of the vector point function. So you will write ijk, then you will write the differential vector, right? This is the differential del operator vector, and then you will write the x component, y component, z component, and then you will solve. Similar, like I have solved. What is the curl of R? Curl of R is 0. Whenever curl is 0, it is said to be irrotational. Okay, I will show you. It is said to be irrotational, correct? So here, if I find out this, let's say if I want to calculate the curl of this particular function, right? What do I have to do? Curl of A. So I will write ijk, then I will write here del x del z x cube y cube z cube. This will be equals to this will be 0. This also will be 0 simply. Your curl will come out to be 0 here. So there is a fact actually. If ever your x component of the vector has only function of x, and your y component of the vector has only function of y, and your z component of the vector has only function of z, then we say the vector field to be irrotational. That is, your curl will come out to be a null vector. Okay. So like few key points are given. Like we know the gradient of R. It is nothing but if you remember, this was the formula. Where did it go? Yeah, f dash of R into R vector upon R, right? So if I do f dash of R here, this will be f dash of R would be 1, because your f of R is R, so that would be 1 into R vector upon R. It's very simple, right? The gradient of R is simply R vector upon R. That's it. The divergence of R is 3, very simple, and curl will be 0. Like that is a key point. Please remember, if your x vector component is only a function of x, your y vector component is only a function of y, and your z vector component is only a function of z, then you can simply directly say from observing the vector point function that it is a irrotational field whose curl is 0. Okay, so uh, curl represents the circulation or rotational effect of vector field. So the magnetic field, if I have a clock, magnetic field exists in a closed loop, so it will have some curve, right? So if it's clockwise, we say the curl is not equal to 0, it will be positive. If it is anti-clockwise, we say curl is not equal to 0, it is negative somewhat, it will not be equal to 0. Okay, okay, I cannot comment about the direction. I think for anti-clockwise the curl comes out to be positive, for clockwise curl comes out to be negative, but definitely I can say that it will be non-zero. Curl will be non-zero for magnetic fields, right? We know it exists in a loop, so it has a rotational effect. So if it has a rotational effect, then the curl will be always non-zero for a magnetic field. But the curl of an electric field, we know electric field, right? Does it have a rotational effect? No, it exists in straight lines. So if it does not have a rotational effect, then we say that the curl of the electric field is 0. Curl of electric field is 0, it is a irrotational field. You see here, curl of electric field is 0, it is a irrotational field. Now it may be possible that if curl is 0, that divergence is 0 or not 0. Okay, but these are not two things that are related, right? If the curl is 0, divergence may be 0, not 0. What does divergence say? Divergence tells me that what is the net flux that is going through a particular surface volume. I cannot comment about the net flux by understanding or knowing the curl. Two things are very different. Okay, so yeah, here if you see, does it have a rotational effect? No rotational effect, so curl will be 0. Here also, does it have a rotational effect? No, curl is 0. Here divergence is also 0. Here curl is 0, divergence is also 0, because ultimately there is no net flux that is passing through this surface. Okay, here the curl is not 0, and if I say the divergence is also positive, because whatever flux is coming in, more flux is going outwards. Okay, so divergence is also positive. So yeah, there can be many things, like these are the few conditions that you can see. So yeah, a vector field is said to be irrotational if basically the curl is 0. Electrostatic field lines are irrotational. Good thing to keep in mind. Same thing I have told you, that whatever I was previously telling you, if I have a irrotational vector field, then I can certainly say that its x component will be only function of x, its y component will be only function of y, its z component will be only function of z. Can I say it? Yes, you can say it. Yeah, or like sometimes okay, no, like this reverse is not true always, because there is few conditions applied, but this forward is always true. So if my scalar point function x component is only function of x, y component is only function of y, z component is only function of z, then definitely the field will be irrotational. But if a field is irrotational, the reverse may or may not be true. Okay, you can take a few corner cases, you will see they are not true always. Okay, so if I have this particular field and they are telling me that this is irrotational vector field, then what will be a plus b plus c? So what you can do, if you know it is a irrotational vector field, then you will simply find out the curl. Okay, you will write this matrix equation, then you will solve the matrix. This you will equate equals to 0. If I solve this, this will be b, hold on a second, this will be c minus 1 into I cap plus 4 minus a into j cap plus b minus 2 into k cap. So c would be equals to 1, a would be equals to 4, and b would be equals to 2, because each of these elements have to be 0 for this to be a null vector. So they have asked me what is a plus b minus c. So a plus b would be 6, minus c would be 1, that is 5. So 5 would be your answer for the question. Now there are few properties of del operator. Again, if I am doing the dot product, then I can distribute these point functions. If I have a scalar point function that is multiplied, what I can do, I can use the chain rule. Okay, use the chain rule here. If I'm doing the curl, then also I can use the chain rule. Chain rule is correct. Like, how can you remember? Always you remember that if I'm applying the divergence operator, then at the end I will get a scalar point function. If I am applying a curl operator, then at the end I will get a vector point function. So if we see, first I will take the, so there can be two things here, right? I am applying the chain rule. I will apply some operation of del with A. I will apply some operation of del with F. That is for sure. But what kind of operation? Because I will get a scalar point function at the end, so I have to take the divergence of A. Then only I will get a scalar function. That's why you see there is a dot. That is divergence of A multiplied by F. F is treated as a constant. Next time again here, I cannot simply take the divergence with F because F is a scalar point function. Divergence is applied with a vector point function. So I will take the gradient of F, and I know at the end the resultant should be a scalar. So I will take the divergence with A. That's how you remember this formula. Similarly here, I am taking the curl of FA. So here this will be curl into first I will take the curl of A because I can take the curl with the vector point function. Then I will multiply a scalar at the end because this already is a vector. I don't need to do dot product. This already is a vector. Right? I'll just simply multiply by the scalar. Here again I will take the gradient because I cannot apply curl with a scalar point function. Then I will keep the A vector at the outside. Okay. So this will be A curl gradient of F. That's it. So this will be your answer basically. Now, yeah, there are a few properties here. If I am, let's say, taking the curl of gradient of F, so I can break it down, right? This can be broken down. Sometimes we tend to forget it, but it's very easy. So how can I remember? So I am taking the curl with gradient of F. That will be a null vector. If I am taking the divergence with gradient, sorry, with curl, this also will be a zero vector. These are called as null identities. So you can always prove it. You can always prove it here, right? How can I prove it? So del cross del of F, del cross del of F. So this can be written as, I'm taking the curl, so this will be curl of F, because at the end I will get a vector point function. So this will be only gradient minus this will be applied here inside. So I will take the, because I have to take the gradient of del only, right? So I have to multiply these two functions and F will be outside. F will be outside and I have to multiply these two functions. This will be del square basically, correct? So here I have del square F at the outside, correct? Del square F at the outside, and then cross, sorry, del cross A vector, right? Hold on a second. First I will apply this cross product, then I will keep it as constant. Sorry, this will be, okay, I cannot take the cross product del F. So sorry, I cannot, what am I doing? I cannot do this cross product, right? There's no. So first I will apply, if I'm doing cross with del cross F, how will I solve this? If I'm doing cross with, okay, you cannot simply solve it. You cannot simply solve it because this itself is a scalar point function, sorry, vector point function, some A vector. Okay, this itself is a vector point function. You cannot break it down because here I had two functions, two different functions, but you cannot just okay, you can actually, but here both of them are scalars, right? Yeah, one was vector here, but here both of them are scalars. So how will you remember? So you remember it like this: CG and DC would be Deccan charges, IPL team, right? Deccan charges, this will be always 0, and your CG also, CG, center of gravity, that also always will be 0. But if you do this, right, C, that is curl and curl, again, that will not be 0. This will not be 0. This will be some non-zero value. So this is again this property. First, I will take the curl with the take the this is called as the vector triple product. First, I will take the divergence with this function, and I will keep my delta outside. Then I will uh, take the divergence with delta, and divergence of delta is nothing but delta square minus f square minus f. F will be at the outside as a constant. Okay, this property is vector triple product. This is similar to the vector algebra that we learned previously at the starting of this lecture. Similar, right? First I will take the outside function, then the inside function. That's it. So these things you have to put in short notes and remember. Otherwise you will not be able to remember. Me saying this will not be enough. You have to put in this. I will provide the short notes and you have to remember all these things. Now there is one more, this table, right? Unfortunately you have to remember the table, because in Cartesian coordinate system it is very simple to find out the gradient, divergence and curl. But in cylindrical coordinate system and in spherical coordinate system it is quite difficult. Okay, so this formula are there. Pause the video and go through these formulas. For cylindrical and Cartesian, sorry, for cylindrical and spherical, you have to unfortunately remember these things. Okay, there is no other option than to remember. Okay, that is the only way. So now we will move on to the integral vector calculus. So we will do integration of vector variables. So there can be single line integration, double line integration and volume integration. So up until now, previously, right, we actually in today's lecture itself we did scalar integrations, scalar volume integrations with real variables. Now we will do the same kind of integrations with vector variables. So there are a few properties which we will use. Okay, so like there are few terminologies, like a function whose output value is same at every input value, that is said to be a constant function. Basically it should not be a function of time. F is x plus xi cap plus yj cap plus xyz k cap. It is not a function of time, so the output will be always same at every input value. Okay, line integration, we will solve few line integrations. I will show you. Where is, yeah, here is one line integration, right? So let's say I have to solve, just give me 1 second. I have to solve this line integration. So I will break down my, so your dr is a vector point function. Now dr would be dx I cap plus dy j cap. So your f would be 3xy I cap plus y square j cap in dot, because there is a dot product here, into dx I cap plus dy j cap. This integration. So points are given, right? So what is the change in x? Change in x is like x is going from 0 to 1 and your y is going from 1 to 2. Now one thing is there, they have also given you the curve along which you have to perform the integration. So first one is y equals to 2x square. So you cannot just simply choose any random curve. First one is y equal to 2x. So you'll write your y equals to 2x square and you will put the points. So if I put x equal to 0, do I get y equal to 0? Yes. If I put x equal to 1, do I get y equal to 2? Yes. Now what is your dy? Dy would be 4x dx. So you will perform this substitution in your integration. So this integration can be converted into 3xy dx plus y square dy. So I can replace my y with 2x square, and I can replace my dy with 4x dx. So if I replace my y with 2x square, this will be 6x cube dx, plus I can replace my y with 2x square, this would be 4x raised to power 4 and dy will be replaced with 4x dx. So this would be x raised to power 4 by 4, that is, now I can put the value of limits of x, right, that is 0 to 1. So this would be x raised to the power 4 by 4 into 6 plus 4 by no, not 4, sorry, 16 by 6 x raised to the power of 6. X is going from 0 to 1. This would be 6 by 4 plus 16 by 6. So if I solve this integration, so I think I have already solved it. 6 by 4, yeah, 6 by 4 plus 16 by 6, that would be 8 by 3 plus 3 by 2 plus 8 by 3. Nine plus 16, that is 25 by 6. So 25 by 6 would be your answer. So there is another way to solve this also as well. Like here in the dx part, you will replace your y. In the dy part, you will keep your y. That's it. You will keep your y. So if I keep my y in the dy part, I can simply integrate the y and I can put the limits of y, and in the x as well I can put the limits. You will get the same answer. So there are many ways to solve single line integration. So this was for an open curve. So you can also solve for curve along y equal to 2x. You will see the answer you are getting is different. So if I change the curve along which I am calculating my line integration, then the resultant integration will be different. But there is a catch. If your field is conservative, then this integration would be same actually. So yeah, so for a, if this integration, right, if I change the curve along which I am calculating my integration, if I change my curve along which I am calculating my integration, and if the integration comes out to be different, then we say that the field, vector field, is non-conservative. If it comes out to be same, then we say it is conservative. Okay, then we say it is conservative. So I can share you, yeah, we can directly go into few conditions. So what are the other ways to check conservative? So if one more thing is there, that if I have a closed line integration, correct, closed line, now if it was an open curve integration, so let's say I'm integrating a function along the curve y equal to x and y equal to x square by 2, and both this integration, right, if I'm going from point p1 to point p2, both this if I integrate along both the curves c1 and c2, both yield me the same answer, then we say the vector field is conservative. Now there is another way to understand whether a vector field is conservative or not. So let's say I have a closed curve like this. If I have a closed curve like this, right, so if I integrate along this closed curve a vector point function, and if the integration comes out to be 0, then we say that that field is conservative. Because let's say I have to integrate along a closed curve, so I could have also indicated like this. So if the vector field is conservative, right, so whatever I went from this point 1 to point 2, whatever was the value, this other value will be negative if the vector field is said to be conservative. Okay, so a vector field is conservative if its closed line integration along any given curve is 0. Along any given curve, the curve C can be anything, it can be a circle, it can be this, any curve, closed line integration is 0, then we say the vector field function is conservative in nature. Electrostatic fields are conservative in nature. Okay, because if you find out the line integration along any path, you will see the integration will come out to be 0 always. Magnetostatic fields are non-conservative in nature. Okay, that is a property basically. How can I verify? So basically, if you find out the curl of any vector field, and if the curl comes out to be 0, then we say that the vector field will be conservative in nature. Vector field will be conservative in nature. Now, yeah, if f is irrotational, that is if this del cross f is 0, that is f is irrotational, then 100% I can say that your vector field f will be conservative in the vector in the given curve if the function is differentiable and continuous in the given region. Whatever region they have given you, the function must be differentiable and continuous. If it is not differentiable and continuous, then you cannot actually conclusively say whether the vector field will be conservative or not. So what is the conclusion? Conclusion is this closed line integration is 0. If this closed line integration is 0, then definitely your curl of my vector field function will be if this is 0, the curl of f can be 0 or cannot be 0. I cannot surely say. No, actually the thing is, if this curl of f is 0, if the curl of f is 0, right, then for surely say that the vector field will be conservative, because there is a Stokes law, because we can convert our single line integration into a open surface integration like this using the Stokes theorem. Okay, and there we say that if this value is 0, then this value also will be 0. That means either your del cross f is 0 or your or your dot product, this is 0. Basically the angle between the surface vector and the curl is 0. That is also another possibility, but mostly we say that del cross f is 0. So if del cross f is 0, just put this in your short notes that if the curl of a vector field is 0, then 100% we say that the field will be conservative. Of course, it has to be continuous and differentiable within the given region. If f is rotational, that is if curl is not 0, then also the closed line integration may or may not be 0, that is it may or may not be conservative. I cannot conclusively say, I have to calculate this and then I can comment. But if the curl is not 0, I cannot say that it will not be conservative. No, I cannot say conclusively. But if the curl is 0, 100% I can say that the vector field will be conservative. Okay, so that is one thing. So if the circulation of f is 0, then that's why the vice versa is not true. If your circulation, basically if your closed line integration is equal to 0, then I cannot conclusively say whether my curl of my vector point function will be 0 or not. I cannot say conclusively. But if it is the other way around, if the curl of my vector field is 0, then I can safely say that my vector field will be conservative 100%, 101%, because we can use the Stokes theorem. So what thing you have to keep in mind? If the curl of a vector field function is 0, then you can say the vector field is 100% conservative. If the closed line integration of a vector field is 0, I cannot comment whether the vector field will be irrotational or rotational. I cannot comment. I have to find out the curl. So that's why these two arrows are there to represent that if curl is 0, then I can say definitely the closed line integration will be 0. If curl is not, if the integration, closed line integration is 0, then I cannot say that with curl also will be 0. I cannot say. Okay. So yeah, that is the important thing that you have to take from here. That is the conclusion. So you can evaluate, let's say I want to they are telling me that calculate the integration along the given curve of this vector point function. If you calculate the integration here, you will see that you are getting uh, what values are you are getting different values. Okay, so whenever you will be given a vector point function, right, first of all, what will be your task? If they are asking you to find out the and they have not given you the curve, if they're not giving you the curve, first you check the curl of this vector point function. If I check the curl for this vector point function, this will be x plus this will be I cap j cap k cap, this will be del x del y del z. 0. This will be 0, this will be y, this will be 1, j cap minus is also there, plus this will be, hold on a second, no, this will be with k cap, right? And with j cap this will be 0, this will also be 0. Yeah, so basically you see that your curl is not 0. If your curl is non-zero at the given point, right, then definitely I can say that there is insufficient data, because they have not given you the curve about which you have to find out the integration. So you can choose two kinds of curve. You can choose y equals to x, or you can choose y equals to x square by 2. And in both the cases, if you find out this single line integration, you will see that you are getting different values. I think that is shown in this page. Yeah, if I choose my curve to be y equals to x, then the answer that we'll get is 4 units. If I choose my curve that is y equal to x square by 2, the answer I think that we will get is some units, right, which I don't. So this, if I solve this particular thing, you will get it equals to 2 plus 2 cube by 2, that is 4, that is 6. So answer that you get is 6 units, which is different, right? So if I choose different curves, then the answer for this question will be different. So because they have not given me the curve, so this is insufficient data. So one day they will frame a MCQ, okay, and they'll ask this exact question. In one of the option, the answer will be 4 units. In the other option, the answer will be 6 units. In the third option, the answer will be none of the above. In the fourth option, it will be insufficient data. So in that case, your answer will be insufficient data, because no path is given, because your vector point function is not irrotational. If it is not irrotational, then your integration, your single line integration will not be path independent. If it was if it was irrotational, then your single line integration would have been path independent. You could have chosen any path, and for any path the value would be coming out to be same. So just be careful. Okay, so yeah, that is the thing about uh, closed line, open and closed line integration. So first of all, simple thing what you have to keep in mind, whenever you will be given a single line integration, you will always calculate of a vector point function, you will always calculate the curl of that function. If the curl comes out to be 0, then you choose null vector. Basically you choose any path, choose straight line, because straight line are the easiest ones to choose. So you will choose a path that is straight line. You will choose a path that is straight line, and then you will solve. Of course you will put the values of point p1 and p2 in the function and check whether the curve is satisfying those points. That is also one more thing. And if your curl is not coming out to be 0 null vector, then you have to integrate along the given path. Okay, that is one thing. You have to integrate along the given path. That's it basically. So yeah, that was the conclusion of you cannot use straight line. You have to, whatever path they will give you, like y equal to x square, and you have to solve according to that. So now we will come to surface integration. So surface integration, there can be two kinds of surface integration, just like a path integration, right? There can be two kinds of path integration. One is the open path, where I am going from point A to point B. It is not coming back to the same point. If it, let's say, was coming back, I was going from a path, then I coming back to the same point. This is called as a closed line integration. And if I'm going from point A to point B, I'm not coming back to my same point. This is called as a open line integration. Similarly, in surface integration, there can be a open surface integration, closed surface integration. So open surface would be this, right? I'm covering a 2D structure. Okay, these are called as open surface integration, which does not enclose any volume. So a closed line integration, you see, encloses a surface. Open line integration does not enclose any surface. Similarly, a open surface integration will not enclose any volume. A closed surface integration will enclose a volume basically. So I will have all the surfaces which are closed, so it will enclose a volume like a hollow cube, hollow cylinder. Okay, so yeah, those are the few things that you have to keep in mind. Now, how can you solve surface integration? Surface integration would be, the format for surface integration would be this. F, obviously the vector point function will be given, dot n cap ds. Now ds is the differential surface length, which would be differential area. In Cartesian it will be dx dy. In any other coordinate it will be magnitude of j into whatever is the coordinate, let's say d rho d phi or whatever is the coordinate, right? Now how can you find out this n cap vector? What will be this n cap vector? So to calculate n cap vector, you have to apply this operation. Okay, so direction of the open, if they have given you the surface, right, they will give you some surface vector. So do I have any? Yeah, so s is a surface bounded by planes x equal to 0, x equal to 1, y equal to 0, y equal to 1, z equal to 0, z equals to 1. So how many surface I have? X equal to 0 itself is a surface. X equal to 0, right? X equal to 0 is x equal to 0 is here. So when x is equal to 0, y and z can take any value. So basically it is telling me that it is this whole plane. If it is this whole plane, then in this surface, what is the what do you call? In this whole plane, yeah. What is the direction of the surface? The direction of the surface would always be, if it's a closed surface, right, it will be always outward from the closed surface. So if I am on the yz plane, what is the direction of the vector that is normal to my surface, given surface, that is outside? What is the direction? It is minus x cap. So you see here, right, this was the surface 1. If you see the surface 2, you see the direction is minus I cap or minus x cap. Okay, so how can you solve it basically? So this is the surface, right, x equal to 0. X equal to 0 is the surface. So I will find out the gradient. So what will be phi? Phi will be equals to x. So what will be grad of phi? Grad of phi would be simply equals to I cap. So what will be the direction vector? It can be plus minus because it is a normal vector to the surface. So this is also a normal, this is also a normal. I will choose this normal because it is pointing outwards of the surface. So I will choose minus I. You will choose minus I. Similarly here, I will choose, basically I will choose the direction along which I am pointing outwards. So in this direction my x is reducing. So my phi would be, actually I should have chosen my phi to be minus of x. I should have taken this x on the other side, that's it. Okay. Similarly, you can choose all these surface. Now, as soon as you have chosen this surface, right? For surface S1, what is your ds vector? It is plus I, and ds is dy dz. Why dy dz? Because if I say, see, right, along ds, along dx, am I changing? No, dx is not changing, right? Along x, because x equal to 1 is fixed. So dx is 0. What is changing? Dy and dz. So my ds differential area would be dy into dz. That's it. Okay. And your vector would be, direction of the surface vector would be I cap, and your function, vector point function is this. So I will only consider the I cap component because there is a dot. So I will only consider the I cap component. So this will be y square dy dz. Now you can simply solve. The limits are given, right? Because it's a cube of length 1. So y will be going from 0 to 1, z will be going from 0 to 1. So you can solve for this particular surface. For S1 you can solve, for S2 you can solve. Like this you can keep on solving. Okay. You can obviously take strips. Obviously this is broken down into a double integration, and you know how to solve a double integration. Correct. So that's how you solve basically. So I'm not going through too much, and mostly these things will not be used. Okay, I'm skipping these things. Mostly theorems will be used. Okay. These things will, like, they can ask you these things, but mostly I'm expecting that they will not ask you these things. They will mostly cover from theorems. Okay. So for R-PYQ, you can go through this basic part, but I am concerned mostly about the theorem. So this is the first theorem for for solving closed line integration. So for solving closed line integration, I can use Green's theorem. Okay. Or I can use Stokes theorem. Basically, Green's theorem is the special case of Stokes theorem. Okay. So what does Green's theorem tell me? So if I have a closed line integration m dx and dy, where m and n both are functions of x and y. Similarly, like if, like, basically I have this closed line integration of f dot dr, basically something like this, correct, in 2 dimension, in 2D. Okay. Green's theorem is the special case of Stokes theorem in 2 dimension. That's it. So dr would be basically x plus x I cap plus yj cap, and f would be function of x and y. Then I can break my this closed line integration into this value. So I will differentiate my n part, that is with respect to dy with respect to x, and then I will subtract my the coefficient, that is with respect to x, m with respect to x, sorry, with respect to y, because it is already with dx. So I will differentiate this with respect to y. This is already with dy, so I will differentiate this function with respect to x. That's it. Okay. Now, yeah. Then I will multiply by the surface vector ds, that is dx dy, and then I will integrate over the surface. So if I have a closed line integration, then of course it will cover a surface. So I'll find out this direction of the surface vector, right? Anyways, this direction is not required. Direction also will not be required. Only this part is required. Okay. So maybe we'll solve a question from that you will understand. Yeah, here we have this vector point function, and I have to, like, this is in 2D, and they're just asking me to find out the closed line integration about a curve. So I don't like, I will first of all draw the curve, that is x square plus y square equal to 4. So this is the equation of a simple circle, right? And this radius is 2, correct? And direction is given as clockwise. So there is a caveat here. So your direction is like, because what we do, we write x then y, right? So we write x then y, that is our convention, right? X then y then z, correct? So first del x should come, then del y will come. If your direction given is in the anti-clockwise direction, we go from x to y, right? That is the reference, x to y, that is the positive angle. So if the direction of the curve, given curve, is given in the anti-clockwise direction, then this will be the result. if let's say the curve direction I am changing it to clockwise, not anti-clockwise, it is clockwise, then the answer will be just negative. So first del y will come, then del x will come, because if I am going in the clockwise, then I am going from y to x. That's why first del y will come, then del x. So that's how you remember this, right? That's how you remember this particular formula. This is very important. If the direction of curve is given in the anti-clockwise meaning I'm going from x to y, that is everything reference. So I will start with del x, then I will write del y. If the given direction of the curve, orientation of the curve is given in the clockwise direction, then I will start with del y, then del x. So we can see here, as the direction is given clockwise, so I am going from y to x. So what will be the formula? Formula would be del, let me name this function as m n. So if I solve my closed line integration, four y into dx 2x minus y 3y into dy. Now let me name this function as m and n. So if I am going in the clockwise, that means I am going from y to x. So this will come, n will come with dx, because here I have already dy, right? So this will come with dx, this will come with dy. So first of all, I will write the dy part, because I am going from y to x, because it is in the clockwise direction. Minus, I will write the other term, obviously del n del x, and then I will find out this surface integration ds. So what is del m del y? Del m del y is basically 4. What is del n del x? It is 2. So 4 minus 2 dx. So it is basically 2 of ds. So the surface integration of the ds vector, that is nothing but the area of the surface. ds is dx dy. So 1 dx dy is nothing but the area of the surface, that is simple equals to pi r square, that is 4 pi. So this will be 8 pi. Okay, so just be careful regarding the negative sign, very careful. So yeah, the same thing I have written over here. Okay, and all these conditions must be satisfied if you're applying Green's theorem. Basically your function must be continuous. Okay, all these things must be satisfied. There are few edge cases that I will discuss, don't worry regarding those, but mostly these conditions need to be satisfied, and mostly I'm expecting they will ask you a question from this basic thing. Okay, anti-clockwise clockwise, that's it. Okay, I hope that part is clear by you. So yeah, another function is given, let's say in this time not in xy but in xz. If it is given in xz, then how will you solve? So again you'll write this thing down. Okay, remember Green's theorem is only applicable in 2D. This is also 2D only, right? Only 2 variables are present, not 3. So Green's theorem is applicable, but how will you apply? So you'll write x, y, z and then x. So if I go in the reference direction, right, in the anti-clockwise direction, then after z, x will come. After z, x will come. So how will I write my formula? So let's say, yeah, if I do this, right, so what will be f dot dl? So dl vector is nothing but the r vector basically. It is basically I cap dx I cap plus dy j cap plus dz k cap. So first of all, if I take the dot product here, closed line integration, this will be 3x plus 4z dx plus 2x minus 3z dz, because k cap dot k cap will be 1. So now the interesting fact here is that I cannot So let me name this as M and N. So, and the curve given is a circle in the anti-clockwise direction about the xz plane. Remember, the curve also should be given in the same plane. Otherwise, the other plane will just be a constant. Okay. So, xz plane they have given you about the anti-clockwise direction. So, anti-clockwise direction. So, let's say my x is here, right? Then my z is here. How will I solve this? So, I will differentiate del m by del z because del x is already here. What is the other available? Z. So, I will differentiate with z. This I will differentiate del n with del x because del z is already here. I cannot differentiate with respect to z. I will differentiate with respect to x. Now, which one shall I write first? Here we will follow this rule, right? So, if I am following anti-clockwise, then I always write, in the previous case I have written dx first then dy. So, here because I am following anti-clockwise, so I will write del z first then del x. So, del z is with this function. So, I will write del m del z minus del n del x into dz dx double integration of the surface. So, this will be, what is del m del z? It is simply equals to 4 minus del n del x is 2 into double integration dz dx, that would be 2 dz dx. So, 2 into pi r square is 4 again, so it will be 8 pi. Answer. So, here, right, whatever formula they have written, you don't have to remember this, you remember it according to this thing, remember it according to this. So, trust me, in any other institution no one will tell you all these things, they will just tell you to mug up the formula, they will just tell you to mug up the formula. But here I have conceptually told you how can you remember it. That is the most important part, because in examination hall you will forget it. So, how to remember it, right? With this trick that I have told you. So, if you are enjoying it, please put it down in the comments below. If you are enjoying this thing, please put it down in the comments below. Trust me, no, in any other institute they will not tell you this part. Okay, but I am teaching you the intuition. How can you remember the formula? Here we have this particular closed line integration over the path shown in the figure. So, this is also a closed path. Okay, so we have to perform this. So, if you try to apply the Green's theorem here, your Green's theorem will simply fail. This will be wrong. Why? Because first of all, this is a polynomial function, and whatever points this surface includes, we have to check whether my function is continuous and differentiable. Otherwise, Green's theorem will not be applicable. If your function is not continuous and differentiable at the given points inside the closed curve, then we say Green's theorem is not applicable. At 0, 0, right? Green's theorem will not be applicable. We have to check whether the function is continuous or not. So, this is a very long thing that you have to check for continuity. So, if your function is not continuous, okay, like you can see how am I checking continuous. I will not explain that continuity in two variables for now. If the function is not continuous, then we have to simply solve with basics. So, what you will do, you will break this closed curve into 4 parts: curve 1, curve 2, curve 3, curve 4, and then solve. So, in this particular curve, right, only my x is changing, my y is constant. So, dy would be 0. So, only I have to integrate this part where my x is changing, y is constant, y is equals to -1. In this path, my y is changing, my x is constant. Similarly, like this. So, you have to break your integration down into 4 parts, and ultimately you have to arrive at your result. Okay. So, just be careful while applying Green's theorem. There can be bit of problems. In crash course, in other institutes, they will not tell you the problems. They will just tell you the formula of Green's theorem. They will solve few questions, and that's it. They will not able tell you how to remember the formula, how to solve the questions, and where can you go wrong, and where can in the exam they can give you a question that will be a trick question. This is a trick question. Okay. Now, the other thing is regarding this region. If I have a doubly connected region or a singly connected region, so let's say the region that is given, this is also a closed curve, but they have given me 2 curves. One is this x square plus y square greater than 1, another one is x like this square. This also forms a closed surface. But how to solve these kind of regions? So for solving this kind of region, now x equal to 0, y equal to 0 is not included. So you don't have to simply solve it separately. You can use your Green's theorem, because whenever your function is rational, you have to just check when does my denominator goes to 0. Whenever your denominator goes to 0, that point of time your function will not, like the limit will not exist, your function will not be continuous or differentiable. Other than that, this function will always be continuous and differentiable. Any polynomial is always continuous and differentiable. Okay, so 0 comma 0 point has been excluded, so I can use my Green's theorem, that is okay. But what will be the orientation of my Green's theorem? What will be the orientation of my Green's theorem? So this is a doubly connected region. So here if I see that on the outside I am covering in the anti-clockwise direction, on the inside I am covering in the clockwise direction. So this kind of region is called as doubly connected region, and overall it is called to, the direction of orientation is called to be anti-clockwise. So what we will do is we will break our curves into a single curve, because of course to apply the Green's theorem we need only a single curve, right? Single closed line integration. So what I can do, I can break this curve into two curves that will be closed, because currently I have this curve and this curve. Although the surface that it is covering is closed, but I cannot conclusively say I can apply the Green's theorem with this curve, because if I choose this curve then it includes the 0 comma 0 point, correct? So what we do a bit of trickery. We do a bit of trickery. So we break this down and break this down into two curves. So this, let's say this curve is curve C1 and this curve is the curve C2. So these are very close to each other, okay? These are just like almost connected but very close. So if I see the first curve, that is also anticlockwise, the second curve is also anticlockwise, then what we do is we solve along the curve 1 and we solve along the curve 2. So if I solve along the curve 1 and curve 2, right, so this inside thing is same. So overall if I add these, this will be the whole surface. So that's why, like, that is the proof. How can I convert this into a Green's theorem? That is the proof basically. But for you just have to remember that, like, one more thing, how is this anticlockwise? This is how, because this is also anticlockwise, this also is anticlockwise. That's why overall your orientation comes out to be anticlockwise. That's why I have told you the orientation that we see is with respect to the outside curve. That is the proof. Okay, that's it. What you have to remember, whenever a curve like this will be given, you will apply the Green's theorem, because your function will be continuous and differentiable along the given points, and simply you check the orientation of the outermost curve. If the orientation is anticlockwise, then you will solve according to anticlockwise. If the orientation is clockwise, then you will solve according to clockwise. That's it. Like, there is an example, this one is the example. So here we have to find out, although this function is totally like differentiable at 0 comma 0 as well, but we have to find out the closed line integration along the given circles x square plus y square equal to 1 and x square plus y square equal to 4. So again I will sense my direction according to the outermost curve, that is anticlockwise, so I will solve according to anticlockwise. So if I solve this, right, this will be okay, let me solve this. This will be 2x plus y cube dx plus y plus 2x cube dy. Now again this will be my, but this will be, let's say this is m, this is n, so there will be two terms. One will be del m del y, and this will be del n del x. So here if I solve this, so again, okay, hold on a second, this got broken, just 1 second. So here if I see that again the outermost circle is the anticlockwise, so I'll solve in the anticlockwise. If I solve in the anticlockwise, that is the reference, so I'll go from x to y. So first del x will be there, then del y will be there. So del x will be there, that will be del n minus del x. So del n minus del x would be 4x square minus, so not 4, sorry, 6x square minus del m del y. Del m del y would be 3y square and dx dy, and the surface is given. Okay, so now you cannot simply solve it. The surface that is given to you, right, it's not that simple. Okay, so because you have to take a strip, what kind of strip shall I choose? So I can choose a strip like this. If I choose a strip like this, that will be okay. This will be a bit difficult. So what you can do is you can convert, like this is a bit difficult, you can convert your uh, you can convert your you can convert from Cartesian to polar. So you can assume, you can take because here both x and y are varying, you can assume that your x equal to rho cos phi and your y equals to rho sin phi. Again your dx dy would be rho d rho d phi. So this whole integration will be converted into, what is the x square? X square would be rho square cos square phi, and 6 will be there out the outside, minus 3 into rho square sin square phi rho d phi. Now your rho d phi is going from 0 to 2 pi, and your rho is varying from rho equals to 1 to rho equals to 2. Rho is varying from rho equals to 1 to rho equals to 2. So if we solve this integration, right, this will be sin square. So this can be, I can convert this thing into cos square theta, correct? I think I have done the same thing. Hold on a second. Yeah, 3 rho square cos square theta minus sin square theta. So what have I done here? Okay, I have first of all integrated with respect to rho. No, I have not. No, I've just multiplied the rho inside. If I multiply the rho inside, how is this? Okay, I have converted. So basically I have done this, cos square phi minus sin square phi is cos of 2 phi. So I have converted that particular thing here, right, and I have kept this one uh, as it is, like basically, right. So this will be what I can take 3 rho square common. So this will be 3 cos square phi minus sin square phi, and additional 3 rho square will be there, plus 3 rho square cos square phi. So this part will be cos 2 phi, right? This part will be cos 2 phi. That is what I have written over here into 3 rho, and obviously rho was there at the outside. That's why it was 3 rho cube plus 3 rho cube into cos square phi. Okay. If I integrate this from 0 to 2 pi, right, this will be basically 0. Integration of cos 2 phi from 0 to 2 pi would be simply 0. Integration of 3 rho cube cos square phi, this will be yeah, this will be half, I believe. The integration of cos square phi would be half, if I remember it correctly, from 0 to pi by 2. Oh, sorry, from 0 to 2 pi we can solve it basically, right. Cos square phi will be something like this. This will be the area basically, correct. So from 0 to pi by 2, actually if we solve from 0 to pi by 2, this area comes out to be half. You can solve it, this area will be half from 0 to pi by 2. Then I am integrating over a whole period 2 pi, right, over a whole period 2 pi. So I have to multiply by 4 because I have 4 segments of pi by 2. Pi by 2 here, pi by 2 here, pi by 2 here, pi by 2. This area would be half, this area would be half, this area would be half, this area would be half. You can prove it as well. I can prove it to you as well, this value. Okay, so I can replace, so I have to integrate cos of pi by 2 cos square phi. So cos square phi, right, I can replace my cos square phi in terms of sine, sorry, cos 2 phi. So we know cos square phi minus sin square phi equals to cos of 2 phi. So I can replace, this will be cos square phi would be equals to 1 plus cos 2 phi upon 2, correct. Okay, I think there will be a pi as well. Oh, sorry, this will not be half, sorry, this will be pi by 2. Yeah, I was mistaken. This will be pi by 2, not half, sorry, pi by 2. Yeah, pi by 2. So if I integrate this function, right, from 0 to pi by 2, correct, this part will be 0 anyways. if I'm not mistaken. This part will be pi by 4. Okay. Huh. Just give me 1 second. Cos square phi, this will be half or what? Uh, Hold on a second. So this will be, if I integrate this, right? Let's say I'm integrating from 0 to 2 pi. Integrating from 0 to 2 pi, this will be pi. Okay, I'm sorry. That's why you don't remember. You should not remember the things. This integration, right, comes out to be pi. That's it. Okay. This 0 to 2 pi, if I integrate this thing, this will come out to be pi. So this whole answer will be, instead of doing all this funny business, right? I could have directly done it actually. Instead of doing that, this overall thing would be pi actually. Okay, no need to do all that funny business, multiply by 4. This will be pi, and then I can integrate with respect to rho. That will be 3 by 4 rho 4, and rho is varying from 2 to 1. So this will be 2 raised to power 4 minus 1 into 3 by 4. Yeah, this will be 3 into 15 pi by 4. Yeah, this will be the answer. Okay, so there are a few things you can sort out, but like the basic idea, I hope I have explained. Like, of course, I'll not be able to solve every single question because we have to go through other topics as well, right? So now we will come to Stokes theorem. So Stokes theorem is applicable only if the function is differentiable and continuous in the given surface S. So Stokes theorem converts your closed single line integration into a open surface integration. Stokes theorem states that integration of f dot dl will be equals to double integration of del cross f dot ds. So very simple. Let's say I have this function, okay, and this is a 3D function. It is not a 2-dimensional function anymore. This is a 3-dimensional function. So if it's a 3-dimensional function, then we cannot use Green's theorem. We have to use Stokes. Basically, Green's theorem is the Green's theorem is the special case of Stokes theorem. Okay, so if it's a 3-dimensional function, and remember, if they're telling you this formula will be valid if and only if it is taken in positive sense. Okay, anti-clockwise, positive sense, anti-clockwise. If it is taken in clockwise, then again you have to apply a negative sign outside. That is the only thing that you have to keep in mind. Okay, so we can use Stokes theorem. So we can find out the del cross f, right? Del cross f is this value. Now I got my del cross f. What is my ds vector? So the surface that is given to me, curve that is given to me, that is x square plus y square equal to 4 in positive sense. If it is in the positive sense, if I curl my fingers along the given curve, so I see that the direction that I'm getting of this area vector is plus k cap. So that will be the direction of my ds vector. Ds vector direction would be plus k cap, and what will be the other parts? What is the differential area? It will be dx into dy because it is lying in the xy plane. So it will be dx into dy. So here I have seen dx dy k cap. So I will take the dot product with k component. So this component is gone, only this part is left. So integration of 1 dx dy, it is nothing but the area of the given curve, that is simply pi r square, that is 4 pi. So 4 pi would be your answer for this question. So you can solve using basic as well, right? What you could have done, again, because the curve that is given, it's like a 2D curve, you can convert this whole thing into its polar coordinate. Like your x will be converted into rho cos phi, that is 2 cos phi, y will be converted into 2 sin phi, and your z, right? Because we're lying in, because the curve that is given, we're lying in the xy plane, that means z is 0 in the xy plane. So you'll put z equal to 0, dz is 0 simply. So you can solve using basics as well. You can see the solution, you'll arrive at the same answer. Okay, there will not be any changes in the answer. Okay, so like here I have proven basically Green's theorem is the special case of Stokes theorem. We will not go into that for now. So these are the few things that you have to keep in mind, right? That if we know that the closed line integration of the position vector with respect to dr will be 0. How? So what is the curl of position vector? It is 0, right? And we know using Stokes theorem we can convert this integration into a surface integration, del cross f. And if this f is r vector and we know this curl is 0, if this curl is 0, this integration will be 0. So that's why this part will be always null vector, that is 0 vector. Okay, this integration will be 0. Again, if I am calculating the closed line integration of gradient of a scalar point function phi, that also will be 0. Why? Because we know that the curl of gradient CG center of gravity is 0. So if the curl of this particular function is 0, that means again I will come back, I will use my Stokes theorem. So this can be asked in MCQ or MSQ. Is this 0? Is this 0? This can be asked in MSQ. Just try to think, how can I prove it? How can I prove it? CG, this thing, right? Remember these things. That's how you can prove it. Okay, this all these things can be asked. So basically, if your function f is irrotational in the given region, then definitely the closed line integration will be 0. Okay, so that is the conclusion. That is what I have explained over here. So let's go through one basic question, that which of the following statements is correct. If vector f is conservative in nature, then is f irrotational? I cannot say, I cannot comment. That is what I have told, right? I don't know whether if vector f is conservative, I cannot comment whether my function, vector point function, will be irrotational or not. If the vector f is irrotational in nature, if the vector f is irrotational in nature, then will f be conservative? 100% yes. If the curl of a function is not 0, will then f is not conservative? I cannot comment. If the curl is not 0, right, if it is not irrotational, then also it can be conservative. I cannot comment. If the curl is 0, then f is a conservative field. Yes, these two things are same only, right? If f is irrotational, that means its curl is 0, right? So yeah, so if f is irrotational or if the curl of f is 0, then for surely say it will be conservative. But if f is conservative, I cannot say whether f will be irrotational or not. Trust me, one day they will ask you MSQ from this part, so be prepared for that. Okay, the key point is, if f is irrotational, what are the conclusions? F will be conservative, for sure. F will be conservative. The open line integration will be independent of path. I can choose any path. Mostly we choose straight line. If f is irrotational, the closed line integration will be 0. Okay, these are the conclusions basically. So now there is one more thing, that is inverse Stokes theorem. Sometimes what happens is they will give you this curl of f, right, and they will ask you to calculate this integration. So you can use the inverse Stokes theorem, because we know that closed line integration of f dot dl is equals to open surface integration of del cross f dot ds. Now sometimes what happens is finding out this del cross f is sometimes tedious, or this surface vector ds vector here, right, the surface that they have given me is this surface, right, that is very tedious. This surface is very tedious. So sometimes solving it directly would be very difficult. I can use inverse Stokes theorem. So I can convert this into a closed line integration. That's it. I can convert this into a closed line integration. So what we can do, instead of doing this, right, I can convert this into a closed line integration. So if I take the projection, right, I will see that this projection is nothing but a closed line about the xy plane with circle of radius equals to 1, z is equal to 0 basically, right. So we can convert this to a closed line integration. So this will be converted into closed line integration. So this will be f dot dl. dl is dx I cap dy j cap plus dz k cap. So f is this function, and if I do dot with dl, that is dot I cap dx, right. So this will be z dx plus x dy plus y dz. Now out of this, right, I know my, like, if I am calculating the projection about the xy plane, that means z is 0. So if z is 0, this will be 0, and dz also will be 0. There is no change in z, so only x dy is left. That's why only x dy is there, right. So if I find out this integration, simple, now we can simply find out the closed line integration about this curve of x dy. That is very easy, right. It is a circle, so you'll replace your x with rho cos phi, circle of radius 1, so you'll replace your x with cos phi and your dy with cos phi d phi. So you can solve this integration, it will come out to be pi. That's it. Okay, so yeah, that's it basically. So yeah, or you can also solve this, right, using your Gauss divergence, sorry, Gauss theorem. Yeah, Gauss divergence theorem basically, right. Either way you solve, like this is a single closed line integration. Now you can solve it using Gauss divergence, or simple basics also you can solve. Okay, So that is the Gauss divergence theorem. I hope that part is sorry. This was the Green's, sorry, this was the Green's theorem, not Gauss divergence. Green's theorem. Now there is one last theorem that is the also the easiest one, that is Gauss divergence theorem, and this is the most easiest one. So if I have a closed surface integration, then I can convert the closed surface integration, and if the function is continuous and differentiable, then only this is valid. I can convert this into a open volume integration, del dot v. So I have to take the divergence of my function. That's why the name Gauss divergence. So let's say if I want to find out this integration, right, closed surface r dot ds. Okay, so then we can say that we know that what is the divergence of r, del dot r, it is 3, right? So it will be del dot r 3 into dv, that is dy dx dz. If it is in the Cartesian coordinate system, this will be 3v, basically 3 times the volume, that's it. Similarly, if I have del cross f, what is the divergence of curl of f? So DC is always 0. Deccan Chargers, have they won anything? I don't remember they win. I don't think they have won anything, IPL or something, right? So DC is 0, right? So DC will be 0. So yeah, so the divergence of this function is 0. That means its surface integration also will be 0, because this part will be simply 0. Okay, so these are the things that you have to keep in mind. Let's solve a very basic question. Very basic question. So this function is given, the vector field is defined, ij cap are the coordinates, surface integration, we have to find out the surface integration evaluated over the inner and outer surface of a spherical shell formed by two concentric spheres whose centers are at origin of radii 1 and radii 2. So basically we know x equal to 0, y equal to 0, z equal to 0 will not be a, like, at that particular point the function will not be continuous and differentiable. So they have avoided that part. They are only asking me to calculate the the surface integration of this particular region, excluding the origin. So how can I solve it basically? So so we have to find out this, right? So d-rho d phi, so I can convert this part. I have to calculate the divergence of my function. That will be hectic. Divergence of my function. This I can write as x of r cube I cap f x plus where r is x square plus y square plus z square under root. Okay, so x plus yj cap plus zk cap. This, right, will be equals to r vector upon r cube. Okay, so I have to find out the divergence of f and integrate over the volume dv. So what will be this divergence? So we know how to calculate the gradient. I don't know how to calculate the divergence of this particular function. Divergence would be divergence would be difficult. It is only a function of r cap, right? So there we can, like, either you can remember the formula. I think there was a formula there, right, for divergence in the spherical coordinate system. If I go, yeah, divergence, if I want to calculate the divergence of a function that is in the spherical coordinate system, then I have to write h1 h2 h3, and this will be del of del r h1, sorry, h2 h3 into ar, basically, correct, ar cap. So yeah, like there is this way. I'll also tell you another way as well. So h1 h2 h3 in r theta sine, right, h1 h2 was r, basically h3 was r sine phi, so sine theta, right? So your h1 h2 h1 was 1, So this product would be r square sine square theta. This will be again r square sine square theta into AV. What will be your AV? So this is r cap, right? So let me write this in unit vector along r direction. That will be basically, this will be okay, r vector. Yeah, this is, yeah, r vector is fine. So the divergence would be this r square sine theta del r divided by 1 by r square sine theta. So this will come out to be basically 2r. So 2 by r, yeah, 2 by r would be the final, like, because sine theta will be cancelled. Okay, the divergence result would be 2 by r. But let's say I don't want to solve like this. What if I want to solve it with basics? So you can use the formula that I have told you previously. What if I want to solve using basics? So yeah, here I have told you how to solve using basics. This is, so if I want to find out the divergence del dot f, so this would be right. Okay, let me, I need another page. Let me put it here. Let me take another page. So in the Cartesian coordinate system only I am calculating the divergence. This will be del dot f, just I component. If I take, that would be, first of all I will differentiate the numerator and I will keep the denominator 1 minus, I will differentiate the denominator with respect to x. That will be basically, if I differentiate under root of x square plus y square plus z square, right, that is my r, sorry, this whole cube, right, 3 by 2 basically, this is my r cube. If I differentiate this function with respect to x, this will be x square plus y square plus z square 1 by 2 into 2x. That's it. Yes, and this will be basically 2x into r. Correct? Yeah, n, oh, n also is there, right? And I have to multiply by n into n minus 1. 3 by 2 will be cancelled. So this will be actually 3xr. 3x into r. Okay, 3x into r. Yes. Okay, 3x into r is there, and of course I have to take into consideration the numerator. So numerator will be there first of all into the differentiation of the denominator, that is basically 3xr. This will be 3xr upon, obviously, denominator whole squared, r raised to power 6. This was only for the I cap component. For the j cap component, it will be again r cube minus, it will be y into 3 yr upon r raised to the power 6 plus r cube into z into 3zr upon r raised to the power 6. So yeah, this will be 3r cube. This is what, 3x square minus 3x square, r is in the common, 3 or r is in the common, x square plus y square plus z square. This is nothing but r square r cube, yeah, 3 is in the common. Oh, sorry, 3 will not be there. Yeah, 3 will be there. So which is basically equals to r square. Okay, surprisingly it is coming out to be 0. Okay, it's coming out to 0. Okay, how is it then this is not coming out to 0? Oh shit, something went wrong. This is r vector. Oh, r vector. Okay, okay, sorry, one slight mistake I had made here. This is r vector upon r cube, right? So actually what I should have written here, this is wrong, right? because I should have written the unit vector. That's why you should not use formulas always. This will be basically r vector upon r, right, is simply ar cap, magnitude of r, dividing by the magnitude of r. So this will be r vector ar cap upon r square. That was your formula basically, ar vector upon r square. So now if I use this, correct, so I have to multiply this h to h3, this is my h to h3, right, into arrow av or ar is simply this 1 by r square. So 1 by r square into r square sine 2 theta, and I have to partially differentiate this with respect to r. So what we see is this is not a function of r anymore, right? Sine, not theta, it's sine theta actually, sine theta only, sorry, sine theta, not sine square theta, sine theta, okay, sine theta only. So this will not be a function of r, so this will be simply 0. So actually your divergence comes out to be 0 according to the formula as well. I here previously had written it wrong. So with basics I hope you can understand. You can use the formula. I'm not going into the formula right now, because if I try to explain the formula that will also take some time. But I hope you can understand the divergence comes out to be 0. If the divergence comes out to be 0, that means simply your answer will be 0. It does not matter, right, what is the surface given, because if your divergence was not coming out to be 0, let's say it was coming out to be 1, then you would have had to find out the volume by the small given volume, right? What will be the volume? It will be basically this cuboid, this sphere minus this sphere, that is the enclosed volume, if it was coming out to be 1. But in this case it is coming out to be 0, so answer will be 0, that is gone. If let's say the divergence was coming out to be 1, so then you would have had to find out the volume, that is 4 pi capital R cube by 3 minus 4 pi small r cube by 3. Okay, so yeah, capital R cube is the radius of the larger sphere, that is 2, and radius of the smaller sphere is 1. So 8 minus 1, that is 7 by 3. So this will be 4 pi 7 by 3, that is 28 pi by 3. If it was coming out to be 1, if it was coming out to be 2 or 3, then also you could have multiplied by 2. If it was, let's say, 2x, then you would have got a triple integration. You would have had to break the triple integration into double integration. That is what we have learned in the starting of today's lecture. And then you again had to solve the double integration. That will be very lengthy, and they will not give you. That is my expectation. They will not give you that much lengthy of a question. Mostly they will give you this simple. Mostly this constant function will come here. Okay. So the answer for this would be simply 28 by pi if this was coming out to be 1. For now the answer is 0. Okay. So now finally we will solve the PYQs. We have done enough theory. Now we will solve the gate PYQs of vector calculus. So let's start. Also we will be covering PYQs of EC, EIN as well as BM. So I will write this. We'll also cover BM branch. So we are covering new PYQs which you have not yet solved, which you are yet to solve. Okay. Let's begin with the first question. The unit vectors along mutually perpendicular axis x, y, z are given. Consider z equal to 0 plane. What does z equal to 0 plane mean? Z equal to 0 plane means that my x and y can be anything. So let's say my x, y and z is here. Z equal to 0 plane will be along the xy plane, this equation of the plane. So the normal vector would be either plus k cap or minus k cap, and two vectors a and b on that plane. So a and b are in the same plane, xy plane, such that a is not a scalar multiple of b. For any scalar b, a vector that is perpendicular to both a and b, that is what they are asking. A vector that is both perpendicular to a and b, which is not a scalar multiple. A and b are not scalar multiples of each other. So which vector will be perpendicular? Let's say my a vector is here and my b vector is somewhere here. They are not scalar multiples. Can you directly see geometrically which vector is perpendicular to both a and b? It would be either plus k or minus k. Whichever vector is perpendicular to this plane, that will be the vector that is perpendicular to both a and b. So plus k or minus k, only plus k is in the option, so option A will be your answer. So this is a question from basics that we have covered for 1 hour. So they are asking you questions from basics of vector algebra. It's not like they will only ask you calculus, vector calculus. No, they will ask you basics of vector algebra as well. With just visualization, we were able to solve this in 10 seconds. Of course, there is a formal proof. So let's say if I say that both A and B are vectors lying on the plane z equal to 0, that means A will be some xa I cap plus x ya j cap, because it is lying on the z equal to 0 plane, and your B would be, where is my B? Give me 1 second, let me turn off the internet. Yeah, B would be xb I cap plus yb j cap. Now of course they are not scalar multiples. So when will be a vector that is perpendicular to both A and B? If I find out the cross product, right? If I find out the A cross B, the resultant of this cross product, if I find out the direction by dividing by magnitude of A cross B, the resultant would be basically a vector that will be perpendicular to both A and B. So if I perform A cross B, this will be I j k xa ya 0 xb yb 0 A cross B. This would be 0 into 0, that is 0 only. This will also will be 0, only k cap will have a vector, and this will be xa into yb minus xb into ya. So as the vectors are not linearly dependent, so this determinant will never be 0. That's why they had provided you this condition. That was the reason. Many people will skip why this condition was given. There is a reason, because once you find out the curl, right, this should not come out to be a null vector. Otherwise you will not be able to, like, any vector then will be a perpendicular basically if this curl comes out to be 0. So there is a problem. That's why they have given you that, yeah, this is non-zero. So now we can safely say what is the direction. Direction is simply k cap. So k cap is a vector that is perpendicular, so it can be plus or minus k cap, right? Plus minus, both are saying the same thing. So plus k cap is in the option, so option A will be your correct answer for this question. Let's solve the second question, again from EC 2022. Consider two-dimensional vector field with x I cap plus y j cap. I j denote unit vectors along this. A contour C is given. This is the contour C in the xy plane as shown in the figure, composed of two horizontal lines. That is, what is the equation of this line? Y equals to 2. What is the equation of this line? Y equals to 0. And two ends of semicircular arcs of unit radius. The contour is traversed in the counterclockwise sense. If you see, we are traversing the contour in the counterclockwise sense. The value of the closed path integration f of xy dx dy. So just by seeing this, directly you can see this is in the two-dimensional space. So I can directly use my Green's theorem. Because this is continuous, right? This is continuous and differentiable. So I can simply use my Green's theorem. So again, it is in the anti-clockwise sense. So this will be basically, as it is in the anti-clockwise sense, first of all del x will be there, then del y would be there. So if I rewrite my integration, this will be x dx plus y dy. I could have solved this simply as well, but that would be a bit difficult. This one is easier. Yeah, now let me write this as my m, this as my n. So first of all del x will be there, so del n del x minus del m del y into ds, double integration, surface integration. Ds is nothing but dx dy. So this will be del n del x. Del n del x is 0. Okay, del n del x is 0, and del m del y is also 0. 0 minus 0 ds, this dx dy does not matter. Your final answer will be simply 0. So your answer will be 0. Now what is the homework for you? The homework for you would be simply, if I am taking the dot product, this is with, hold on a second, x I cap, yeah, everything is correct. Yes, so this will be n. I will differentiate this with this to x. Yeah, everything is correct. Yes, I'm just thinking like whether I'm making any mistake or not. Del m del x. Yes, this will come out to be 0. Yeah, correct. So now what we will do is we will uh, the homework for you, method 2, is solve using basics. What is the basic? You can use the Stokes theorem. Okay, you can use the Stokes theorem as well. Stokes theorem. Your closed line integration, right, will be del cross f of open surface integration dot ds. So here also you will see that your del cross f is coming out to be 0. So hence it will be simply irrotational. Correct? Yeah. Now let's solve the other one. Next question. Let v1 and v2 be two vectors. Okay. This will be I cap, j cap, k cap. So the first row will be I cap, second row would be j cap, third row would be k cap. The value of the coefficient alpha such that v1 is equals to alpha v2 plus e, which minimizes the length of the error vector. What is the length of the error vector? So let's say v1 which minimizes the length of the error vector. Okay. So v1 is what? v1 is 1 2 0 minus alpha into v2. So this will be 2 alpha into alpha into 3 alpha equals to error vector. So error vector will have a x component, y component, a z component. So ex is 1 minus 2 alpha, ey is 2 minus 2 alpha, 2 minus alpha, and ez is minus 3 alpha. So they are telling me that the length of the error vector must be minimized. What is the length? So my error vector is 1 minus 2 alpha in the x direction, 2 minus alpha in the y direction, minus 3 alpha in the k direction. So the length of this error vector would be whole under root 1 minus 2 alpha square plus 2 minus alpha square minus 3 alpha. This is the length of my error vector and this has to be minimized. So what will be the value of alpha? So I can simply differentiate this function, right? Let me write another function. If I have to minimize this, then I can say that L square also will be minimum and that will be easier for me to calculate actually. So L square, let me write that this as a function v. So I'll differentiate that function with respect to alpha and then I will equate it equal to 0 and I will get the condition for minima. So v is this squared, that is 1 minus 2 alpha whole square plus 2 minus alpha whole square minus 3 alpha square, and I will differentiate this function with respect to alpha and equate this equals to 0. So this will be minus 2 into minus 2 1 minus 2 alpha plus 2 into minus 1 into 2 minus alpha minus 6 alpha equals to 0. So this will be minus 2 minus 4 minus 4 plus 8 alpha. This would be minus 4 minus 2 alpha, sorry, plus 2 alpha and minus 6 alpha equals to 0. So this would be 8 equals to 10 alpha, 4 alpha equals to 8. So alpha would be equals to 2. Okay. Something is wrong because 2 is not in the options. I am messing up something. This has to be minima. This will be 6 alpha, correct. So inside function has to be minimum, right? So this will be 1 minus 2 alpha square, 2 minus alpha square minus 3 alpha whole square. Okay, sorry, extremely sorry. This will be plus 3 alpha, right? Yeah, because like I'm taking the mod of this, right? This 1 minus 2 alpha whole square, 2 minus alpha whole square minus 3 alpha whole square. I'm extremely sorry. Here I made a mess of it. Yeah, this will be plus 3 alpha. So this will be plus 6 alpha. So this will be 10 plus 6, that is 16. Still it is wrong. Still something is wrong. Okay, what is wrong? Okay, something is still wrong. So this will be 2, 1 minus 12 into minus 2, that is 4. So this will be this will be plus 8 minus 4, correct. This will be 2 into minus 1 into 2 alpha, yeah. This will be minus 4 and plus 2, correct. So this is 10, that is 16. This is okay, again I'm making a mistake, right? This will be 3 minus 3 alpha whole squared. So this will be actually 9 alpha squared. What am I doing? Something is happening with me. This will be like with that term only everything is going wrong. So 18 alpha, 10 alpha plus 18 alpha, that is 28 alpha equals to 8. So 4, if I multiply, this will be 2 by 7. Yes, 2 by 7 is in the options. That is correct. So alpha equals to 2 by 7 would be your answer. Of course, you might have a doubt, sir, how is this minima? Because only differentiation equal to 0 does not satisfy that my function will be minimum. It can be maximum as well. First of all, you are getting only a single value of alpha and they are asking you minimum. So of course, this condition will be for the minimum condition only. Second, of course, you can differentiate this function again and then put the value of alpha. You will see that that value is coming out to be negative. That means, sorry, that value is coming out to be positive. That means you will get a maximum. That is for your homework. The value of the line integral, this along the straight line joining the points P and Q. So they are asking you basic questions. Okay, they're not asking you double integration trivialization. This has been asked in EC 2023 without any knowledge of vector calculus. Still, you will be able to solve it if you have paid attention in the initial portion in vector algebra only. Okay, so here first of all, I have to write the equation of line. How do I write the equation of line? So how do I write the equation of a line in 2D? It is y equals to mx plus c. What is m? M is x1, sorry, y1, y uh, y2 minus y1 by x2 minus x1. So yeah, this is m. So if I want to write the equation of line, how can I write the equation of line? This will be y equals to mx plus c. So they will have what I want to do is like I want to write x equals to y minus c upon m. That is what I want to do, right? And that is y2 minus y1. So this will be y2 minus y1 into x2 minus x1, and that will go on the other side. So x minus x divided by x2 minus x1 equals to y minus c divided by y2 minus y1. And what would be the value of c? So I can say when x is equals to x1, then y will be equals to y1, correct? When x will be equals to x1, y will be equals to y1. Or let when x is equals to x2, y will be equals to y2. So y2 would be equals to m x2 plus c. So c would be equals to y2 minus m x2. So 2 minus, so this will be x by x2 minus x1 equals to y minus y2 minus, this will be plus m into x2 by y2 minus y1. And what is m? M is y2 minus y1 divided by x2 minus x1. So this will be x divided by x2 minus x1 equals to, this will be y minus y2 divided by y2 minus y1 plus x2 divided by x2 minus x1. So x minus x2 divided by x2 minus x1 equals to y minus y2 divided by y2 minus y1. This is the equation of a straight line basically in 2D. In 3D, you'll just extend this. This will be z minus z2 divided by z2 minus z1. Like for the students who forget, right, what is the formula? For those students, I am deriving it. In most cases, they will never derive this formula, okay, but I am deriving it. In the starting of this lecture, I told you the formula, remember it, but now I am deriving it so that you can also get and feel like how to remember this particular formula. So that's how you can actually remember it. Now, like you can assume this variable to be some variable t, and then you can solve singular variable t, and then you can simply solve. So in this case, the equation would be x minus x2, that is 2, divided by x2 minus x1, that is 2 minus 1, equals to y minus y2, that is 3, divided by y2 minus y1, that is 3 minus 1, and z minus z naught, that is 2, divided by z2 minus z1, that is 1 minus 2, that is minus 1, that is equals to t. So I will convert every single variable in terms of t, and then you can simply solve, or you can directly convert this z, because here I have z square, right? That will be a bit difficult. So yeah, we can replace our variables. My x will be equals to t, hold on a second, x would be equals to t plus 2, my y would be equals to 2t plus 3, my z will be equals to minus t plus 2. So I will replace all those variables in this equation, and then I will solve. So first one is z square dx. Z square is minus t plus 2 whole square dx. Now what is dx? Dx is simply dt, dy is 2 dt, and dz is minus dt. So dx is dt, and if my x is changing from x equal to 1 to x equal to 2, so when x is equals to 1, t is equals to minus 1, and when x is equals to 2, t is equals to 0. So x is varying from minus 1 to 0. X is varying from minus 1 to 0. So x is varying from minus 1 to 0 plus yeah, again, so not x, sorry, t is varying from minus 1 to 0. Again for the next term, it is 3y square. Y is what? 3 into y, that is 2t plus 3 whole square dt. Now dy is 2 dt. So here I will have, instead of dt I will write 2 dt plus minus 1 to 0 2x into z. So 2 into x is t plus 2, and z actually here, right, because it is only a function of y, right, I don't need to actually convert this in terms of t. I can directly integrate, right? This is like 3y square dy. This is very simple, 3y square dy, and y is going from y is going from what? Y is going from 1 to 3. So this will be 1, so not this, 1 to 3. Actually, like yeah, this is one, this was one of the, let me do one thing. Yeah, this is one of the way. And what is your dz? Dz is minus dt, so this will be minus dt, and x is also there, right? X into z. Z is basically minus t into 2 minus t plus 2 and minus dt, and then you can solve this. Like, this is one of the way to solve the integration. What is the other way? Other way is, instead of converting everything in terms of t, I can convert according to their differential. So here I have dx. So if all the values here are with respect to x, then this will be very easy for me to calculate. Here it is already y square dy, so I can calculate this. Here I have z, I just need to convert x in terms of z. So let me write x in terms of z. So this and this I can equate, correct? So my x minus 2, and I can multiply a minus 1 there. This will be equals to minus z plus 2. This is z, okay? Don't get confused. This is x minus 2. So I can say my x is equals to 4 minus z, or my z is equals to 4 minus x. So my dz would be minus of dx. But I don't need this information, but still dz equals to minus of dx. So yeah, okay, that information actually also will be helpful. So dz is minus of dx. So I can replace my dx with minus dz. So the first term will be z square minus dz. And how is my z varying? Z is going from 2 to 1. So this will be 2 to 1. Second term is very simple. It is y square, 3y square dy, and y is going from 1 to 3. And my, what I can say, what about this term? What is my x? X is 4 minus z. So I can replace this to be 4 minus z, and of course a 2 is there at the outside, 2 can come outside, into z into dz, and z is varying from 2 to 1. Z is going from 2 to 1. So I can club these two integrations together actually. So here this will be uh, z square, minus of z square, and minus 2z square. So overall I have minus 3z square, and this will be 8z plus 8z, and z is going from 2 to 1, plus this will be y cube by 3 y cube 1 to 3. So this will be 8 into minus 1 minus 3 into 1 minus 4 plus 27 minus 1, that is 26. So this will be minus 8 plus 9 plus 26, that is plus 1, that is 27. So your final answer would be 27, which is not present in the options. So somewhere I have done a mess. Okay, let me just think. Minus z square minus 2 minus 3z square, correct? Yes. Plus 8 z is there, yes. 3y cube by t, y is going from, z is going from 2 to 1. So this will be 8 into 1 minus 2, that is minus 1, correct? This will be z cube by 3. Okay, sorry, this will be cube, right? Sorry, this will be cube. So 1 minus 1 cube minus 2 cube, that is 8. So this will be minus 3 3 into 7, that is minus 21. Minus 21. Okay, still this value is very small. Still somewhere I'm making some mistake. 3 is there at the outside. This will be y cube by 3. 3 cube minus 1. 3 cube is 27 minus 1. This will be z square, z cube. 2 cube is 8. Yes. By 3 is automatically, sorry, by 3 is automatically getting cancelled, right? Sorry. By 3 will be automatically cancelled. Sorry. Minus 7. Yes. Minus plus 7. Okay. Minus plus 7 by 3 will be automatically cancelled. This is dz. sorry, what am I doing? I have to integrate this. What am I doing, man? I'm extremely sorry. This will be 8 4z square, correct? 4z square. Simple integrations, I'm messing it. So 1 minus 4, yes, minus 1 minus 8, yeah, correct. Yeah, now this will be 4 minus 3 minus 12, and this will be plus 7. Still I'm doing some minor mistake. Z square, right? So 1 square minus 2 square, that is 4, that is 3. 3 into 4, 4, yes, 3 into 4 would be 12. 1 minus 2 square, minus sign is there, 3 will be automatically cancelled, that would be 8 7, yes, plus 7, that is plus 5, and this would be 3 cube minus 1, that is 27. 2 is at the outside. What is happening? Simple integration I am not able to do. So z square minus z square minus 2z square, yes, z is there, 8z, 8z is there, 8z, this will be 4z square, 4z square. So 1 minus 2, yeah, I was just thinking what have I done wrong. So here, right, this will not be 1, right? X naught z naught z2 minus z1, this will be z2, right? That was like, that was the formula basically. Yeah, z2 should be here, I by mistake, so this is also wrong. So this will be t minus t plus 1, actually. I'm extremely sorry, right? There is a mistake. So z will be, this will be plus 1, this will be plus 1, this also will be, I guess, minus t plus 1. Yeah, so that's what I was thinking. What is going wrong? What is going wrong, man? So here this will be 3 minus x. Yeah, that is what I was thinking. Something is going, some silly error I'm doing. So 3 minus, this will be 3 minus z. So now I think it will be matched. Okay, I'm extremely sorry for pulling this so long. So 3 minus z. Okay, now I think it will be fixed. So this will be 6z. This will be 3. This will be 3 into 3 minus 9. Yeah, now finally it is fixed. 24. 24 is your answer for the question. 24. You can solve here as well. You will get the same answer. 24. Let's solve the next question. Let rho and u be density and velocity functions. You don't have to worry. Just they are functions of x, y, z and time. Del p upon del t is continuous. Let v be any arbitrary volume enclosed in the surface. Then del p upon del t plus del dot, which of the following equations are valid if del p upon del t plus del dot rho into u is equals to 0? Okay, very interesting. Del p upon del t is, so what I can say is del p upon del t is equals to del dot rho into u. This statement is definitely correct. So what I can do is I can take the volume integration on both sides. If I take the volume integration on both sides with respect to dv, then this, right, is nothing. I can use the reverse Gauss divergence theorem. What is the reverse Gauss divergence theorem? So reverse Gauss divergence theorem will be like, the divergence of this function would be, it will come from the closed surface integration of this function, that is rho u ds n cap. N cap is a normal vector from the that is pointing outwards of the surface. So this statement with the Gauss divergence theorem, because this function is continuous everywhere, I can use the Gauss divergence theorem. So where is this statement written? I think it is written in the option B. Which of the following equations is or are equivalent? So option B, it is definitely written. So option B would be definitely correct. Okay, now this is the MSQ, right? If I'm not mistaken. Okay, sorry. This is going on the right hand side, so there is a negative sign. Don't forget, there is a negative sign. So don't make a mess of it. There is a negative sign here, right? Negative sign. So negative sign would be there as well. So this option B is not correct. Option A is correct. So this is not your conventional Gauss divergence, but because I'm taking on the right hand side, then I'm taking the volume integration. Negative sign is there. Don't forget the negative sign. Okay. So option A is definitely correct. Now this is a MSQ, so you have to check other options as well. So this option is definitely not correct. What about this one? Del dot rho u is equals to, yeah, this is from where I got, right? Yeah, this is the first equation that I wrote here, correct? This equation. So this is correct. I'm taking the volume integration on both sides. This option C is again correct. This is the first equation that I wrote, right, without the Gauss divergence. So of course this will be correct. So A and C are my correct answers for this question. So they are asking you basic questions. They're not even asking you very difficult questions. Now let's solve another question. So this is a question. Let f1, f2, f3 be functions of x, y, and z, and suppose for every given pair of a and b, the line integral evaluates to same value along any curve that starts and ends at b. So the two points, the line integral is same. That means my field is conservative. Field is conservative. That is for sure. Now, if my field is conservative, can I surely say that it will be irrotational? No. Can't comment about rotationality, right? That del cross f equals to 0, I cannot comment. It can be, but I cannot comment. But if this is true, this will be definitely true, but I cannot comment the reverse. That is the first thing that you must write down. Now then which of the following options is or are true? For every closed path uh, tau or whatever this is written, we have this closed line integration to be 0. Yes. If a field is conservative, first of all, if it's open line integration, it does not matter which path I choose, I will get the same integration value. If it is a closed line integration and if the field is conservative, definitely it will be definitely the closed line integration will be 0, 100% sure. Okay, definitely the closed line integration would be 0, that is for sure. There exists a differentiable scalar function f such that f1 equals to del f by del x, f2 equals to del f by del y, f3 equals to del f by del z. There exists a differentiable scalar function. Okay. So this will be 0. Closed line integration will be 0. There exists a differentiable scalar function. So this, right? So what I can do is I can find out I can use the Stokes theorem according to this. If I use the Stokes theorem, this closed line integration, right, can be converted into a open surface integration del cross f dot ds vector. Okay. Now, of course, I cannot comment that del cross f will be 0 or not, null vector or not, but there can be two things here, right? This integration is 0. So there can be two things. Either del cross f is 0, or obviously magnitude of ds vector is it is not 0, non-zero, or the angle between them, the del cross f and the ds vector theta is 90. There can be two things. Okay. So so what is del cross f? Del cross f, if I write del cross f, right, that will be I cap, j cap, k cap. This will be f1, f2, f3. Sorry, first of all I will have to write the differential operators. So this will be del x, del y, del z. This, like, yeah, this is the curl of f, correct? So this will be equals to I cap into del f by del f3 by del y minus del f2 by del z plus j cap this will be minus j cap into del f3 by del x minus del f1 by del z plus k cap into del f2 by del x minus del f1 by del y. Now one thing is there, if my function, they are telling me that the function is same value along C, they have not mentioned anything. So if it evaluates, so if the field is conservative, right, then definitely function will be continuous. Okay. Function will be continuous, that is for certain, correct? If I'm going from a point to another point, function will be continuous. So okay, there is another way to solve this as well. Okay, one more thing is that if this evaluates to 0, if this evaluates to 0, let me assume that my this function, right, let us assume a function f vector field, that is f1 I cap plus f2 j cap plus f3 k cap, right? From if I do the dot product with dl vector, then I will get back my function dx I cap. This is actually a very good question, dx I cap dy j cap plus dz k cap. Actually very analytical question. Now I am doing the dot product with my function, right, and then I am calculating the closed line integration, that is coming out to be 0. So what I can say is this function, right, I can write this value, that is my closed line integration f dot dl is coming out to be 0, correct? So I can write this f vector field as a curl, sorry, not curl, gradient of a scalar point function, gradient of a scalar point function dot dl, that is equals to 0, correct? So if it's a gradient of a scalar point function, what can be said regarding the scalar point function, right? So okay, yeah, so basically if I am doing the gradient of a scalar point function, so what will be my f1? F1 will be del of phi upon del x, the x component, correct? F1 would be del of phi upon Lx, or like let's say this is some gradient of some scalar point function f. So F1 would be del of f upon del x, correct? And F2 would be del of f upon del y, and F3 would be del of f upon del z. Because I can write like this. So yeah, this second option is also correct. There exists differentiable scalar function, f1 is del f upon del x, f2 is del f upon del y, f3 is del f upon del z. This option is correct. Okay. Now, what about this option? All of this addition will be 0? No, certainly they will not be 0. I cannot certainly say, I can certainly say they will not be 0. Okay. Now here they have given the third option also as correct, but I think there has to be a bit of ambiguity because the surface is not given, because this, right, yeah, here I see that this is equals to 0, this curl can be equal to 0, that is one possibility, correct? That is one possibility, the curl can be equals to 0. Another possibility, if the angle between the surface vector and the curl is 90, that is also another possibility, correct? So in this case, if I equate this equals to 0, this equal to 0, this equal to 0, that is what they have given, the del f by del f3 by del y equals to del f2 by del z, right? Del f1 by del 2 is equals to del f3 by del x. They are just equating all this 0. So yeah, this condition is telling that curl of f is 0 actually, but actually this will not always be the case. Certainly I cannot say this will be true always, because the angle between them also can be 90, and when the angle is 90, then also this will be equals to 0. So I think there has to be empty. I don't remember exactly which options they gave as answer. According to me, option A and B are correct actually. Option D, it is not always true. They should always say that the surface that they're getting, right, from the curve, that is not perpendicular. If it is perpendicular, then also without this curl being 0, then also this value will be 0. Okay, so just be careful regarding this. This will be bit ambiguity. So I don't think option D is correct. I think option A and B are correct answer. So people in the comments below can let me know what is the correct official answer key for this. Okay, so yeah, let's solve the next question. Let E be a field, vector field, and we have to find out del dot E dv, where V is the volume enclosed by the unit cube. So yeah, you can find out this with surface integration, or you can directly take help of the volume integration. I not use any Gauss divergence theorem. You can take the Gauss, you can use the Gauss divergence theorem, that is E surface closed surface integration dot ds. What will be the surface? Surface will be the surface defined by the cube. That will be like we will have 6 different surfaces because a cube has 6 sides. So there will be 6 different surface. That is very hectic for you. So instead of doing it, directly calculate the divergence. What is the divergence? That would be 4x plus 5 plus 3 dx dy dz. And how is your x varying? X is varying from 0 to 1, y is varying from 0 to 1, and your z is also varying from 0 to 1. It is basically a unit cube. So this will be 4x square by 2, that is 2x square. So 2 into x square, that is 1 plus 8 into 1, basically that would be 10. So your answer would be simply 10. So you don't have to do the surface integration. You can check whether you are getting 10 or not, but you will get the same answer. Let's solve the next question. Let f of xyz be equals to this function, the direction in which the function increases most rapidly at point P. When does my function increase rapidly? In which direction will my function increase most rapidly? Along its own gradient. Along its own gradient. So what is the gradient of my function f? Gradient of my function f is equals to 8x plus 7y plus 3z square I cap plus this will be 7x j cap plus this will be 6xz k cap. This is the gradient. I will find out the value. I'll put the point 102. So if I put 102, okay, 102, that would be, this will be 8, this is 0 plus 2, so this will be 12 I cap 1, this is 7 j cap plus 102, this will be 12 k cap. Actually, right, they have asked in which direction. Actually they should provide unit vector, but they are directly providing the gradient only. So not properly correct, but still it is correct. So direction I can say, but just this is not the unit vector. They should have provided the unit vector. So 20 I cap 7 j cap plus 12 k cap, that will be option B. Option B will be a correct answer for this question. Let's move on to the next one. Let R be the region in the first quadrant xy enclosed by the curve C in the counterclockwise direction, in the anti-clockwise direction. Which of the following expression does not represent the area of the region? So 1 dx dy about the region R, yes, this definitely represents the area. So this is not my correct answer. X dy, will x dy represent the area? X dy also represents the area actually. Do you remember what is x? X is simply f of y dy, and this also along the curve, right? If I integrate my f of y along the curve, this will actually represent the area. This is also correct. How can I verify? You can use the Green's theorem. You can use the Green's theorem. So if you use the Green's theorem, I have x dy plus 0 into dx. So remember, in the anti-clockwise direction, so first there will be x, then there will be y. So first there will be del x, then there will be del y. So this will be my m and this will be my n. So first I will write del x. So del m, so this m will be with respect to y, right? So first I will write del n into del x, that will be 1, and del m into del y is 0. So 1 minus 0 into the surface, I am using Gauss divergence, that is dx dy. So yes, this is representing my area only, dx dy. So this is correct. Similarly, this also will be correct. If I see, this also will be correct most probably. I will just check once. So this will be basically, now my function is y dx plus 0 into dy. So here again let us assume this to be m, this to be n. So first of all I will write del n del x, that is 0 only. Okay, then I will write minus del m del y, that will be 1. Actually, okay, no. So this minus del m del y, so this will be minus 1 dx dy. So actually this does not represent my area, this is negative of my area. What about the last option? So this option is actually correct, this does not represent my area. Let me check the last option as well. If I check the last option, again I will apply the Green's theorem. So this time it is x dy minus y dx. So again I will assume this to be my m, or let me assume this to be my m, this to be my n. So first of all I will do del m minus del x because it is in the anticlockwise. So del m minus del x will be 1, and then I will do minus of del m minus, so this time right your n is minus y, just don't forget m is minus y, okay, m is minus y, n is minus y. So what is del n minus del n del y? It will be minus 1. So this will be minus 1 basically, and minus sign is already there at the outside, into dx dy, and don't forget there is a half at the outside, so half sign is there at the outside. So this will be double integration dx dy, that's it. So this will be the answer. So yeah, this also is the area of the surface only. So option C is incorrect, it does not represent, it represents the negative of area. So just be careful, and without even remembering the orientation, everything, without doing that, I'm directly solving it. That's the advantage that students of PrepFusion will have if you are following the R-PYQ series. Let's solve the next one, this one. So for a given vector, the vector normal to the plane W transpose x equals to 1 is. So first of all, let me find out the vector W transpose into x equals to 1. So W transpose into x. So W transpose would be simply 1, 2, 3, and x, let's assume that x is a column vector because column we represent in column only. This should have properly mentioned x1, x2, x3, right? This will be 1 cross 3 and 3, yeah. So this will be basically x1 plus 2x2 plus 3x3 equals to 1. Now they're asking for a given vector, the vector normal to the plane defined by this, the vector normal to the plane. So I can assume this to be my, like, basically x, y, z. So this will be x plus y plus 3z equals to 1. So I have to find the vector that is normal to this plane. How can I find? Simply find out the gradient. So gradient of my function. So let me write phi is equals to x plus 2y plus 3z minus 1. So grad of phi would be equals to this will be I cap plus 2j cap plus 3k cap, that's it, the vector that is normal to the plane. So yeah, 1, so what are the direction ratio? 1 2 3, 1 to 3. So 1 to 3 is present in the option D. So option D will be correct. Actually this question can be more well defined, but like I hope you get the idea. Like you have to just find out the normal vector and then you can equate the components, x component, y component and z component. Let's solve the next question. So mostly questions will be solved in minutes only. The closed curve shown in the figure below is described by this particular relation where r is equals to 1 cos theta and x is equals to r cos theta, y equals to r sin theta. Magnitude of the line integration of the vector field around the closed curve would be, what is the magnitude of the line integration? Minus yd plus xj closed curve. So yeah, dx I cap plus dy z cap. So what we can do is we can actually, can we use the property? Will that be helpful? Let's not use the property because calculating the surface integration would be a bit difficult. Let me choose this. This will be y dx plus x dy. I have to calculate along the closed curve, right? So basically, how is my r varying? So I have to calculate. So theta will start from here. Let's say from 0 to 360, 0 to 2 pi t, 2 pi, right? Theta will go from 0 to 2 pi. But okay, I have to anyways convert this, right? Because both r and theta are varying. Yeah, both r and theta both are varying actually. Or no, because r is this relation, correct? So what I can say, okay, let me convert this. So what is del r in terms of, so what is del r del theta? That is equals to minus of sine theta. Yeah, so del r is equals to minus of sine theta d theta, correct? Yes, that is true. So what will be dx? So dx would be equals to, like, x is equals to r cos theta. So dx, okay, there are two components here, two things that are varying. That will be difficult. So we have to convert this into double integration. Yeah, we don't have any other option. We have to convert this into double integration. Okay, no problem. Otherwise, this will be a problem. So yeah, if I convert this into double integration, again, orientation have they mentioned around the magnitude of the line. They are asking magnitude of the line integral. So they are asking magnitude of this. So it does not matter what orientation I choose. Anyways, they are asking me magnitude. So clockwise or anti-clockwise, there is just a difference of negative sign. So it does not matter. I can assume clockwise. Sorry, I can assume counterclockwise. So if I assume counterclockwise, so if I assume this to be my m, this to be my n. So first of all, I will do del m by del x. Then I will do del n by del y, and this surface integration dx dy. So this will be del m minus del x is 1. Okay, 1 minus 1, that is 0 only. This coming out to be 0. So we don't have even have to solve this. That's interesting. Am I doing this correctly? Del m minus, hold on a second, this is y close. Okay, sorry, this is minus. That minus was there, right? Don't forget. That's what I thought. It should not be that simple. It is minus. So this will be actually 2. Minus of minus 1, this will be 2 dx dy. So here I will have 2 into surface integration of dx dy. So as this is in the polar coordinate system, right? R cos theta, r sin theta, I can use conversion. So this will be 2 dx dy will be converted into rho or r. Let me write rho d rho d phi, otherwise you will be confused. Okay, I hope you remember these things. So what are the how is my rho varying, or how is my r varying? So theta, right? Theta goes from 0. Theta starts from, sorry, yeah, theta starts from, let's assume, what is the minimum value of r? The minimum value of r is r equal to 0, right? When r is equal to 0, what is the value of theta? Theta is minus pi, right? When theta is minus pi, then r is 0. Yes. And when r is equals to what, r maximum value of r, that is the distance from the origin, this is the maximum value, that is r equals to 2. Okay, so r is going to 2, or okay, oh, no, what am I doing? Let me do this. Let me take strips here, right? That is the best way to do. So let me take a strip. Yes, that will be the best way. Rho d rho. R is this curve described 1 plus cos theta. When theta is 0, then this is 2. Okay. So just hold on a second. I'm getting a call. Okay. So how is my R? So this time, right? How do you choose your R basically? So if it is the equation of a circle, we say that if the circle is varying, so we say r equals to 0 radius to r equals to this, whatever is the equation of the circle. Let's say that I am giving you a surface that is x square plus y square less than 4. So we say the radius is varying from r equal to 0 to r equals to 4. So that will be the limits. But this time, right, the radius is starting from 0, r equal to 0, because the lowest radius is 0. Then I am going and touching this curve, that is r equals to 1 plus cos theta. So they should have properly provided the equations here. So r will be starting from 0 to r equals to 1 plus cos theta, and your theta, definitely you are covering a whole circle, right? Whole curve. So theta will go from start from 0 to 2 pi. So this will be rho square by 2, that is 2 into 1 by 2, that will be cancelled. This will be 0 to 2 pi. This will be 1 plus cos theta whole squared d rho. So d phi, right? Rho square by 2 is gone. So this will be 0 to 2 pi cos square. So this will be 1 plus 2 cos theta plus cos square theta into d phi. So 2 cos theta d phi, theta is simply 0, and this term would be basically, if I want to solve this one, this will be 2 pi plus, I think this will be pi by 2, if I am correct, because over a cycle this value is pi by 2. Yes, this value is pi by 2. So what will be the answer? So 2 pi plus pi by 2, if I am not mistaken. Hold on a second now. This will be rho square plus 1 plus cos 2 theta 0 to 2 pi, that 0 will go away. Okay, yes, that 0 will go away, theta will be there. So by simply square it, this will go. Let me just remember what was this. So again I can break the cos square theta. So what is the cos square theta integration? So actually I tend to forget this, 0 to 2 pi, correct? So this can be broken down into d theta is there, correct? So this can be broken down, cos square 2 cos square theta would be equals to cos 2 theta minus sin square theta, will go there, 1 plus cos theta upon 2. So this will be, that term will anyways be gone. So yeah, 2 pi, yeah, pi. So this will be pi, sorry, pi. This will pi. I hope we can solve this, right? 2 pi cos phi. So this will be 3 pi. So 3 pi would be, I think, 9.42 something. 3 pi if I solve would be 9.42. Yeah, 3 pi would be 9.42. So 9.42 would be your answer for the question. Okay, that would be your answer. Like, this question was good actually. Properly they should define exactly what they're talking about. Radius is starting from 0 to 1 plus cos theta. So 9.42 would be your answer for the question. Let's solve the next question. So this is the next question. Here, a quadratic function of two variables is given. Magnitude of maximum rate of change of the function at point 1 comma 1. Okay, actually this is not a vector calculus problem per se. This is a like a maximum minimum problem, right? I've been given a function into variables. Actually there are two variables, so what you can do is individually you can calculate the derivatives and equate that equals to 0, or you can also, they are asking you the maximum rate of change of the function. When do we get the maximum rate of change of a function at particular point along its direction of gradient? That is the maximum. Actually this is the vector calculus problem only. Maximum rate of change, they are asking me the maximum rate of change, they are not asking me the maximum value of the function. No, read the statement properly. They are asking me the magnitude of maximum rate of change of the function. What is it? It is the directional derivative of the function along its gradient. So magnitude of del f upon magnitude of del f at this particular point. Sorry, magnitude, yeah, first of all find out the gradient of the function and then take the dot product with the gradient divided by the magnitude of del f. That's it. Yeah, correct. So what is the gradient of the function? Let us assume that x1 and x2 are two dimensions. So I will differentiate with respect to x1, that will be 2x1 plus 3 plus x2. Let us assume that this is in the I cap direction and x2 is in the j cap direction. So If I differentiate with respect to x2, that will be 4 of x2 plus 3 plus x1. Okay, if I put the, what is gradient of f at the particular point 1 comma 1, this will be 2 plus 3 5 plus, so this is 6 I cap plus 7 8 j cap. So now I just simply have to find out the divergence along its own direction. So what is a of f? A cap, right? So this will be basically 6 I cap plus, actually this will be 3 I cap, 3 I cap plus 4 j cap divided by 5, divided by 5. So yeah, that is the unit vector. So if I take the dot product, this will be 18 plus 24 divided by, sorry, this is not 24, right? 32, 18 plus 32 divided by 5, that is equals to 10. So the maximum rate of change of the function would be simply 10. This will be your answer for the question. Now let's solve the next question. Okay, consider the vector u uh, equals to this value and directional derivative of the function this at the point this in the direction of u. That's very simple. So first of all I have to find out the direction vector of u. That would be uh, so if I put the point, right, this is 2i u at the particular given point is 2i plus 2j plus 2k, and the unit vector, sorry, this is y cap only, sorry, this is y cap only. So yeah, let me just write this xy. So x cap plus y cap, it is a constant function. So if I divide by the magnitude, that could be 4 plus 4 plus 1, that is under root 3. So this will be 2x cap z cap upon 3. So that is what AU cap is. Now uh yeah, f of xyz, I have to find out the gradient of f of xyz. That would be this will be ln, so 2 by x y, that will be very hectic, plus this is already a function of yz, xz is there, so this is anyway 0. Differentiation of with respect to x, this will be 0. Differentiation with respect to x, this will not be 0. So first of all, what is the differentiation with respect to x? 2 upon xy into differentiation of the inside function, that is y, plus differentiation of this function with respect to x, that is 3 upon xz into differentiation of the inside function, that is z. So yeah, that is the x cap component. Similarly for the y cap component, this will be 2 upon xy into x plus 1 upon yz into z. Y cap component plus the z cap component. So z cap component will be 3 upon xz hold on a second, differentiate with respect to z, that is 1 upon yz into y plus 3 upon xz into x. So yeah, this will be 2 upon x plus 3 upon x, x cap plus 2 upon y plus 1 upon y. So this will be actually 5 upon x cap. Give me 1 second. This is not erasing. Okay. This will not go with, sorry. So let me just write for now sake of it. 3 upon y cap plus this will be 1 upon z plus 3 upon z, 4 upon z cap. So let me put the value of x, y and z, that is 1, basically 1 1 1. So this will be 5 x cap plus 3 y cap plus 4 z cap. Now we'll take the dot product with the direction. So 2 into 5, that will be 10. Then 1 into 3, that will be 3, plus 2 into 4, that would be 8 upon 3. So this is 21 upon 3, that is 7. So 7 would be your answer for the question. Let's move on to the next question. So we have this xy that belongs to two-dimensional region. The rate of change of the real valued function at the origin in the direction this. So they are just simply asking you the directional derivative. So rate of change of the real valued function at origin in the direction of the point 1, 2. So in 2D, right, at origin and in the direction 1, 2. So basically it is pointing towards the direction 1, 2. So what is the directional vector? So I have to write this position vector, that's it. That is my directional vector basically. Indirectly they have not given you the directional vector, you have to write the directional vector, that is OP. Okay, OP would be x minus 0 from the origin, that is 1, that is I cap, plus 2 minus 0, that is 2 j cap. Okay, I cap plus 2 j cap, that is your position vector. So I have to obviously write the unit vector about the position vector, that is I cap plus 2 j cap. So I cap plus 2 j cap divided by under root 5. So yeah, that is my position vector, sorry, that is my direction vector. What will be the rate of change? Rate of change will be the simply the gradient and then taking the dot product, that is the directional derivative. So let me find out the gradient. So that would be 2x plus 1 I cap plus 2y j cap. Now we'll put the value, I'll put the value right at origin. They are asking at origin, remember at origin they are asking. So at origin x is equals to 0, y is equals to 0. So this will be simply I cap only, that is my gradient. So the directional derivative would be del v dot AOP, this would be 1 under root 5. So 1 under root 5 would be your answer. Now remember, they are asking you to round off to the nearest integer. Read the question. They are asking you to round off to the nearest integer. So this will be very smaller than 0.5 actually, because 0.5 is 1 by under root 4. So that this is greater, right? Under root 5 is greater than under root 4. So definitely it will be 0, because they have asked you to round off to the nearest integer. Okay, just be careful. I think at the end they have provided you this range, but read the last part, round off to the nearest integer. So answer would be 0 actually for this question. Let's move on to the next question. This one, yeah, I1 2024. I think I have removed. Yeah, we have BM question as well. Don't worry, we have BM question as well. Let's see be the closed curve in the xy plane traverse in the counterclockwise direction. So it is traverse in the counterclockwise direction. So x is going from to y. Along the boundary of rectangle vertices 0 0 by vertices 0 0 2 0 2 1 and 0 1. Yes, so basically this is the curve, right, along which we were calculating the integration in the anti-clockwise direction. The value of the line integral would be what? Simply again you can use the Green's theorem. So if I use the Green's theorem, because this function is continuous and differentiable, so again it is in the anti-clockwise direction. So first I will choose del x. So I will differentiate this with respect to x. that will be e raised to power x. Just hold on 1 second. Previously did I move the things? Yes, I think I did move the things. Yeah. So then I will again differentiate with respect to y. This will be minus of e raised to power y, and then this will be dx dy. Okay, dx dy. So yeah, this would be, so what will be the integration? Basically e raised to power x dx. That is interesting. So how is my x? So actually you will not be able to, so you have to do the surface integration. So I can take a strip, any strip you take, right? So if I take a vertical strip, so what is changing here? So this line is y equal to 0, this line is y equals to 1, right? Because this point was 2 comma 1, this point was 0 comma 1. Okay, and how, what is the range of x for this vertical strip? X equal to 0 to x equal to 2. So my x is going from 0 to 2, and my y is going from y equals to 0 to y equals to 1. E raised to power x plus e raised to power y dy dx. Remember, this is the limit of y. So I can solve this. This will be e raised to power x dy. So this is constant, that will be into 2, so into 1 plus e raised to power y, and the range is 0 to 1, and now I have limits of x dx. So your masters are solving the double integration, so I'm going through this bit quickly. So this will be e raised to power, so this will be actually e raised to power x plus e minus 1 dx 0 to 2. So this will be e square plus e minus 1 into 2, minus 1 is also there, right? Yeah. So this will be e square plus 2e minus 2 minus 3, so minus 3, e square minus 2e minus 3, e square plus 2e minus 3. So that is present in option A. So option A would be your correct answer for this question. So it needed bit of double integration, very simple strip, and knowledge about Green's theorem. That's it. Mostly you have to solve using Green's theorem, divergence theorem, or Stoke's theorem. That's it. Okay. So inverse Stokes theorem is also asked, but rarely. So let me solve the next few questions. The value of the surface integral this over the surface is x square plus y square z square. So we have to solve this. Dy dz dx dy over the surface. That is interesting. So this is a closed surface that they have given me. So this function, right, can be converted into, so this surface is what is dy dz, or let me first use the easier, what is dx dy? Dx dy is a differential surface on the what plane, on what axis? Xy axis. So what will be the direction of dx dy? K cap, right? Direction of the area, small area dx dy, what will be the direction? K cap, correct? So direction is k cap. Similarly, if I am lying in the, so this is my x and y, if I am lying in let's say yz, if I am lying in yz, what is the direction? Direction would be, this is my x direction, so the direction of the differential surface would be along I cap. Okay, so that is the thing basically. So these, right, this I can rewrite my surface integration like this. This will be some f vector dot the surface vector. I think I have forgotten to mention what is the surface vector. It is basically dx dy I cap plus dy dz j cap, so not j cap, sorry, what I mean, dx dy k cap plus dy dz I cap plus dz dx I cap, sorry, j cap, dz dx j cap. So yeah, that is how I can write my surface vector f dot ds. So this I can write. So if what is the advantage? Because it's a closed surface, it's a closed sphere, I can write this in terms of my divergence theorem. That will be del dot f dv. That will be much more easier for me to solve. So f dot ds, right? So f dot ds, f will have three components: fx I cap, fy j cap, fz k cap. So if I do f dot ds, so fx dot this, sorry, fx dy dz, fx dy dz plus fy dx dz plus fz dx dy will be the dot product result, right? That is what is written over directly here. So f of x into dy dz. So this is my f of x basically. This is my f of y. This is my f of z. So f of x is 2x plus z I cap. F of y is 2, sorry, yeah, f of y is also 2x plus z j cap, and f of z is 2z plus y. Okay. So yeah, now I can simply calculate the divergence. Divergence would be, this would be 2 plus this will be 0 basically, because this is 2x plus z, and this will be 2 dv volume integration. So that would be 4 into volume dv. So 4 into volume, right? 4 into 4 pi r cube by 3. R cube would be, r square is 9, so r is 3, so this will be 3 cube, so 3 square, so 16 into 9 pi. Okay, 16 into 9 pi, that would be your answer. So 16 into 10 is 160, so this will be 16 minus 160, that is 144 pi. So 144 pi would be your answer for the question, that is option B. Let's move on to the next question. This is the next question, right? This is a BM question now, so we are solving few questions which you have not ever solved. So given a scalar function, the directional derivative in the direction of the vector this at point 1 comma 1. So first of all, let me find out the unit vector of the given direction vector. At 1.1 this will be 3i minus 3j, so this will be basically I minus j under root 2, that is the unit vector along the given direction. And what will be grad of v? Grad of v would be 2x, sorry, x I cap plus y j cap. So 1 comma 1, again at 1 comma 1 this will be I cap plus j cap, so unit vector would be I cap plus j cap by under root 2. So your directional derivative would be dot product of this, that is 1 minus 1 divided by under root 2, that is basically 0. So your directional derivative is simply 0, that is present in option B. So option B is correct. Let's move on to the next one. So if a v is equals to a plus b plus c, this value, identify the invalid operation. What is invalid? I am doing curl of my vector point function, then taking the divergence. Is this valid? Yes, this is definitely valid, right? Because I can take the curl of a vector point function, and then I can take the divergence, because the output of this will be a vector only, let's say a vector, and I am taking the divergence of a vector, that is totally valid. Here I am first taking the divergence of a vector point function. If I do the divergence of a vector point function, I will get a scalar function s, but I cannot take the curl of a scalar function. This operation is absolutely invalid, and they are asking which is invalid, so option B will be correct. Here again, if I see, I am taking the divergence, I am getting a scalar function, and I am taking the gradient of the scalar function, operation valid. Here I am taking the gradient of a vector function. Okay, gradient of a vector function, is this valid? Curl, sorry, gradient of a vector function is also not valid, right? think they have missed the mark here. I think D also will be wrong, right? Gradient of a scalar function. Gradient of a scalar function is invalid. Right? You cannot take the gradient. You can take the divergence of a scalar function. I think here, right, they missed a dot. But if you take the divergence, yeah, that will be anyways wrong. Gradient of a scalar function. Not a scalar, sorry. Gradient of a vector function. Gradient of a vector function. Uh, you are taking the gradient of a vector function. Yes, actually that is also valid, right? If I have a vector function, I'm taking the gradient. That is also valid. That is not a problem. But I cap plus del del y j cap plus del del z k cap, and I have, let's say, this a I cap plus b j cap plus c k cap. Okay, okay. This will be, this is not dot product, this is just simply multiplication. I'm just multiplying them. So if I'm multiplying these values, no, that is not valid, right? Oh, still, no, I cap into I cap, there is no operation as I cap into I cap, correct? Only dot operation is there. So actually this is also incorrect, I believe. This also should not be correct, because in BM no one checks this question. So in GATE maybe they give bit of wrong questions. Okay, I feel this one is also incorrect. So using divergence theorem, evaluate the integral. So directly they are telling you just use the divergence theorem and evaluate the integral. That is very simple. So the surface that they have given me is, like, they have also told this is the surface of cone. They could have not mentioned it, right? Because we have studied this is the surface of a cone, right? Where my x square plus y square is less than z square. That means x square plus y square is varying linearly. My radius is varying linearly, right? So this is the surface of the cone. Z is going from z equal to 0 to z equal to 3. So everything they have given you. So you have to use divergence theorem. So what will be del dot f here? Del dot f would be, this would be 4 plus 3 plus 5. So 4 plus 3 plus 5, that would be 7 plus 5, that is 12. 12 v, basically 12 dv. So it will be 12 v. What is v? What is this volume of the cone? It is, I think, 1 by 3 pi r square h. That is the volume of a cone, correct? So 12 into this, so that is 4 into pi into r square. R is basically z square, that is 3. So that will be 9 into height, where height is also 3. So this will be basically uh, with the unit of value of the integral rounded off to nearest integer. This is 27 into 4. So 27 into 4 would be 108 pi. Okay, 100, and if I am not mistaken, just hold on, using divergence theorem, yeah, hold on a second, r square z square, yeah, 1 by 3 pi r square h. If I take the divergence, okay, hold on a second, hold on a second, don't be in a rush, don't be in a rush. So this will be 4, that is, this is not 3, right? This is 0. Differentiation with respect to y, this is 0. I'm extremely sorry. And this will be also 0, sorry, don't be in a rush, don't be in a rush. This will be 4 actually, yeah. This will be 4, divergence will be 4, this will be 4, this will be 4, this will be 4. So this will be 4 by 3. So this will be 3 into 3, 9 into 4, 36 pi. So what is, round off to the nearest integer. So if I round this off to the nearest integer, just give me 1 second. 36 pi, I think, yeah, 113. So your answer would be 113. They are asking you to round off to the nearest integer. 113 would be your answer for the question. Okay, so this is the last question that we will solve. In BM mostly they ask easy questions. So here they are asking, the function is given, the value of the closed line integration along the path shown, it is in the anticlockwise direction. Again I can use the Green's theorem. So if I use the Green's theorem, this will be like f dot dr. So it will be xy dx plus x plus y dy integration, right? So like this differentiation will come out to be same actually. So it is in the anti-clockwise direction. So first I will differentiate the x. So it will be 1 minus this one, then I will differentiate this one, that is 1, and then the integration, like double integration, that is 0. So answer will come out to be 0. So your answer would be 0 for this question. Like mostly in BM they ask very simple questions. So with that we have ended our vector calculus portion. Now we will start with the complex variables portion. Let's begin with complex variable. So we have covered vector calculus in about 6 hours. So complex variable will also take around 5 hours to complete. So again, similarly like vector calculus, as we have covered vector algebra, now we will cover complex numbers, basics of complex numbers, and then finally we will start with the complex calculus. So up until now we have done calculus on real functions, scalar functions, then we have done calculus on vector functions which have a direction. Now we will do the same calculus on complex functions, because complex numbers are also very important, because we have a very important quantity, that is phasor, and phasor are used with complex variables. Those are complex numbers. Power, apparent power is a complex number, reactive power is a complex number. So understanding complex number is also very important. So we will begin. Just give me 1 second. So first of all, we will understand what is a complex number. What is a complex number? A complex number is the sum of a real and a imaginary number. What is imaginary number? Imaginary number is this one, iota, I. That is your, just hold on. That is your imaginary number, I. So that is equals to under root of -1. Just give me 1 second. Let me turn off the internet. Yeah, under root of -1. This is a imaginary number. So complex number contains both imaginary and real number. That is a combination of real and imaginary. So z is written as x plus iy, where x and I both belong to real sets of number, and your I is the one that actually makes this part imaginary. So this part is called as imaginary part, this part is called as the real part, and this z x y is called as a ordered pair. So a complex variable is of the form x plus iy and is usually represented by z. Both x and y are real numbers. X is called the real part of the complex number, z also denoted by real of z, and your y is called as the imaginary part, which is denoted by imaginary of z. Iy is called the imaginary number. So I has very properties, right? Because we know I is basically under root of -1. So if I do I square both sides, it will be basically -1. It will be -1. I'm not going into the details like how complex number came, what is the importance. I'm not going into that. You just know that I is under root of -1. That's it. Mathematically, this much is important. If I do I cube, what will be I cube? So I square is -1. If I want to find out I cube, I can multiply I on both left hand side and right hand side, LHS and RHS. So it will be I cube equals to, sorry, this is -1. So this will be minus of I. So your I cube is minus of I, and your I raised to power 4. If I multiply by I again, this will be I raised to power 4 equals to minus of I square, and I square is -1. So this will be actually 1. So I raised to power 4 is 1, and this cycle will repeat. Basically, then again if I go into I raised to power 5, it will be I only, because I can cross multiply I both sides. So every fourth period power of I will result in 1. Like I raised to the power 4 is 1, I raised to the power 8 is 1, I raised to the power 12 is 1, I raised to the power 4k plus 1, where k belongs to any integer, right? Any integer. I raised to the power 1 is I raised to the power 5 is I raised to the power 9 is I. Again, I square is -1, I raised to the power 6 would be -1, I raised to the power of 10 would be -1, like that, and this also will be similar. Okay, so I will just follow a coordinate. So this is also called as a complex plane. It can be shown graphically. We used to have x and y, right? So similarly, this is also x and y, but x represents the real part of z, complex number, and y represents the imaginary part of z. So if I keep on multiplying I, basically I am shifting my axis. So initially I was here 1 is a real number. If I multiply 1 with I will move on to the imaginary axis. Then again if I multiply I, again I will come to the real axis, but this time I square will be minus 1. Again if I multiply I, this will be minus of I. I will come into the imaginary axis but in the negative side. Again if I multiply I, this will be minus I square, that is simply 1. Okay, so that's how I is represented graphically. So there is a very like basic question. You have to find out the value of the sum going from n equals to 1 to 13 of I raised to the power n plus I raised to the power n minus 1. Whenever you have a series kind of question, you write few terms of the series. So n equals to 1, this will be I raised to the power 1 plus I square. Then again n equals to 2, this will be I square plus I cube, and n equals to uh, 3, this will be I cube plus I raised to the power 4. Now one thing is there, right? So we know one thing, that I is equals to I only, I square equals to minus 1, I cube equals to minus I raised to the power 4 equals to plus 1. So this will be I, this will be minus 1, this will be minus of I, this will be plus 1. So what is happening, every period of 4, this sum is actually simply 0. Similarly, if I say I raised to the power of 5 plus I raised to the power of 6 plus I raised to the power of 7 plus I raised to the power of 8, this sum will again be 0. So same thing will happen here. So I will get a series I square, I cube, this will go on till I raised to the power 12. Those are basically groups of 4, that will be simply 0. Then finally I will have I raised to the power of 13. I will finally have I raised to the power 13 for this term. I am talking about for this term. So because that will not be paired with any quad. So I will have I raised to the power 13 alone. All the other terms will be simply finally 0. You can write the numbers, you will see they are adding up to 0. And for the second term, I will get, first of all, I will start with I square, then it will be I cube, I raised to the power 4 plus I raised to the power 5. This sum again will be 0. The last term will be the odd one out. This sum will be 0. You can add this, all this up, this will be 0. Last term would be I raised to the power of 14. So I will have I raised to the power 13 plus I raised to the power 14, that will be left out. That will be equals to, this will be basically, what is I raised to the power of 13? So I raised to the power of 12, right, is a multiple of 4. So it will be 1. So this will be I raised to the power 13 will be simply I. And I raised to the power 14, because I raised to the power 13 is I raised to the power 14 would be minus of 1. So your final answer will be I minus 1. So you can write down the terms, you will see only you are left with these two terms. Okay. So I minus 1 will be your answer. Now there are few operations, just like in real variables you can do addition, multiplication. In complex variables also you can do addition, multiplication. Just be careful while multiplying complex numbers. Addition would be whenever you are adding to complex numbers, you can only add the real parts of the complex numbers and the imaginary parts together, because they are similar quantity. Just like you cannot add speed and distance, these are different quantities, right? These have different units. Similarly, you cannot add real part and imaginary part together. No, you cannot club them. You can only add either both the real parts or the imaginary parts. So here if I do z1 plus z2 to complex number, then the real parts will be added and the imaginary parts will be added separately, and they will be written separately, like x1 plus x2 plus y1 plus y2. Similarly, if I say z1 equals to z2, then basically what do we mean? We mean that the real parts are same and the imaginary parts are same. That's it. Okay, so the real part and imaginary part are two separate quantities, different quantities. Similarly, if I am multiplying two complex numbers, then it is just like a vector multiplication. So I can do x1 into, I can expand this multiplication, x1 x2 and this multiplication. This also I can do. So basically it will be x1 x2 into x1 into I y2. Wherever there is I, that will be coming out with the imaginary part. Then again if I multiply I y1 with x2, I y1 with x2 and I y1 with y2. So I square would be minus 1 and y1 y2 would be simply y1 y2. That's it, correct? So I square is minus 1 and y1 is a real number, y2 is a real number. This also is a real number, I square is minus 1. So ultimately this comes out to be totally real. So I'll write this with the real part. So what is your real part? x1 x2 is a real number minus y1 y2. That is my real part. What about the imaginary part? Imaginary part would be this: x1 y2, x1 y2 would be imaginary, and y1 x2. So these two would be my imaginary parts. I hope you get the idea. Okay, so x1 y2 and y1 x2. So I hope you get the idea. That's it. Yeah. So this is my imaginary part, this is my real part. This representation, we can use Euler's representation to multiply. Like there is a representation I will show you, that will be like polar representation. Okay, I'll show you that. So division also we can do, x1 plus I y1, x2 plus I y2. What we do is we take help of rationalization, right? Because I cannot divide these two, because these two are some separate quantities, right? Not that easy to divide. What I can do, I can convert this denominator totally real. How do I do it? So what I do is I multiply and divide by the conjugate of this. What is conjugate? Whenever its imaginary part, the sign changes of the imaginary part, I make the sign of the imaginary part negative. That is the conjugate basically. So this would be x1 plus I y1, x2 minus I y2 divided by x2 plus I y2 into x2 minus I y2. So you will see this will be totally real. This will be basically, if I do x2 into x2, that is x2 square, x2 into I y2, that is minus I y2 x2, and plus I y2 into x2 plus I y2 into x2. So this will be simply cancelled, and then again this multiplied by this, that is minus I square y2 square, and I square is minus 1. So this will be minus 1 of minus, that is x2 square plus y2 square, that is written over here. And the numerator, again you can do the simple multiplication. Don't worry, there is a easier method of dividing two numbers and multiplying two complex numbers when we are converting them into our Euler's format. It is much easier. I'll show you the Euler's format. So let's say if I have a complex number, what will be, like if they're asking you find out z raised to power 4, and z is a complex number, that is the division. So first of all, you simplify this complex number. Okay, you simplify this complex number. How can you simplify this complex number? Simply you can multiply and divide by the complex conjugate. So this will be 7 plus I into 3 minus 4i upon 3 square plus 4 square. So this would be 21 minus 28 I plus 3i minus 4 I square, so plus 4 upon 25. So yeah, that would be, this would be 25 upon that is 1 only. Okay, just give me 1 second. This 4 into I square, yes. Yeah, 1 and minus, yeah, 1 minus I, and I have to raise it to the power of 14. That will be a bit difficult. Like you can convert this into Euler, which I will tell you. Like there is a shortcut method. If I convert this into Euler format is basically r e raised to power j theta. Okay, where r is the magnitude of my complex number and theta is the angle. So what is the magnitude? That is, it is 1 square plus, like it is the imaginary part whole square plus the real part whole square minus 1 whole square, then of course the whole under root. It is similar to the magnitude of a vector, similar to the magnitude of a vector. This will be equals to under root of 2. So your r is under root of 2. What is the theta? Theta would be simply angle. So my x, like in the x, real part is 1 and the imaginary part is minus 1. So I am lying somewhere here. Real part is 1 and imaginary part is minus 1. So angle from the positive x axis would be minus 45, similar to angle in the xy coordinate system. So it will be minus j minus 45 degrees. So if I am raising this to the power of 14, So what will happen is your r will be raised to the power of 14 and your angle will be multiplied by 14. That's it. So theta will become theta into 14. That's it. So r raised to the power of 14 would be, this is 2 raised to the power of half raised to the power of 14, that is 2 raised to the power 7, and there will be some angle involved. Angle would be 45 minus 45 into 14. So minus 45 into 14, let me calculate this value. 45 into 14 plus 360 plus 360, it is 90. Okay, I can convert them into like my own angle, that is e raised to the power j 90, right? So here what happens if it is 90? When is the angle of a complex number 90 plus 90? That means it is lying in the real part, or sorry, imaginary part. So this can be written as only j or I. I or j both are same thing only, and magnitude is 2 raised to the power 7. So this will be your answer. Like, is there any other way? Like, this was using the Euler's method or polar method, which of course I will come to. Don't worry. For the students who already know, they will be understanding what I am talking about. But of course, we can solve using basic as well, right? So first of all, if they're asking you z raised to the power 14, let me simplify this. Z raised to the power 14 is very difficult. Let me find out z square. What is z square? So z square will be 1 minus I whole square. This would be 1 square plus I square minus 2I. So that would be minus 2I. So minus 2I. Now it's a bit simpler. Minus 2I is manageable. So if I do this raised to the power of 7, that will yield me nothing but z raised to the power of 14. So I can do this raised to the power of 7. So this will be minus 2 raised to the power of 7. And okay, minus sign is here. Z minus I, yeah, actually something, this was negative. Plus 360 plus 360, hold on a second. So 45 into 14, just 1 second, plus 720. If I do if I add 360, should not make any difference. It comes out to be plus 90. This also should come out to be plus 90 actually. Okay, yeah, that is fine. Yeah, this is fine. So this is 2 raised to the power 7. So I can break this down, minus 2 raised to the power 7 and I raised to the power 7. Now what is I raised to the power 7? So we know I raised to the power of 8 is 1, correct? Like basically I raised to the power 7 will be minus I. How? So I raised to the power 4 is 1. I raised to the power 5 would be I raised to the power of 6 would be I square, that is minus 1. I raised to the power 7 would be minus I. So I raised to the power 7 would be minus I. So 2 raised to the power minus 2 raised to the power 7 would be minus 1 basically into 2 raised to the power 7. That's it. Into minus I. So this will be 2 raised to the power 7 into I. Correct? And that is what we have derived here as well. 2 raised to the power 7 into I. So there are multiple ways to solve a particular question. So like, I hope you know these basics. If you don't know, just go through this once. Okay. So here we are representing complex number. So complex number will have two axes, right? In real numbers, we can only derive or write the real numbers. An imaginary number line will have imaginary number, right? Real number and imaginary number. Now, complex numbers, like to represent complex numbers are combination of real number and imaginary number. That's why we have two axes. One is the real number and imaginary number. So this plane is called complex plane, sometimes also called as Argand plane. Name is not important. So there are many representation. This representation, whatever we have been studying, this is called as the Cartesian form or the rectangular form, where I can directly see the real and imaginary part. There is another representation that is known as the polar representation. So what is polar representation? This can be written as mod of z cos theta plus I sin theta. What is mod of z? Mod of z would be the magnitude and theta would be the basically angle. So this representation, polar representation, is mod of z theta. That is my complex number representation. In Euler format also sometimes it is written like e raised to power I theta. That is the Euler representation. Okay. So mod of z would be the magnitude, basically magnitude x square plus y square under root, and theta would be the argument, angle from the positive x axis, modulus and argument. So I will show you, like there is a way to find out the angle that I have taught in my network theory AC part. So I will not go through this again. I have already taught how to find out the angle in network theory AC part. So argument, remember always the range of argument would be minus pi to plus pi. It cannot go beyond plus pi and it cannot go below minus pi. The range will be minus pi to plus pi. So like this is given. Find out the principal argument. I am talking about the principal, because angle, right? If let's say I say this angle is 45, someone else can say this angle is 450. He or she is also correct, because if I go beyond another 360 and then again reach the same point, that will be the same point, right? The angle will be 415. Another person can say this angle will be 775 degrees. Okay, 360, this angle will be 775 degrees. So yeah, that's it basically. So yeah, so but we are talking about the principal angle, and principal angle will be the unique angle that will lie between minus pi to plus pi. Okay, minus pi to plus pi. So yeah, so what will be the angle? So let me first locate the point x, I, y. The point is located -1 here and -I, that is here. So what is the angle from the positive x axis? You can show either this angle will be, this angle is 45, it is plus minus 1 here, 45, this angle is 45, right? So this will be 180 plus 45, that is 225, or you can say this angle as well, negative. If you come in the clockwise direction, this would be 180 minus 45, that is negative, because you're coming in the clockwise direction. So minus what do you call 180 minus 45, 135, yes, 135 degrees. So negative 135 is also correct, or you can say positive as well, that is also correct, right? Yeah, both are correct. So yeah, but because if you add 360, this will be the same thing. If you add 360, okay. What about this angle? So here I see that the real part is negative and the imaginary part is positive. So the height is √3 and the base is 1. So if I draw the triangle, what will be this angle? This angle would be basically height upon base tan inverse. So √3 upon 1 tan inverse, that is 60 degrees. So this angle is 60. So from the positive x axis in the anti-clockwise direction, what is the angle? This whole angle would be 180. So 60 minus that would be 120. degrees. And if I find out this angle, yeah, in the clockwise direction, this angle would be 120, 360. So this will be 240 degrees. This would be 240 degrees. So yeah, that is this angle. So that's how you can calculate the, sorry, not plus 240, minus, because I'm going in the clockwise direction. So just be careful. Remember, I'm going in the minus. Now because we are only we have to decode only a single angle, right? Only a single angle, and I have told you that the argument always lies between minus pi to pi. So minus 180 to plus 180. So you will decode only, like, that's why, that is the reason why we make a range, because I want to decode a unique number. So which number is lying between minus 180 to plus 180? This number. So I'll decode this number. So argument of the first complex number would be minus 135. Argument of the second complex number would be plus 120, because my argument, range of argument will always be between minus 180 to plus 180. That will be given to you in the question, but still I'm telling you. Now another property is conjugate. Conjugate is nothing but whenever the imaginary part is negative of the real, negative of the previous part. So I just change the sign of the imaginary part, that's it. I make it negative. Let's say if previously I had a number 3 plus j4, now, or i4, j or I both are same complex numbers. Now the number would be 3 minus i4. Or let's say if I have previously 2 minus I, now the new number conjugate of this complex number would be 2 plus I, that's it. So basically, geometrically, we just form the mirror image about the x-axis. Now there are few properties of complex number. Your z will not be equals to z inverse. Z inverse basically means 1 by z, right? They are both are not same. Z and z inverse are not equal to each other. Okay, one more thing is there. Z into z bar. Z bar is nothing but the conjugate basically. Z bar is represented with the conjugate, would be x square plus y square. How? But this property is a very important property. So z bar is what? Z is what? X plus iy. Z bar would be what? X minus iy. So z into z bar would be x plus iy into x minus iy. So this would be equals to x square plus y square, which is nothing but the magnitude whole square, because magnitude is x square plus y square whole under root. So same thing is here, magnitude whole square. So yeah, that is the thing over here, basically magnitude whole square. If I take the conjugate of conjugate, I will get back the same complex number. Like if I do plus x plus iy, then I take the conjugate, that will become x minus y, then again I take the conjugate. So again I will change the sign. So I get back the same complex number. That is what this third property tells me. So z will be equals to its own conjugate whenever my complex number is purely real. So let's say I have a complex number 2 plus i3. If I take the conjugate, this will be 2 minus i3, and these two are never equal. But let's say I have a complex number that is 2. 2 is also a complex number actually, because its imaginary part is 0. So complex, like real numbers are subset of complex numbers. Imaginary numbers are subset of complex numbers. So let's say z is equals to 2. If I take the conjugate, I don't have any imaginary part. So I will make minus i0. That does not make any difference. So it is 2. So these two numbers are same. So whenever z bar and z are equal, that is z is equal to its own conjugate, that means the number is purely real. Whenever z bar is equals to minus of z, that means the number is purely imaginary. So here I have taken an example, z equals to plus 3i. If I take the conjugate, it is minus 3i. So it is nothing but the negative form of my initial number. So it is purely imaginary. That's it. Okay. So that's it basically. There are a few more properties of complex number. If I add z bar, you can see, go through this. I will not explain every single property. You can go through this. Okay. So pause the video, go through this and try to prove it. If four complex numbers z bar minus 2 real of z bar and 2 minus real of z represent the vertices of a square of side 4 units. Okay. Then mod of z would be, okay, so these 4 represents the vertex of a square with 4 units. So if they represent the vertex of a square with 4 units, that means the distance between 2 points, right, will always be 4. The length will always be 4. Correct? If I subtract two numbers, the distance would always be 4. So let's assume that z is equals to x plus iy, then its z bar would be x minus iy, and if I find out the distance between the two complex numbers, z minus z bar, that will be equals to x will be cancelled. This will be I y, I into 2y. So I is just a complex number. This 2y represents the length of this particular complex number. Length is 2y, that is equals to 4. So y will be equals to 2. I got the value of y. What about the other part? What about x? So for x, I can find out the distance between these two. So what is z bar minus real of z bar? So z bar is x minus iy minus 2 into real of z bar. Real of z bar would be again real of x minus iy, that is x only. So minus 2x. So this will be minus x minus iy, and this will be z, that is x plus iy, and minus 2 real of iy, that is minus x, yeah, minus x plus iy. So again, if I find out the distance, that will just make this 0 actually, but that is not a problem. If I find out the distance between these two, this will be 0, this will be minus 2, why that is also 4 now. This is, so if I find out the distance between this side z bar, or yeah, or let me find out the distance between z and z bar minus 2 real. So if I find out the distance between these two, so iy will be there actually, and this will be 2x plus 2iy. So if I find out the distance magnitude, right, this will be basically yeah. So my iy is 2. So this is 2 actually. So this would be 4. So 2x plus 4i. Okay, I got this number. Now this distance should be a complex number, right? Okay, just hold on. This no, actually, if they're no, if they're, so let me first of all, actually I should have done the drawing. So these are my phone numbers basically. So this will be minus x minus iy, this will be plus x iy, this will be x minus iy, yeah, and this will be minus x minus iy. Sorry, this will be minus x minus 2 real of z, yeah, minus x plus iy. So yeah, if I plot this, right, so where is my x plus iy? Here. Where is my x minus iy? Here. Where is my minus x minus iy? Here. Where is my minus x plus iy? Here. So this is basically my square. This distance is x, this is also x, and this is also y, that is 2y. So overall, right, x would be 2 and y would also be 2. That is my complex number. What are they asking? They're asking then magnitude of z. So my complex number is x2 plus I2 or J2. Magnitude would be 2 square plus 2 square whole under root, that is equals to 2 root 2, that is equals to 2 root 2. So 2 root 2, yes, is your answer. Like you first of all should plot the function and then check what is your x and y, right? Yeah. So there is another form that is known as the Euler's form. So basically your theta would be like a complex number would be represented as r e raised to power I theta, where r is the magnitude of the complex number and this I theta represents the basically e raised to power I theta is nothing but cos theta plus I sin theta. Because you know what is your sin theta? Do you remember the series that I have taught you? Sin theta is e raised to power I theta minus e raised to the power of minus I theta upon 2i, correct? And cos theta is e raised to the power of I theta plus e raised to the power of minus I theta upon 2. So if you multiply by I, right, this will be e raised to the power I theta minus e raised to the power minus I theta by 2. And if we add these two numbers, cos theta plus I sin theta, so this part will be cancelled, this part will be there, that is e raised to the power I theta. So from this actually we get the identity. So finally, if you have understood how this identity is proven, hit a like below. This video is long, so hit a like video if you are still listening and watching the video. Yeah. So yeah, that's the thing basically. So there are few conversions that we can do from polar to Euler. So this is my rectangular or Cartesian representation. Then I can convert this into polar, and polar can be converted into Euler. So then the multiplication is very simple in polar representation. So if I multiply to, like, first of all, if I'm multiplying to complex numbers and then calculating the magnitude, or if I individually calculate the magnitude, both are same thing. How? So if I convert this, so let's say my z1 is r1 e raised to the power I theta 1 and z2 is r2 e raised to the power of I theta 2. So what I can say is z1 into z2. What is z1 into z2? It will be r1 r2 e raised to the power of I theta 1 plus theta 2. Then find out the magnitude. What is the magnitude? R1 R2. And what is this method? So magnitude of z1 is r1, magnitude of z2 is r2, r1 r2. Similarly, you can prove all this, right? Argument. So basically, if I'm multiplying two complex numbers, the angles will be simply added and their magnitudes will be simply multiplied together. So then any question on multiplication and division, you will be able to solve in a single second. Okay, it is very easy. Like here, let's say I have to find out the argument of z1 by z2, where z1 is a complex number, z2 is a complex number. So z1 is like this 5 by root 3 into I, and z2 is 2 by root 3 plus 2i. 2 by root 3 plus 2i. So what is the format? So I can write the complex number format, polar format, sorry, Euler's format. So this magnitude will be 5 square plus 5 root 3 whole square, that is under root 2. So this will be 10. What is the angle? Angle is root 3 by 1 tan inverse, that is 60. And this angle would be, this will be difficult. 2 I can take common, 2 will be there outside, into 1 by root 3, that is, yeah, 1 by 3 plus 1, that is 4 by 3, so 2 by root 3 basically, 2 by root 3. What is the angle? Angle would be, yeah, y upon x, 60. This angle is also 60 only, 60 degrees. So ultimately, right, if I am dividing the two complex numbers, what will happen? The magnitudes will be cancelled. So this will be 10 upon 4, that is 2.5, that is 5 by 2 into root 3. Angle will be subtracted. So their magnitudes will be divided. Magnitude you can do normal operation, division or multiplication, whatever doing. But if I am dividing two complex numbers, their angles will be subtracted. If I am multiplying two complex numbers, their angles will be added. So here I am dividing, so their angles will be subtracted, that is 60 minus 60 would be simply 0. So answer for argument will be 0. If they would have asked you the magnitude would be 5 by 2 root 3. So 5 by root 3, 5 by 2 into root 3, yeah, that is your magnitude. Now there is a theorem called as de Moivre's theorem, which is nothing but the extension of whatever we know. So let's say if I have cos theta plus I sin theta, that I can write as e raised to the power I theta. So if I raise it to the power of m, it is basically e raised to the power of, like, because where, remember, what is the magnitude? 1. So it will be 1 raised to the power of m, and angle will be added. So if I have, let's say, e raised to the power of I theta into 2, that is nothing but e raised to the power I theta into e raised to the power I theta. And I have told you that if I am multiplying two complex numbers, their angles will be added. This is how their angles are added, right? Because their powers are added. These powers are added, right? E raised to the power theta plus theta, I theta plus theta, because I am multiplying. This will be e raised to the power I theta plus 2 theta. This will be basically e raised to the power 2 I theta. That's why their angles are added if I am multiplying. If I am dividing, this will be e raised to the power I theta 1 by e raised to the power of I theta 2. their angles will be simply subtracted. E raised to the power of I theta 1 minus theta 2. Okay. Yeah. Yeah, so here if I'm doing this twice, this becomes e raised to the power 2 I theta. If I did this thrice, this will be e raised to the power 3 I theta. So if I did this m times, this will be e raised to the power m I theta, and then again I can break this down into polar. In polar, this will be cos of m theta plus minus I sin m theta. So that is what your de Moivre's theorem is. So basically this m goes inside, so that is basically the theorem. That's it, nothing special. That's it, that is the theorem. Okay, so I hope you have got the idea. Like there is a question as well. This is the question. So if alpha and beta are roots of this particular equation, then alpha raised to the power of n plus beta raised to the power of n would be equals to what? So alpha and beta are roots. So if alpha and beta are roots, first of all let us discuss what is the root of this quadratic equation. So minus b, there is 2 plus minus b square, let me use a different color, b square minus 4ac, so 4 minus 8 by 2a. So this will be basically 2 or 1 plus minus, yeah, I, 1 plus minus I. So these are my roots. So alpha would be 1 plus I and beta would be 1 minus I. Now what is the answer of alpha raised to the power n plus beta raised to the power m? So what is alpha in, because whenever there is this power term, right, always convert in Euler format. So what is 1 plus I in Euler form? What is the magnitude? Root 2. What is the angle? I pi by 4. Here what is the magnitude? Root 2. What is the angle? Minus I pi by 4. Minus pi by 4. Argument of my complex number. That is the angle. Now if I do alpha raised to the power of n, this will be 2 raised to the power of n by 2 e raised to the power of n pi by 4 plus 2 raised to the power, for the second term beta raised to the power n, this will be n by 2 e raised to the power of I minus n pi by 4. Okay, so I can take 2 raised to the power of n by 2 common. I can take 2 raised to the power of n by 2 common, because I see everywhere there is 2 raised to the power of n by 2. 2 raised to the power n by 2, I have taken it common. This is e raised to the power of n pi by 4 plus e raised to the power of minus n pi by 4. Okay. Now what I can do, I can multiply and divide, because I see there is cos or sine, cos, right? So I can multiply and divide by 2. So this will be nothing but my cos I n pi by 2. That's it. Here, right, I have written what is cos theta. So this is nothing but my cos n pi by 4. So this will be 2 raised to the power of n by 2 plus 1 cos of n pi by 4. That is present in option C. Okay, that's how you can solve these kind of questions. Now there is one more thing, that is cube root of unity. They have not asked from this topic, but they can again ask. Again, cube root of unity is nothing but the root of 1. Okay, cube root of 1. So this, right, z equals to 1 raised to power of 1 by 3. This has 3 solutions. Basically if I cube both sides, my z cube would be equals to 1. Z cube is equals to 1. So z cube minus 1 equal to 0. So there are 3 solutions like this, right? So this is one of the solution, that is z equals to 1. This is definitely one of the solution. Other solution is this one. Solution of this. Solution of this would be, if you find out, this will be the exponentials. Okay. So yeah, these are called as cube root of unity. For those who have studied 11th and 12th, they will remember these things, right? Omega square. There are few properties of cube root of unity. 1 plus omega square will be 0. Omega raised to the power 3 and would be 1, like, because if you raise it this to the power of 3, you will get e raised to the power of I 2 pi, and e raised to the power of I 2 pi is simply 1, because cos of 2 pi is 1 and sine of 2 pi is 0. So 1 plus I 0 is 1. So these are the properties of cube root of unity. Okay, you can go through this. So there is another property, this one is very pretty interesting. They have not asked some questions from cube root of unity, but they can any day they can ask a good question from cube root of unity, okay, or nth root of unity. Till now they have not asked much, but they can definitely, if they want to, they can definitely, because mostly they have asked in Lucas and very simple questions. Okay, they have not asked these kind of things, but if they want to, they can, because these are included in the syllabus. So this is one property, that let's say 1 plus omega square is 0, because uh, omega, okay, like, where is the proof? These are nothing but the sum of the roots of this equation, right? Or if you want the proof, I can prove it as well. So 1 plus e raised to the power of omega is e raised to the power of I 2 pi by 3, I 2 pi by 3 plus e raised to the power of I 4 pi by 3. Or you can simply write this properly, right? So what are your complex numbers? These are my complex numbers. So 1 plus this value plus this value. So minus half will be 1, minus 1. So minus 1 plus 1 will be 0. Then plus I root 3 by 2 minus I root 3 by 2. This will be also cancelled. So ultimately it is 0. So that's why the sum of the roots are always 0. Now there are a few properties like this one. If whenever I am doing this, 1 raised to the power of, let's say, if it's a multiple of 3, if it's like 1 plus omega square plus omega square cube, or not cube, sorry, omega square plus omega square square, this will be always equal to 0. How? So 1 plus omega square, omega raised to the power of 4, what is omega? So omega cube is 1, omega raised to the power 4 would be omega. So this will be simply 1 plus omega square plus omega, and I know 1 plus omega square is 0. So whenever I have this format, and I'm raising all the values omega square and 1 to the power of 1, to the power of common number r, and if r is not a multiple of 3n, if r is not a multiple of 3n, if r is not a multiple of 3n, then this will be simply uh, 0. As you can see, if r is a multiple of 3n, then this will be 3, this will be plus 3. If r is a multiple of 3n, this will be plus 3. How? So let me take the case, if I am doing this 1 cube plus omega raised to the power 3 plus omega square raised to the power of 3, this will be 1 plus omega cube is also 1, correct, and omega square raised to the power 3, that is omega raised to the power 6. So I can write this as omega cube raised to the power whole square, and omega cube is 1, so this will be 3. So that's how you can see, whenever I am raising this to the any power of 3, right? So there is a 3 in power. So whenever there is a 3 in power, then that becomes 1. Omega raised to the power 3n is simply 1. Okay, so this will always be 3 if it is a multiple of 3. Okay, so we can solve a pretty simple question, this one. If I is equals to minus 1, 4 plus this value raised to the power of 3, 3, 4, and this value raised to the power 365. This is what, how can I remember this value? So first of all, you can convert this into, whenever, if you don't remember whether this is omega or what, right, just convert this into exponential. Convert this into exponential. So what is the magnitude? Magnitude is 1 plus 5. And what is the angle? Angle is, its real part is negative, its imaginary part is positive. So I am lying here. So this angle, its real part is minus half and its imaginary part is root 3 by 2. So this will be equals to, this will be equals to y upon x, so root 3, so this is 60 degrees. So yeah, this angle would be 120. So this will be e raised to the power of 2 pi by 3 I plus 3 e raised to the power of I. This will be basically same thing, right? I think, okay, I forgot to oh, this is same thing only. Same number only, right? So this will be e raised to the power of 2 pi by 3 raised to the power of 365, and this is raised to the power of 334. So I will change this to a multiple of 3 actually, that will be easier for me. So this will be 4 plus 5 e raised to the power of I 2 pi. Now this I can write as 333 plus 1. So this will be e raised to the power of 2 pi will be 111, okay, into e raised to the power of I 2 pi by 3, and this also I can write as, okay, e raised to the power of 363 plus 2. So this will be 3 e raised to the power of I 2 pi, 3 is cancelled, 3 is like cancelled, so this will be 121 into e raised to the power of I 2 pi by 3 whole squared. So this would be, now this is what is e raised to the power I 2 pi? It is 1. E raised to the power of I 2 pi is 1. So this will be 4 into 5, 1 raised to the power of 111 into e raised to the power of I 2 pi by 3. Let me keep it as it is for now. Plus 3 e raised to the power, again e raised to the power of I 2 pi is 1. This will be e raised to the power of I 4 pi by 3. That is interesting. 3. So again, like you can break it down. Now you can, whenever there is some addition or subtraction, right, you can break it down into your rectangular format. So this will be 4 plus 5. Now e raised to the power I 2 pi. So cos of 2 pi by 3, that is nothing but minus half plus j or I root 3 by 2. Three e raised to the power of minus half this will be minus I root 3 by 2. Like you can break it down, right? Sin theta plus cos theta. So if I solve this, the real and imaginary part, 4 minus 5 by 2 minus 3 by 2. So this will be minus 8 by 2 minus 4. So that part is gone totally. So 5, yeah, the that part is gone. Okay, there is no real part left. This will be plus I 5 by 2 minus 3 by 2. So 2 by 2, that is, yeah, I root 3. So your answer is simply I root 3, that's it. So without remembering any omega and stuff, we can directly solve. So for addition and subtraction, you will use your Cartesian or rectangular format. For multiplication division, you will use polar or Euler format. Simple as. Now there is another thing known as nth root. So I had cube root, right? So nth root will be, I can replace my I or 1 to be e raised to the power of I 2 pi k. K will be any integer. I raised to the power 2 pi is also 1. I raised to the power of 4 pi is also 1. I raised to the power of 6 pi is also 1. You can put in the calculator. Okay, so nth root will be like, I can divide this by n, there will be n roots. So one root will be surely 1, another root will be I raised to the power 2 pi by n. So let's assume that I am doing cube root, so it will be I raised to the power of 2 pi by 3. Then I will have I raised to the power of 4 pi by 3, right? 3 roots. So for 4 roots, I will have I raised to the power of 1, I will have 1 as the root, another root will be I raised to the power of 2 pi by 4, another root will be I raised to the power of 4 pi by 4, another root will be I raised to the power of 6 pi by 4. Okay, so yeah, that's how the roots are. There are a few properties of nth root, so you can go through, you can watch these things. I will not go through this because there are a lot of things to cover. Okay, so yeah, you can do this simple thing, evaluate 16 raised to the power of 3 by 4. Like, this is a MSQ. Okay, so you will be shocked that you will only answer here the real part, right? 8. What you will do, you will write this 16 as 2 raised to the power of 4, then this is 3 by 4, so this will be 4 will be cancelled, 2 cube, so 2 cube is 8. Yeah, 2 cube is 8, so you will answer 8, but only 8 is not the answer actually, surprisingly. So MSQ can come from this. So always, to be on the safer side, what you do is, whenever these kind of questions are there, right, you have to find out the quad root, fourth root. So you replace your, like, you write 116 as 1 into 16 raised to the power of 3 by 4. Okay, and then you write 1 as e raised to the power of I 2 pi k, where k can be anything from 0, 1, 2, 3 and so on. So there can be more solutions. Okay, so yeah, this will be I e raised to the power of I 2 pi k into 16 raised to the power of 3 by 4. This will be equals to yeah, e raised to the power of I into 3 pi k by 2 into 8. So magnitude will be 8 surely, but this term will be different for different values of k. So for k equal to 0, for k equal to 0, this value will be 8. For k equals to 1, this will be e raised to the power of I 3 pi by 2. So it is e raised to the power of I 270. So I 270, this is 90, 90, 270. So it is minus of I. So minus I into 8. That is also present in the option. So option C is also correct actually. What about the k equals to 2? So k equals to 2, this will be for k equals to 2, this will be e raised to the power of I 3 pi. So this is minus 270, sorry, plus 270, 8 into I 3 pi. So I will be lying 180, 180 and then a 180. So minus 1. So this will be minus 1 into 8, that is minus of 8. So minus 8 is here also, and similarly you will get plus 80 for the last one. Again, if you keep on repeating, if you write k equals to 5, you will get this, like, you will get repeated solutions, like same solutions. You will get whatever you got at k equal to 0. It will just keep on duplicate, like repeat whatever solutions you have got. So you will not, only 4 unique solutions you have. These are my 4 unique solutions: 8, minus 8, plus 8i, minus 8i, because we are taking the fourth root. So just be careful. If I have 5, right, divide by 5, then I will get 5 unique solutions. But of course, they can only frame a MSQ of 4 options. So mostly this kind of questions will be asked. So just be careful, very, very careful. Now we will come to locus. Locus is nothing but plotting of the complex number. So we can do a very simple example. Let's take few questions. Okay, let me first of all plot the locus of this line z equals to x plus iy, where x is varying from minus infinity to plus infinity, y is constant, y equals to b. So if x is varying from minus infinity to plus infinity and y is constant, that is the imaginary part is constant, but x is varying. So if I plot this in the complex plane, I will just get a straight line that is parallel to my x-axis. Similarly, if I say my x is constant and my y is varying from minus infinity to plus infinity, then I will get a like complex number that is just lying here. Okay, that is just lying here. Yes. Now, how to get a rectangle? If let's say your x and y both are varying through fixed limits, right? Then you will get a rectangle. If your magnitude of the complex number is fixed and your theta varies from minus pi to plus pi, then you will get a circle. So plot the locus of the complex number this. Okay, this has already been plotted here. So I don't feel I need to plot. Like basically, right? They're telling you that the complex number z is equals to e raised to power 5 I theta minus I theta, sorry, plus I theta, where your argument of z is varying from 0 to minus pi. So the argument of z angle would be going from 0 to minus pi. So I'll go in the clockwise direction. But its magnitude is fixed. So its radius is fixed everywhere. That is 5. So this will be the complex number basically. Okay, so it is varying from minus pi to theta. So I'll go start from minus pi and then I will end at theta. So that is the complex locus of my complex number. So how to get a disk? So to get a circle, your radius will be fixed. To get a disk, right? Disk means this will be filled. That means your radius will keep on increasing from 0 to it will go to the maximum radius of the disk. And theta of course will rotate throughout. Okay. So like this part is pretty important. How to write the equation of a circle in complex plane? In real axis, you know how to write the equation of a circle. In complex plane, it is even simpler. So in equation of a circle, right, is nothing. Here, this is the equation of a circle basically. What is this? It is just magnitude of my complex number fixed, that is r. This is my equation of a circle. So magnitude of r is fixed, that is nothing but x square plus y square is equals to a square. That is the equation of circle, correct? So this is x square plus y square is nothing but z square, right? That is equals to a square. So what I can do, I can take the under root on both sides. This will be a z equals to a. Okay, so this is magnitude of z whole square equals to a. And magnitude of z is always positive number. So I write this magnitude of z equals to a. That is the equation of a complex equation of a circle whose center is 0. Let's say the circle whose center is non-zero. Then how can I write? So this is how you can write. So it is similar to this, right? Similar to my this coordinate, normal Cartesian coordinate system, x minus x naught whole square plus y minus y naught whole square equals to r square. Similar to that in case of a, if I want to write this equation of a circle in complex number, it will be z minus z naught mod equals to r. Okay, so it is similar to that only. So what is z minus z naught? Z, let's say, is x plus iy. Z naught is, let's say, some x naught minus is there, right? Minus I y naught. It is also a complex number and I am taking the mod, that is equals to r. So this would be x minus x naught plus I y minus y naught mod. That is the modulus, that is r. Modulus means just the magnitude. This will be real part whole square plus the imaginary part whole square equals to under root equals to r. I can square both sides. This will be x minus x naught whole square plus y minus y naught whole square equal to r square. So that's how you can get the equation of a circle. Okay. So if the center is a comma b, right, in complex plane, then you have to do z minus z naught, that is a plus ib. That's it. That is the only difference. Okay. So now what is a complex function? Till now we have been learning about a complex number, a particular point. Complex function consists of variables. Okay. Where both my x and y will vary. That is what my complex. So complex function, there exist 4 variables which are x, y, which are independent, and u, v, which are dependent variables. So u plus iv will be a function of x plus iy. I will show you. So there, I think there are a few examples. Here this. So we have a complex variable w equals to log of z. So w is equals to ln, z is what, x plus iy. So I can further break it. So what is x plus iy? This will be ln of r e raised to the power of I theta, correct? So this is multiplication. So I can break this multiplication into two parts. This will be ln of r plus ln of e raised to the power of I theta. So this is raised to the power of I theta. I theta can come at the coefficient. This will be ln of r plus I theta. Yeah, that's it basically. So that is my complex variable w. So complex variable w is also a function of x and y. X and y are independent variables. W is a dependent variable. That is equals to u plus ib, which is a combination. U is also a function of x and y, and v is also a function of x and y. So these things are different. Okay. So this is my complex function. Complex function is dependent both on x and y. Complex variable is a separate thing. Z equals to x plus y. Complex function is a different thing. So we can break any complex function in terms of u plus iv, where u and v both will be function of my independent variables x and y. Okay, so this is a complex number, this is a complex function w. So they are asking us to plot the complex function if u equals to constant line gets mapped. So u constant, if u is constant, that means this real part is constant, u plus iv real part is constant, that is ln of r is constant, that is r equals to constant. If r is constant, correct, hold on a second, sorry, if u equals to constant line is mapped, yeah, if r is constant, and your yeah, that's it. If r is constant, if this part is constant, this part is variable, theta is variable, what is that in the complex plane? That what will be that? That will be nothing but r is constant. So the distance from the origin is constant, and I'm varying the theta. That is nothing but the equation of a circle. So that's it. That is what they're asking. Okay. Don't be confused if I have plot the UV plane. UV plane is a separate thing. Okay. XY plane is a separate. So XY UV basically means the real part is constant. That is, yes, your U is constant. So in the UV plane, it will be just like a straight line because your U is constant. In the XY plane, because your u is constant, that is your ln r is constant, that is your r is constant, r constant meaning the distance from the origin is constant. In the xy plane, it will be an equation of a circle. I hope you have understood this point. Okay. Yeah, let's solve this question. Like this has recently came in GATE. A point z has been plotted in the complex plane. It is inside the unit circle in the xy plane. The plot of y by z, what will be like, where will the complex number 1 by z lie? So what is 1 by z? I can write z to be magnitude of r into e raised to the power of I theta. So this will be 1 by r into e raised to the power of minus I theta. That I'm just taking the power on the numerator. So what is happening to this complex number y? The magnitude of my complex number y is 1 by r. The angle of my complex number y is minus theta, negative. So if it was lying in the plus theta here, right, let's say this angle was plus 45, now it will lie at minus 45. So I am lying here, possible answer. I am lying here, no, not possible, right? Angle will be absolutely mirror image, right? It will be minus theta. This again not possible. This, yeah, this is possible. So these two are possible. What about the magnitude? So let's say this is a unit circle. If this is a unit circle, this distance will be something less than 1, because it is lying inside the unit circle, because this distance is 1. So let's assume this distance to be 0.8. Now the magnitude of my new complex number is 1 by r. Previously it was r. So 1 by 0.8 is something greater than 1. So I will be lying outside the unit circle, not inside the unit circle. The magnitude will increase. Previously it was less than 1. Now it will be more than 1. So I will be lying outside the unit circle. So option D will be correct. So these kind of basic questions they will ask. Even though if you have no knowledge of complex numbers, still you will be able to solve it. But I have cleared the basics, everything from scratch. So my purpose was to clear everything from scratch, and I have done it. So the basics of complex numbers are done now. So we have solved questions as well. Now we will move on to the complex functions. So let's start with limits. So up until now we have been finding out limits for a single independent variable. The example being, let's say I have this x upon x, x plus 1 upon x minus 1, or sin x upon x. So in each of these cases, I only had a single independent variable, and it was very easy to find out the limit as x tends to 0. Now, what can happen in complex variable? There are two independent variables, x and y. So z will be a function of x and iy. Of course, there will be imaginary part and a real part. So how will I find out the limit for this particular case? So in real variable, we say x is tending to x naught. And in complex variable, we say z is going to z naught, but both x and y will be varied. Here only x will be varied. This is two dimensional, it is one dimensional. So we will see one very basic example. Limit as z tends to 0, z bar by z. So what is z bar? Z bar is x, let's say z, like they should have provided that z is equals to x plus iy. So z bar would be x minus iy. Z bar would be x minus iy. One second. Yeah, z minus iy upon x plus iy, and limit as z tends to 0. That basically means that the real part is also tending to 0, the imaginary part is also tending to 0. So let me put x equal to 0. So this basically means 0 comma 0. Let me put x equal to 0 and y equal to 0. If I put x equal to 0 and y equal to 0, we get a 0 by 0 format. So this is definitely a indeterminate format. So how shall I solve it? So there are many ways of solving limits of two variables. What we can do, first of all, we can put one of the limits. So I say limit as x tends to 0, limit as y tends to 0, x minus iy upon x plus iy. So first of all, I will find out the limit for y, then I will find out the limit for x. So if I do first, if I calculate that limit as y tends to 0, if I do this, so if y is 0, it will be x upon x, limit as x tends to 0, correct? I can assume my x to be very small variable h, so this will come out to be 1. Now I will change the order. This time what I will do is, this time first I will make limit as like last I will make limit y tends to 0. First I will do limit as x tends to 0. So this will be x minus iy upon x plus iy. Now if I make x is going to 0, this will be limit as y tends to 0 minus iy upon plus iy, that is minus 1. So this will be minus 1. So you see, this is the limit L1, this is the limit L2. Both L1 and L2 are not equal to each other, so limit does not exist. So this is one of the way to verify whether your limit exists or not. So first you will make the y 0, then you will make the x 0, or like whatever it is tending to, and then check whether, if I change the order of calculating limit, whether they are equal. If they are equal, then limit can exist. It can exist. If it is in the variable separable format, it can exist, right? You cannot surely say it will exist for sure. It can exist. You have to check, you have to go and check for other paths as well. I will show you a few more examples. So yeah, I will show you one more, this one. So here we have a polynomial and polynomial, and z is tending to I. So what you can do, if your limit is written in terms of z and your numerator denominator is also a polynomial in terms of z, so this is like a single variable only. So you can use your simple L'Hopital's rule. You can use your simple L'Hopital's rule because it's like a single variable only, right? It's not two variables. You can think of it like that, although exactly it is not like that, but you can think of it. So what you can do, first of all, you put z equals to I. If I put z equals to I, the numerator is I square plus 1, that is minus 1 plus 1, that is 0. Numerator is 0. What about the denominator? Denominator would be z cube, that is I cube, that is minus of I plus 2z, that is 2y, minus I into z square plus 2, that is minus 1 plus 2, that is 1. So this will be again 0. So we are getting a 0 by 0 format. So definitely, for sure, I can use the L'Hopital's rule. So if I use the L'Hopital's rule, I can differentiate the numerator, that will be 2z. I can differentiate the denominator, that would be 3z square minus 2 minus I 2z. Okay, then now what I will do, limit as z tends to I. So now I will put I. So numerator is not 0 anymore. What about the denominator? This will be minus 3. This will be plus 2 minus I into 2I. So this would be basically yeah, minus I square, that is plus 4. So that is 2I only. So finally your limit will come out to be 2I. So there is another way to solve it. First, again you do this thing, right? You make like, because your z is tending to I, what is z? Z is equals to x plus iy. So if z is tending to I, that means your x real part is 0 and your imaginary part is tending to 1. So first you do x tending to 0, then you do y tending to 1, and if you solve the limits, you will get the result. You will see that you are getting the same value, that is 2i. So you can do by yourself, you will say you are getting the same value. Now there are, like, now we will officially come to the complex function. A complex function, like, we will come to the continuity of a complex function. A complex function fz is said to be continuous at z naught. Like, we discussed the limit exists at a point, right? We only discussed whether the limit exists at a particular point. Now how can I say whether the function will be continuous or not? The limit has to exist within the given range, similar to the real variable calculus. So a function will be continuous at z equal to z naught. At a particular point it will be continuous if and only if the limit exists of that particular function and it is independent of the path. How do I say it is independent of the path? So what we can do is, do I have any other example? Yeah, this is do I have any other example with the path, because I want to show you the path. So let me take here, anyways limit does not exist. So what you can do is, this is one of the way to solve limits. Another way is to take a path. What do I mean by path? So you about what point you have to find out the limit is 0 comma 0. So I can take a line y equals to x, so that will satisfy 0 comma 0. So if I choose y equals to x, then this function, it gets converted from, if I put my y equals to x, that means this will be x minus ix upon x plus ix. And now if I write limit as x tending to 0, this will be what? This will be 1 minus I, 1 plus I. So this will be the value of limit if I choose this path, y equals to x. Now I can choose another part, y equals to x square, that also will satisfy 0 comma 0. That also will satisfy 0 comma 0. So here yeah, here what we can say is, where did it go? Yeah, so now if I choose this path, then this limit will be converted, x will be x minus y will be x square upon x will be x plus y I x square, limit as x tends to 0. So this will be, if I take x common, x will be cancelled, this will be 1 minus ix, 1 plus ix, limit as x tends to 0. So now if I put x equal to 0, this will be 1, okay, which is different. So my limit is not path independent. From here also you can verify your limit is not path independent. If it is not path independent, then your limit will not exist simply. The limit will not exist. Okay. First thing is, if you are swapping the order of your limit and if both of them are coming same, then limit will definitely exist. Previously if I told you that you cannot say no, you can say limit will definitely exist. Now second, how to check? Secondly, what you can do, you can change the path. You can change the path. So if I change the path, you are seeing that this value will be not 1 definitely. This will be some complex number. I can calculate this number. This will be yeah, 1 minus I whole square upon 2 basically. So 1 minus I whole square would be, this will be 1 plus I square, that is 0, that is 2I. This will be I and this is 1. So it is not path independent, it is path dependent. So if your limit is path dependent, value of the limit, then definitely limit does not exist for this particular function. So definitely at the point 0 comma 0, this function is not continuous. Here limit is existing. If limit exists and if I get a finite value of the limit, then definitely and the value of the function at that particular point is equals to the value of the limit, then definitely function will be continuous. Let's take example, this one. If I take this example, real of z upon z. What is real of z? Real part of z is nothing but x. X upon x plus iy. So check continuity at z equal to 0. So if I put limit at z equal to 0, that is z tends to 0. So this would be that means this is nothing but x comma y tending to 0 comma 0. Okay, so this would be 0. So first of all, what I can do is I can write limit as x tends to 0, limit as y tends to 0. First I will solve this limit, then I will solve the other limit. So this will come out to be, if I put y equal to 0, this will be x by x, that is 1. So this limit comes out to be 1. If I solve it other way around, that is y tending to 0 and limit as x tending to 0, then this will be x upon x plus iy. So if this goes to 0, right, 0 upon 1 plus iy is 0 only. So this comes out to be 0. So of course limit does not exist because this value is not equal. Then limit will not exist. Function will definitely not be continuous. Now how to check differentiability? So for checking differentiability, first of all the function has to be continuous. Also this value has to be finite. Basically it has to have a finite slope, f of z minus z naught upon z minus z naught. This is dy upon dx, similar to that. That is f dash of z naught must be finite and it must exist. Okay, that is the differentiability. Don't worry, you don't have to remember all this because mostly they will not ask you all this. Okay, just like this, check the differentiability of this function fz equal to z. Whenever a function is purely polynomial, it will always be differentiable. We can check the differentiability. So f of z, formula is f of z minus f of z naught upon z naught, sorry, z minus z naught. So z naught is 0 basically. So this will be f of z. F of z is z minus 0 upon z minus 0, that is 1. That is finite. So definitely at limit as z, basically this will be z naught actually. This also will be z naught. Limit as z naught tends to 0. So this will be basically, this is same, right? Numerator, denominator are same. They will be cancelled. So ultimately this will be 1. So yeah, definitely the function is differentiable. Now we will not do all these things. We have a theorem known as analyticity. So with the help of this analytic function, we can directly comment whether my complex function will be differentiable or continuous or not. So what is the definition? A complex function is said to be analytic function at z equal to z naught if it is differentiable at z naught and also differentiable in the neighborhood of z naught. So if I say that the function is analytic, then definitely it will be differentiable at z naught. Okay. Now few important points. If I say a function is differentiable at z naught, can I say it is analytic? No, you cannot say. Because what does analytic say to us? It says that yes, if a function is analytic, then it will be differentiable at z naught as well as in the neighborhood of z naught. But here I am only saying that my function is differentiable at z0. I don't know in the neighborhood of z0 whether it is differentiable or not differentiable. Okay, so that is the thing over here. Now differentiable over if it is differentiable over a region R, then we can definitely say that it is analytic at that region, because analyticity comments about the neighborhood as well. So we have to include the neighborhood. I hope that part is clear. Cauchy-Riemann equations, right? CR equations. So these are the necessary and sufficient conditions that needs to be satisfied if I want to say that whether my function is analytic in the region R or not. So for the function fz, complex function u plus iv, to be analytic in the region R of a z-plane, this CR equations, these are called as my Cauchy-Riemann equations, this has to be satisfied. This you can put it in the short notes and remember. How to remember? So we have f of z equals to u plus iv. So this is the real part, this is the imaginary part. So I will differentiate the real part with respect to the real variable u of x. In short, this is called as u of x. Then I will equate this with the differentiation of the imaginary part with respect to partially differentiating with respect to y with the imaginary variable. This has to be equal one Cauchy-Riemann equation. Another Cauchy-Riemann equation is I have taken ux, so I will choose other one uy. So I have already told you ux equals to vy, so this will be something opposite. So here I will have a negative sign. Uy will be equals to minus of vx. That's it. That's it. That's as simple as it gets. That's how you remember. That's how I remember. You write ux equals to vy. We have already taken that. Then the other equation will be just the opposite. Uy equals to minus. There will be a negative sign, minus of vx. That's it. So here they are telling me that w is a complex analytic function. Which of the following is correct? So ux must be equals to vy if it is analytic, and your uy must be equals to vx. So I ux plus vx will be equals to ui plus I vy. So if I see the imaginary part, ux equals to vy. So that is correct actually. Us, yeah, imaginary parts are equal, ux equals to vy, and here vx equals to ui. No, vx is not equals to ui. Vx is equals to minus ui. So this option is gone. Here I see ux equals to minus of vy. This option is again gone. I will just equate the imaginary parts and the real parts. Here I see that ux is equals to that if I equate the real part equals to vy, correct? Vx equals to minus ui. So this is also correct. So option 3 is definitely correct. Let's read the last one. Ux equals to minus ui. No, this is definitely not correct. Both u will not be there. Both u will not be there. So only option 3 is correct answer for this question. That's how simple it is. Check analyticity for this particular function. How do you check? So you write this. What is fz equal to z square? Z is equals to x plus iy. So I can say this will be x plus iy whole square, that is x square minus y square plus 2y xy plus 2y xy. Okay, that is the thing about analyticity. Yeah, analyticity. So here, what is the real part? Real part is this one, and imaginary part is this one. So what is my u? U is x square minus y square, and what is my v? V is 2xy. So let me first compute ux. Ux would be 2x, partially differentiation with respect to x. And what is vy? Vy is again 2x. So ux equals to vy. That is the first condition for analyticity. Analyticity. So I was just missing the t. That is silent. Analyticity. So next condition is uy. Uy would be minus 2y, and vy is sorry vx is 2y, but negative sign I have to add. So minus 2y is equals to minus 2y. So uy equals to minus vy, that is vx, that is correct again. So definitely this is also satisfying both CR equations. So definitely the function will be analytic. The shortcut is basically any polynomial as a function of z will always be analytic over the entire set. Okay, this equations, wherever CR equations are satisfied, in whatever region CR equations are satisfied, in those regions function will be definitely analytic. Here CR equation is always satisfied, like there is no boundation, and for what values of x, ux will be equals to vy. For any value of x, ux will be equals to vy. For any value of x, ux will be equals to vy. Okay, yeah, that's the thing. Now next is the analyticity test over a open set. So we have this function. So if the ux, uy, vx, vy are continuous over the entire set from x equal to minus infinity to x equal to plus infinity, y equals to minus infinity to y equals to plus infinity, and CR equations are satisfied, then we say the function is always analytic. The function is always analytic. Okay, now sometimes what happens that your ux, uy, vx, vy, of course CR equations will be satisfied, right? CR equation has to be satisfied, that is the first thing. CR equation has to be satisfied, that is the first thing. So yeah, CR equation has to be satisfied, that is the first thing. Here let's say at a point or a range where the ux, uy, vx, vy are all continuous. So in that neighborhood and in the neighborhood of the region, particular region, function will be analytic. First thing is, everywhere I am assuming that CR equations are satisfied. That is the first condition. CR equation must be satisfied. That is the first condition. Now sometimes what happens that CR equations are satisfied only in a particular range, or sometimes ux, uy, vx, vy are not continuous over the entire range, minus infinity to plus infinity for x and y. They are maybe continuous in a particular region. Let's say x equal to minus 2 to x equal to plus 2. After that the function is not continuous. I can take an example. Let's say I calculate ux and it comes out to be 1 by x minus 1. So this function is always continuous except at x equal to 1. So at x equal to 1, definitely I cannot comment whether the function will be analytic or not. So you have to be careful. Whenever you are finding out ux and uy, vx, vy, you check whether your function is continuous or not. Right? If it is not continuous everywhere, then you cannot say that it will be always analytic. Sometimes it will not be analytic, just like here at x equal to 1, this function will not be analytic. Okay, but at other points this will definitely be analytic. Let's take example. Here I have example f of z equal to z into z bar. Z into z bar is nothing but x plus iy into x minus iy. So this would be x square plus y square and minus 2y xy. Will this be analytic? Let me check. This x minus plus y square, yes. So if I find out ux, that is 2x, what is vy? Vy is minus 2x. So this is okay. Hold on a second. Sorry. What am I doing? This will be 0, right? It's imaginary part will be 0. Sorry. Yeah, imaginary part will be 0. So ux is 2x and vy is 0, and uy is 2y and vy is again 0. So this comes out to be 0. So when does my CR equation, like when are my CR equations satisfied? When are my CR equations satisfied? CR equations are satisfied only at point x equal to 0, 0. So what can we deduce? So now this point is very important. Please listen to me carefully. Like whatever I think previously I said something wrong, so I will just correct it. Listen to me very carefully. So if CR equations are only satisfied at a point, then you cannot say that the function will be, obviously function will not be analytic over the entire region. That is gone. You also cannot say that the function will be analytic at x equal to 0, that is origin, x equal to 0, y equal to 0. You cannot also say that, because analyticity is the test for continuity in a given region, in a neighborhood. So only at origin it is satisfying. At x equal to 0.001 it is not satisfying, or y equal to 0.001 it is not satisfying. So function will not be analytic at origin as well. But if CR equations are satisfying at x equal to 0, 0, then you can definitely say function will be differentiable at x equal to 0, 0, x equal to 0, y equal to 0. That is the conclusion. That is the conclusion. Okay, I think here I have mentioned, have I mentioned it? If the function is analytic at origin, it is not, yeah, function is differentiable. So if CR equations, like this point is very, very important, because they will ask you, is the function differentiable or not? So function is differentiable at x equal to 0, y equal to 0, function at origin, function is differentiable. But is the function analytic at origin? No, because in the neighborhood, the CR equation is not getting satisfied. So you cannot say function is analytic. So if a function is analytic at z equal to z0, then CR equation will be satisfied. That is 100% sure. But if CR equation is satisfied at a point, then f of z may or may not be analytic. F of z may or may not be analytic. You cannot say with 100% assurance. So just be careful regarding that. Now, like there are a few definitions of a function which satisfy analyticity. Okay, analyticity. So first one is entire function. If the function is analytic for all real, like, or for all values of z, not real, sorry, for all values of z, that is x is varying from plus infinity to minus infinity, y is also varying from plus infinity to minus infinity, then the function is called as an entire function. All polynomials in z are entire functions. All sinusoids in z are entire functions. All exponential in z are entire functions. All hyperbolic functions, cos hyperbolic of z, sine hyperbolic of z, are entire functions. Okay, so these are few key points of analyticity. So continuity is the necessary condition for differentiability, while differentiability is the necessary condition for analyticity. So if my function is analytic, then function will be definitely differentiable. If my function is differentiable, function will be definitely continuous. If my function is continuous, will the function be differentiable? I don't know. If the function is differentiable, will the function be analytic? I don't know. Okay, so I can go in the reverse manner, but I cannot go in the forward direction. I can go in the reverse direction, but I cannot go in the forward direction. Like this is a very, very beautiful block. So here I have my entire function. So if the limit exists for a function, then the function may or may not be continuous. I don't know. If the function is continuous, then function may be differentiable or may not be differentiable, but limit will exist. If the function is differentiable, then function is analytic or not, I don't know, but definitely it will be continuous. If the function is analytic, definitely it will be differentiable, but I don't know if it will be entire or not, entire function or not. If a function is entire function, then definitely it will be analytic, it will be differentiable, it will be continuous, limit will exist. So this is a very, very important block diagram, or what do you call, Venn diagram kind of thing, so which you can keep it with yourself. Now there is another definition known as harmonic function. A function u of xy, like a function, sorry, w, actually should be w, which satisfy the Laplacian equation, is called harmonic function. So basically Laplacian equation is what? Del square of f. So del square of f is nothing but double derivative with respect to x, double derivative with respect to y, and if it's in the 3 dimension, it will be double derivative with respect to z. So it has to satisfy this Laplacian equation equal to 0, like that is the Laplacian equation, then that function is called as a harmonic function. Okay, basically I will double differentiate that particular function with respect to x, and I will double differentiate that particular function with respect to y, and I will equate it to 0, and that will be my harmonic function. So here we can like do a basic problem. So let u equals to this is a harmonic function, then the value of a and b would be. So if it's a harmonic function, like it has to satisfy this particular equation. So I will double differentiate this with respect to x, This will be, first of all, I will differentiate once with respect to x. This will be 4x cube minus 2 ax y square plus 3bx square minus 3y square. Now if I differentiate this again, this will be 12x square minus 2ay square plus 6bx equal to 0. Now this is the uxx. What is uyy? So uyy would be 4. Let me just first do uy. It will be 4y cube minus 2a x square y 2ax square y minus 6xy. Then if I differentiate this again, this will be 12y 2x square minus 6x. So it is harmonic. If it is harmonic, then this addition should be 0. So 12x square minus 2ay square plus 6bx plus 12y. Hold on a second. This will be y square, right? 12y square minus 2ax square minus 6x equals to 0. So if I see, if I take x square common, that would be 12 minus 2a. If I take y square common, this would be 12 minus 2a again. If I take x common, this will be 6b minus 6. So this has to be 0, right? So this term has to be 0. So a will be 6 and b would be 1. So for a equal to 6 and b equals to 1, it will satisfy for any value of x and y, any real values of x and y, this equation will always be 0. So there are few basic analyticity test of f of z. So here we have like a function fz equals to z bar. So they are asking me in the domain z greater than 0 positive, that is basically mod of z greater than 0. Mod of z greater than 0 means what? Basically, yeah, it includes everything. Mod z greater than 0 means it includes everything that is whose radius, a circle whose radius is greater than 0. So basically it includes all the values. So over the entire range, it is asking me whether the function will be analytic or not. So what is fz equals to z bar? That is fz would be equals to x minus iy. Fz would be equals to x minus iy. So fz is equals to x minus iy. So if I find out what is my ux, ux is 1. What is my vy? Vy is minus 1. So ux is not equals to vy. So definitely function will not be analytic. So first, in the first equation only, CR equation is not getting satisfied. Function is not analytic. I don't care. Domain woman, I don't care. What about the next one? So fz equals to ln of z. Fz is equals to ln of z. Fz equals to ln of z. So if fz is equals to ln of z, so let me first of all convert this. What is z? Z is mod of z, that is r e raised to power I theta. So this I have previously also converted. This will be ln of r plus e raised to power I theta. That will be simply I theta because ln of e is 1. Okay, I can take the power in the coefficient of log. Now what is r? R is x square plus y square raised to the power 1 by 2. So I can take the half outside log. This will be x square plus y square plus I theta. Theta is what? Theta is if okay, domain they have given me mod of z greater than 0. So like there are multiple values of theta. Correct. When both, like let me write, when both x and y both are positive, then your theta will be tan inverse y upon x. Otherwise your theta can be different, because like in different quadrants the value of theta is different. That is what we have learned in network theory. So here theta would be tan inverse y over x. Here theta would be minus tan inverse mod of y over mod of x. Here theta would be 180 minus tan inverse y over x. Here theta would be 180 plus tan inverse mod of y over mod of x. So let me first consider the first quadrant only. So this is my u and this is my v. So if I calculate ux, that would be equals to 2x, 2 will be cancelled. This will be x upon x square plus y square. What about vy? This will be 1 upon 1 plus y by x whole square into y over x. I am differentiating with respect to y, so 1 by x will be there. So actually it is satisfying x upon x square plus y square. Yeah, ux equals to vy. What about the other part? That also will satisfy. But remember, for x greater than 0, y greater than 0, right? This will satisfy. For let's take another case, x less than 0, y less than 0. For that case, here, right, I will have a negative sign, minus tan inverse y over x. Then my vy will be opposite. Vy will be just negative, minus x by x square plus y square. This will not change. Ux will not change, but vy will change. Correct. So yeah, so definitely what you can say is they are not equal. So for x less than 0, y less than 0, the function is not analytic in that region. But for x greater than 0, y greater than 0, it is analytic, except origin, because at origin, uh, yeah, at origin this function, right, tan inverse y upon x is not differentiable. Tan inverse y upon x is not differentiable. So except origin, because this value, what is u at origin? U at origin is ln of 0. Ln of 0 is minus infinity, right? So except origin, the function will be analytic for positive values of x and y. But it is not an entire function, first of all, because for negative values of x and y, right, the CR equations will not be satisfied. And for other values, let's say when my x is positive, y is negative, then also CR equation will not, like it can be and it cannot be. You have to check, but mostly you can check, it will not be satisfied, like it will be 180 minus theta or something. Okay, so it is not an entire function, but definitely it is analytic over a range. So yeah, I hope that part is clear. Now any function which includes z bar, like these are few key points to keep in mind. If a function includes z bar, that function will not be analytic. If fz is purely real or purely imaginary, if it only contains real terms or imaginary terms, then also the function will not be analytic. These are few key points. You can remember it, or you can take help of CR equations and directly prove it by yourself. If u plus iv is analytic and u and v are orthogonal to each other than u and v to each other, then u and v will be harmonic functions. So that is also another definition of u and v. So if they tell you that, if you find out that your function fz is analytic, and if they tell you that your u and v are harmonic with each other, or if they tell you that u and v are harmonic functions, then u and v will be orthogonal with each other. U and v will be orthogonal with each other. So there is a proof, like how this orthogonality is satisfied, but we are not going into it. If the CR equations are basically satisfied, if the CR equations are satisfied, and if the function is harmonic, then we say that u and v are orthogonal to each other. So check whether u and v are harmonic and orthogonal to each other if u plus iv, if fz is equals to u plus iv. Like first thing is, harmonic and analyticity are bit different things. Okay, I will like summarize at the end. Don't worry, there is a summary table here. I will summarize. So if a function is analytic and if the function is harmonic, if both u and v are harmonic, then u and v will be orthogonal to each other. Likewise, if I say if u and v are orthogonal to each other and u and v both are harmonic, then I can say definitely that your function will be analytic. Okay, but like there is a proof, we don't go into that, just basically you understand this. So let us do a basic problem here. So check whether u and v are harmonic and orthogonal to each other if fz is z cube. So if fz is z cube, let me solve this, actually that will be best. Okay, if fz is z cube, that is x plus iy whole cube. So this will be like, if I want to solve this, this will be a bit difficult for me to solve. If I do it like that, r cube, that also will be difficult. Okay, so this will be x cube minus I y cube plus 3i xy into x plus iy. This would be equals to x cube minus I y cube plus I 3x square y minus 3x y square. This will be 3x square y minus y cube. So this will be, if I do ux, if I calculate ux, this would be 3. Like any polynomial in x will always be analytic, right? Will always be analytic. So of course this will be analytic. I don't even have to do all this, right? You can check, but it will be analytic. That I already know. I just need to check whether it is harmonic or not. So checking for harmonic, of course I have to do ux's. So first of all, this will be ux, that will be 3x square minus 3y square, and uxx would be 6x. Uy would be minus 6xy, and uyy would be minus 6x. So uxs plus uyy is equals to 0. So definitely the function is harmonic. Definitely the function is harmonic. What about here? Vx is 6xy and vxx is 6y. Vy equals to 3x square minus 3y square, and vyy is equals to minus 6y. So again vxx plus vyy is equals to 0. So definitely the function will be harmonic. So both u and v are harmonic. I know function is analytic, so definitely it will be orthogonal. Definitely u and v will be orthogonal. So the condition for orthogonality is this: ux into vx equals to minus uy into vy. That is the condition for orthogonality. Okay, like they are harmonic and orthogonality, two different things, but I hope you get the point, right? So there is a proof. I don't want to go into the proof here. Like this is the condition for orthogonality. I don't want to go into the proof. So whatever we have learned about analyticity, we will summarize, and from this only mainly question will be asked. So first thing is CR equation, most important. You have to remember the CR equation. If the CR equation is satisfied, then definitely if the function is analytic, then CR equation will be satisfied. Okay. Also, your Laplacian equation also will be satisfied actually. I have not told this previously. Your Laplacian equation, that is u and v, will be harmonic functions. That also will be satisfied. If a function is analytic, then CR equation will be satisfied. Your Laplacian equation also will be satisfied. That is u and v will be harmonic. And we say u and v to be harmonic conjugate of each other. We say u and v to be harmonic conjugate of each other. Okay, like if function is analytic, u and v, CR equation will be satisfied, u and v will be harmonic functions. Also we say u and v are conjugate harmonic of each other. U is a harmonic function, v is a harmonic function, and if together we make u plus iv and it is analytic, then I can say that u and v will be harmonic conjugate of each other. Also if the function is analytic, I can say that the u and v will represent the, like u and v will be orthogonal to each other. U and v will represent orthogonal to each other. So this is the condition for orthogonality. Previously if I said that they have to be, I think here bit of misprint is there. Like I think I was getting confused with the Laplacian operator. No, Laplacian operator and these are bit different thing. Okay. Yeah. So if a function is analytic, then all these conditions will be satisfied. So make a note of it and remember it. I will provide short notes. There you can remember. This part you can ignore for now. For ESC this is important. Basically, if you have a function where u and like w, that is fz, that is equals to u plus iv, and if that fz is analytic, then another complex function whose real part will be u minus v and whose imaginary part would be u plus v, that also will be analytic. There is a proof. I'm not going into the proof, like I have proven it in my full course, but I'm not going into the proof right now. But this is important in ESC. In GATE they have not asked from this particular topic. So like let's do a question. If w equals to u plus iv is a analytic function, which of the following is slash r correct? Uxx plus uyy equals to vxx plus vy equals to 0, because if it is analytic, then it will be harmonic. If it is analytic, it will be orthogonal. So this condition is also satisfied. Ux equals to minus vy, ux plus vx equal to 0. Yeah, this is also correct because this is nothing but the CR equations. Ux plus vy equal to 0. No, ux equals to minus vy. This is the opposite. It is the opposite. Then here we have this question: if w is an analytic function, then phi z u plus iv will also be analytic if capital U is u minus v and capital V is u plus v. Yeah, this will also be analytic as I have mentioned in the table. Yeah, this also will be, then this also will be analytic, right? M phi. Now if this function is analytic, capital U plus capital V, then this also will be analytic, and similarly this also will be analytic. So I can keep going basically, right? First I said that I have a small function small u plus small v, then u minus v and u plus v, I into u plus v, that also will be analytic. Now capital E and capital V, these are these values. So capital U minus v plus I capital U plus v, that also will be analytic. Similarly I can say r plus is, where r is capital M minus n and I is, sorry, your s is capital M plus s, that also is analytic. So all these functions will be analytic. Okay, so yeah, that's it basically. So now there is one more thing. Now if a function is analytic, then we can find out the real and imaginary parts. I can take an example. So yeah, this is a very long example. Is there, oh no, this is short only. Okay, so here this question we will solve, we'll try to solve. So they have given us that, just give me 1 second. They have told us that my function fz equals to u plus iv is analytic and u is given, the real part of the function is given, then find the harmonic conjugate of u and fz. What is the harmonic conjugate of u? That is basically this v. So there are a few methods. First one is the Milne-Thomson method and second one is the total derivative method. Like just see whichever one is suitable, you use that method, that's it. So in Milne-Thomson method, what we do is first we will write our complex function in terms of z. Okay, if your complex function is given in terms of z, then we will use Milne-Thomson, otherwise we will use total derivative, that is the easier one. Okay, so hold on a second. So what do you know that if the function is harmonic, sorry, if the function is analytic, u plus iv, if the function is analytic, u plus iv, so u is equals to sin x into cos of hy, correct, sin x into cos of hy. Now what can be said? If the function is analytic, then CR equations will be satisfied, ux will be equals to vy and uy will be equals to minus of vx. So we will satisfy the CR equation. That's how simple it is, correct? So if I do ux, because I know u, I will start with u. If I do ux, this will be, I'll differentiate with respect to x. So ux would be cos of x into cos hyperbolic of y. This will be equals to my vy. Vy is what? Vy is del v upon del y. So now we will integrate with respect to y on both sides. So what is the integration of cos hyperbolic of y? Because you will forget this. So let me write the definition of cos hyperbolic of y. So sine hyperbolic of y. What is my sine of y? It is e raised to power of iy minus e raised to power of minus iy upon 2i. Then cos of y. It is e raised to power of iy minus Now what is sine hyperbolic of y? So simply this I part will go away, that's it. It will be purely real. This will be e raised to power y minus e raised to power minus y upon 2. And what would be your cos hyperbolic of y? It will be e raised to power of y minus e raised to power minus y plus e raised to power y. So this will be plus, right? Sorry, plus upon 2. So because you will forget, I know you will forget the differentiation of cos hyperbolic of y. That's why I am telling you all this. So if I differentiate sine hyperbolic of y, so if I differentiate this will be e raised to power y only. This will be plus e raised to power y. This is just a constant. So this is nothing but cos hyperbolic of y. So differentiation of sine hyperbolic of y is cos hyperbolic of y, and differentiation of cos hyperbolic of y, this will be what? This will be e raised to power y. This will be minus e raised to power y. This is nothing but my sine hyperbolic of y. So there is no negative sign here. There is no negative sign. So simply, if I now, because I have to integrate on both sides, cos x is just a constant, I will integrate with respect to y. So I have to integrate cos hyperbolic of y. So if I integrate, it will be nothing but sine hyperbolic of y. So here I will have v will be equals to cos x sine hyperbolic of y plus a constant. Now this constant will be actually a function of y. Sorry, will be actually a function of x. Why? Because here when I'm integrate, right. So if I want to come back to this previous equation, what will I do? So I will differentiate my function with respect to y. So if I differentiate my function with respect to y, then this constant x, right, that is a function of x, will be treated as a constant. That's why I have to write this, because there can be any family of values of x that can always satisfy this equation, right? If I differentiate this with respect to x, this will be anywhere 0. So I have to keep it because this will be used later on. So if I differentiate this with respect to y, this will be 0. Only this will be cos hyperbolic of y, that's it. So we have to write the constant, which is a function of x. So we got this. Now, this is one of the equation. What is the other equation? U of y. What is u of y? I have to differentiate with respect to y. So what is the differentiation of cos hyperbolic of y? That is sine hyperbolic of y. So this will be sine x sine hyperbolic of y, that is equals to that is equals to my minus vx. So minus sign I can take on the other side, vx, that is vx is nothing but dv upon dx. So now if I integrate with respect to x, what is the integration of sin x? Integration of sin x is minus of cos x, and because differentiation of cos x is minus of sin x, correct? So minus will become here, so this will be v, this will become cos x sine hyperbolic of y. Now there will be a constant. This time this constant will be a function of y. This time the function will be a function of y. So from this I can see that this term is matching, right? And here this is the only function of y, and so this function of y will be nothing but this value actually, or no, not this value. So these two are matching, so these are exactly matching, right? So basically whatever I will get, this result and this result must be equal to each other. So if these are equal to each other, so I can say that these two are equal. So cos x sine hyperbolic of y plus c2 of y equals to cos x sine hyperbolic of y plus c1 of x. So ultimately this will be cancelled. So c2 of x will be, c2 of y will be equals to c1 of x. So a constant that is only, this is only a function of x and only a function of y, that is only a function of y, and this constant is only a function of x. These two are equal. That means both of this has to be 0, because that is the only possible condition where if c2 is only function of y, let's say y square plus 2y, and c1 is only function of x, let's say x plus 2. When will this be equal? When these are 0, otherwise they will never be equal. They will never be equal. So they, both of them has to be 0. So ultimately your v comes out to be this value. And of course there will be a constant of integration, like this can be, there will be, like you can write plus c at the end. That constant can be there because you're integrating, but the functions, right, x and y functions, those are sorted. Okay, this is my v. So that's how you solve using total derivative. This was the total derivative method, but you don't have to remember basically, right? You just solve, that's it. You just solve the CR equation. You don't have to remember whether total derivative method or Milne-Thomson method. No, like there are few methods, but just solve using total derivative method. Sometimes what happens in Milne-Thomson, it is easier. It is easier because it consumes less time, but I will recommend, like if you don't want to remember, no need to remember it. Just use this method, that's it. That will be more than enough. Okay, you don't have to worry about anything. Just use CR equations and solve. Use your brain and use CR equations. There are a few questions. You can do this question, try this question. Okay, you can find FZ and U. So I have already solved one question, so I'll not solve everything. So I think now we will like, okay, let us solve this last question, because that will be easier for us. Then we will start with the integral complex integral complex calculus basically. That will be the last topic. After that we will definitely solve the gate. I think, yeah, integral complex calculus and few series are there, Cauchy, all these things are there, and then we will start with the what do you call our questions basically, right? So yeah, let me first solve this. So if this function is analytic and v is given, then find fz. So no need to remember anything, right? No need to remember anything. So this would be, so v is, so if function is analytic, CR equation will be satisfied, that is ux will be equals to minus ux will be equals to vy and uy will be equals to minus of vx. So let me calculate v of y. So what will be v of y? So u of x, that is del u upon del x, would be v of y. If I differentiate this function, differentiate my v with respect to y, that would be 3x square minus 3y square. So now if I integrate this with respect to x, this would be u will be equals to x cube minus 3 y square x plus, of course I will have a constant c1 of y. Now uy will be del u upon del y. If I integrate, if I differentiate my v with respect to x, that would be minus of 6xy. If I integrate this with respect to y, this would be u will be equals to minus of 3xy square plus some constant c2 of x. So if I equate these two, right, I see this c2 of x is nothing but x cube, because this c2 of x is supposed to be only function of x. So it is x cube, and here I am matching, that is minus 3xy square minus 3xy square. So c1 of y will be simply 0, or I can write a constant at the end. So your function fz would be x cube minus 3y square x, or x y square plus I 3 x square y minus y cube plus a constant. So this is your solution, this is you. So do you have to remember anything? Milne-Thomson method, total derivative method? No, nothing. No need to remember anything. Just remember the CR equation and solve the CR equation. That's it. Okay, please go through it by yourself. You will understand. I'm not explaining every single step because this is a rank improvement batch. This is a crash course, right? So go through it, and if you're loving the content, put a like and comment down below, because everywhere else they will tell you the two methods and they will just tell you to mug it up. But here I'm just telling you how to solve the question. That's it, without remembering anything. So now we will start with complex integrations. Yeah, let's begin with integral complex calculus. Let's solve a very basic question, and with that we'll understand how to solve complex integrations. So I have a function fz. I have to integrate with respect to dz, where along the curve y equals to x by 2, where fz is z bar. So let me decode the question. So I have to integrate with respect to dz. What is z? Z is x plus iy. So what would be dz? Dz would be dx plus I dy. So this integration is a similar integration what we have been doing all along. If I break this down, let me break this down. What is fz? Fz is z bar. Z bar is x minus iy. So this integration would be, I will come to the limits just in a second. This will be x minus iy. Just give me 1 second. X minus iy into dx plus I dy. So this can be rewritten like this. 2 plus I will come to the limits. This will be x dx plus y x dx plus y dy plus, I'm just equating the, like I'm taking the real parts together and the imaginary terms together. So yeah, this will be x dy minus y dx. Okay, limits are the same basically, 2 plus I. Now this is my integration. Can you do this integration? Yes. So complex integration is similar to my normal integration only, just here there are imaginary terms. That's the only difference. Now let's come to the limits. So these limits are given. So limits are, let's say z equals to z naught or z1 to z equals to z2. Z1, z is what, x plus iy. Z1 is what, 0, 0. So basically z1 is 0, 0 plus I0. So basically your x naught is 0 and your y naught also is 0. That is your initial point. Final point is 2 plus I. So here x naught is 2 and your y naught is, sorry, y, let's say, let me write this as 1 only, x1 y1, and x2 is 2 and your y2 is 1. So just put the, now you know the limits of x and y. You know this integration. Will you be not be able to solve it? Yes, of course you can. One more thing is there, that regarding this curve, we have to integrate along this curve. Now similar to vector calculus, this integration will be independent of the curve if my function is analytic. Just like in vector calculus we learned, if my vector function is conservative, then that line integration is independent. Similarly here also, if my function is analytic, then this integration will be independent of the path chosen. So I hope you can relate the things. Whatever we are learning with vector calculus, we are relating it with complex variables. So that is the important part that you have to understand. That is why we stressed on analyticity so much. Why is it so important to understand analytic function to solve this integration in a simpler manner? So yeah, for now we know that z bar is not analytic, right? Whenever there is some mod, it is not analytic. So if it is not analytic, definitely we have to choose this path only. We cannot choose any other path. So integration will not be independent of path, it will be dependent of path. So they have given me this path y equals to x by 2. So whenever they will give you some path, it must satisfy the limits. It must satisfy the limits. So if I put x equal to 0, is my y also equal to 0? Yes. If I put my x equal to 2, what is my y? 1, which is exactly whatever I have decoded. So yeah, my limits will always satisfy the given path. Now what you will do, you can simply solve it. Like there are multiple ways to solve it. Either what you do is you write your y in terms of x. So y is x by 2. What will be my dy? Dy would be dx by 2. So I will replace my, wherever I have y, I will replace it with x by 2. So this I can further write, this will be x dx plus y. Y is x by 2 and dy is dx by 2. I will just put the limits of x now because everything has been converted in terms of x. So I'll put the limits of x, that is 0 to 2 plus I, don't forget the I. This will also go from 0 to 2. This will be x into dy. Dy is dx by 2 minus y into dx. Y is x by 2, dx by 2. So this will be simply cancelled. Like this is same, right? This will be 0 only. Now this part, I'm interested in this part. This will be 3 by, sorry, yeah, 1 by 4 x by 4 plus x, that is 5x by 4. So 5 by 4. 5 by 4 x dx. So this will be equals to x square by 2, that is 5 by 8x square, that is 2 square. So this will be 4, so 5 by 2, so 2.5 units. So your answer would be 2.5. Now there is another way, like method 2 is you write x in terms of y. So you replace x in terms of y, you will get the same answer, 5 by 2. That will not make any difference. Okay, so vector function, we know we compute the line integration about the vector function. For complex function, we compute it along the complex plane. Okay, so yeah, these are the differences. So basically here your closed line integration of any vector field was equal to 0 if my vector field was conservative. Here the closed line integration along any curve fz dz will be 0 if the function is analytic. Basically it is entire or within the given region limit, right? The function is analytic. If it is entire function, then you take any path, it will always be 0 obviously. But if it is analytic within a certain region, so in that region if the function is analytic, then definitely this integration, closed line integration, will be simply 0. That is the conclusion. Yeah, so you can solve, there are multiple ways to solve integration. Either if you have given fz dz and your fz is given in terms of z only, so you can directly solve with respect to z. You don't need to solve by putting x and y. You can do it simply. So if they have given you the limits and they have not mentioned you the path, so you have to assume that the function is analytic over the given path. If they have given you the function and if they have given you the limits but they have not mentioned you the path, that means you have to assume that the function is analytic, because this function is not always analytic. It is not analytic at z equals to 0. Correct? So just be careful regarding that. But here we'll assume it to be analytic because they have not given me the path and it will be a NAT type question and they are directly asking you the answer or something, or so you have to assume that the function is analytic. If it is analytic, if the function is analytic, correct, you can simply integrate this with respect to z. How? So this will be 5 to 3i fz. Fz is 1 by z and dz. What is integration of dz by z? Z is just a dummy variable. That will be ln of z. So I will go from 5 to 3i. So this will be ln of 3i minus ln of 5. So this will be equals to ln of 3i by 5. So if I rewrite in terms of real and imaginary parts, correct, so this will be ln of 5. So ln of 3 by 5 plus ln of I. Now what is I? I will be equals to e raised to power I of pi by 2. So that my e and ln can be cancelled and that pi by 2 can come outside. So this will be 0.6 pi by 2, I of pi by 2. So this will be answer for the integration. Okay. Now what you can do, you can again break this down in terms of x and y, 1 by x plus iy. Then you can solve using some path, random path y equal to x, and that will also suffice. But you have to choose the path such that it should satisfy both the upper limit and lower limit. Correct? Yep. So that's how you solve. Now this rectangular transformation we will skip actually. Yeah, because that will be a bit hectic for you to do all that. Yeah, again here if I've been given this fz dz along x equal to t plus 1 and y equals to 2t square minus 1, where fz is z. If the function is analytic, you don't even have to worry x equal to this and y equal to this. You just simply solve the integration, that's it. This will be answer. Even if you solve right along the given path, then also you will arrive at the same answer. So if the function is analytic, because any polynomial will always be analytic, so you don't have to worry about the path. Just simply solve with respect to z. If the function is analytic, this is only valid if the function is analytic, because then the function will be continuous and differentiable throughout. So these are the transformation. Like there are many. This is one of the transformation that we do is polar transformation. Let's take an example. Compute fz dz where c along the curve where C is the upper half of the complex plane mod of z minus 2 equals to 2 in the anti-clockwise direction, where fz is equals to z square. Now this is analytic over the entire region, and they are asking me to calculate the integration about the semicircle given by the complex plane z minus 2 equals to 2. What does it mean? What does it represent actually? So let me decode it. Z is x plus iy. So x plus iy minus 2 mod equals to 2. So this would be x minus 2 whole square plus y square equals to 2 square. I can square it because mod is just under root. So I can square both sides. So this represents a circle whose center is at x equal to 2 and y equal to 0 and whose radius is 2. So the semicircle in the first quadrant would be something like this, anti-clockwise direction, upper half of the complex plane, upper half of the complex plane meaning in the top side basically. So I will go from 2 comma 0 to 0 comma 0. Now how shall I solve it? Yeah, so either if the function is analytic, right, either I can choose the path, I can use some polar transformation, or you can solve it simply as well without, because the function is analytic. So let me first choose the polar transformation. So what kind of polar transformation shall I choose? So I can see that my theta is varying from 0 to pi, but if the center was this arrow, if my center was this arrow, then my theta would be varying from 0 to pi. How can I bring my center to here? So we can do this transformation. Z equals to this z naught plus r e raised to power I theta. So if I use this transformation, this represents a circle. So z equals to r e raised to power I theta represents a circle whose center is at origin and it is whose radius is r. So this would represent a circle whose center is at z naught, whose radius is r. Z naught in our case is actually 1 comma 0. That is our, sorry, is this our z naught? Hold on a second. Center is at 2. Sorry, center is 2. Sorry, this is not, this is 4 comma 0. Sorry about that. This will be 2 comma 0. Yes. Yep. So z naught would be 2 comma 0. It's a complex number whose imaginary part is 0. So I can use this transformation. Z equals to 2 plus, what is the radius of my circle? 2 e raised to power I theta, where my theta is varying from 0 to pi, not 2 pi actually, only the first half. So I can solve this integration now along the given curve. That would be z square. Z square I can replace with 2 plus 2 e raised to power I theta. Now what will be dz? So z is equals to r e raised to power I theta, where r is constant, it is fixed. So this, right, z equal to z naught plus r e raised to power I theta, where your z naught is constant, r is fixed, it is the radius, theta is varying. So if I differentiate with respect to theta, this will be basically r e raised to power I theta. R is just a constant, one I will come outside. If I differentiate with respect to theta, yes, yeah, one I will come outside because I is just a constant. So e raised to power 2x, differentiation with respect to x will be 2 e raised to power 2x. So similarly, just I is just a constant, I can take it outside, theta is the variable. So differentiation of e raised to power I theta with respect to theta would be I into e raised to power I theta. Of course, r is just a constant, it is still there at the outside. So this is my dz, and of course don't forget d theta is here. So I can replace my dz with this value. That would be I r is 2, the radius of the circle is 2, e raised to power I theta d theta. So I can solve this. This would be, if I rearrange, 2, 4 can come outside, 4i. integration 1 plus e raised to power I theta into e raised to power I theta d theta. This would be equals, now theta is varying from 0 to pi. This would be equals to 4i e raised to power I theta plus e raised to power 2 I theta d theta 0 to pi. So if I integrate this thing, this would be 4i, I can take common, this will be e raised to power I theta plus e raised to power 2 I theta by 2. I have taken common outside. Theta is varying from 0 to pi. So e raised to power 2 pi theta is what? 1. It is simply 1. And e raised to power 0 is also 1 only. So this will be simply 0, this integration. What will be this? This will be e raised to power I pi plus 1, sorry, minus 1. E raised to power I pi is minus of 1. Yeah, e raised to power I pi is minus of 1. So this will be equals to minus 1 minus 1 minus 2 minus 2 into 4, that is minus 8. So we get minus 8, but maybe somewhere I'm making a error. That is what I'm thinking. Just give me 1 second. I'm multiplying these values. This, it is z square. Sorry, it is z square, right? It is not simple z. Sorry about that. It is z squared. So yeah, it's not that simple. So first of all, I can take the 2 common. 2. If I take 2 common, 2 square will come outside. So this will be 8i actually. That is one thing. And what will be the square value? Here I will have 8. These all thing will change actually. If I square this, right? If I square this thing, correct? 1 plus e raised to power I theta, that would be 1 plus e raised to power 2 I theta plus 2 e raised to power of I theta. So yeah, and if I multiply this with e raised to power I theta, this will be e raised to power I theta plus e raised to power 3 I theta plus 2 e raised to power 2 I theta. So actually here I will have e raised to power 2 I theta, that will be there with a coefficient of 2, and I will have an additional term, that is e raised to power 3 I theta d theta. So I will have e raised to power 2 I theta with a coefficient of 2, so this will be automatically gone, and this will be plus e raised to power 3 I theta upon 3. I is at the common, 0 to pi. So this term will be again 0. This will be 0, does not matter. This will be minus 2. So here I will have 8 minus 2 plus what will be this term? This will be e raised to power 3 pi. What is e raised to power 3 pi? So I move pi, then pi, another pi. So which is minus 1 only, and that is also minus. So this is minus 2 by 3 basically. So basically how am I calculating? So e raised to power 0 is 1. E raised, if I multiply, if I am shifting by pi, e raised to power pi would be here. I am shifting by pi angle, so that is minus 1. E raised to power minus 2 pi would be again 1, or plus 2 pi would be 1. Again if I shift another pi, that is 3 pi, it will be minus 1 again. So this will be minus 1. This will be minus 1. So that is minus 2 by 3. So this would be minus 6, minus, yeah, 6 minus 8 by 3. So minus 8 into 8, that is 64 by 3. Minus 64 by 3 would be your answer for the question. Now it was so difficult to do this polar transformation and all those things, but I can simply use simply integrate this without doing all this funny business. I can simply integrate because my function is analytic. So if my function is analytic and they are asking me to integrate along the anti-clockwise direction, so what is this value from z equals to what value? Z equals to 4. From z equals to 4, I have to go to z equals to 0. So what I will do is, I don't even need to do all this, right? Yeah, directly I can integrate. This is the one. I am going from z equals to 4 to z equals to 0. So z equals to 4 to z equals to 0. z square dz. It will be z cube by 3, 4 and 0 I'll put in the limit, that will be minus 64 by 3. So I got my answer in seconds, but in transformation it took me so much of brainstorming. So I hope you understand, like if your function is analytic, and most cases they will give you a function such that it is analytic and you will be able to simply solve the question. But one day I am 100% sure they will give you a function such that this function is not analytic. Then you have to go by basics. You will not be able to solve using that property. So in rank improvement batch, in everywhere else, they will teach you only this particular thing. They will not teach you this one, because I teach you, like in our course we teach the difficult things as well, and of course the simple things we'll teach. But I teach you the difficult things because one day in gate examination they will ask a difficult question from that particular topic, and no one else will be able to solve it other than you guys. So that is the advantage that you guys are getting. So now let's come to another topic, that is singular points. This is again very important topic. Questions directly will not be framed from this, but we will use this concept of singular points later. Singular point of a function fz is a point at which the function is not analytic. I hope you remember that we discussed a point 0 0 origin initially, and I told you that at that particular point the function was definitely not analytic. It was continuous, but it was not analytic. So how to find singular points? What in whichever points the CR equations are not satisfied, point where fz is not differentiable, point where f dash of z is not continuous, it is the same thing only, point where your ux, uy, vx, vy are not continuous. Similarly here, find the singular points. Directly, I can directly see that at z equal to 1, I have a singular point. But this is not the actual way to calculate singular point. What you do, we should differentiate our function. If I differentiate our function f dash of z, I see it is minus of z minus 1 whole square. So of course at z equal to 1, the derivative is breaking. So of course z equal to 1 would be a singular point. Now here you cannot directly see what is your singular point. So wherever your derivative goes to infinity, that means basically your function is not differentiable at that particular point, and that will be your singular point. Here directly you cannot say that I have a singular point, because by just observing the function you will say that I don't have a singular point. But if I differentiate the function f dash of this z, that would be 1 by 2 z minus 2 under root. One by 2 under root z minus 2. So the derivative is the derivative is this, and I know at z equal to 2 this function is going to infinity. So definitely z equal to 2 would be a singular point, although directly from the function you cannot observe, but once I do the derivative must be continuous, right? Function must be differentiable. Here again ln z at z equal to 0, I see the function is breaking. So of course function will not be differential. If I differentiate this function, it will be 1 by z, and of course at z equal to 0 the derivative is breaking. So one thing is, few important points. All poles of fz are singular points, but all singular points are not necessarily poles. So what are called poles? The poles of a function are the value of z or x at that particular point where the function goes to infinity. So z equal to 1, here is a pole, and definitely z equals to 1 is a singular point. Here do I have a pole? No, it does not have any denominator, right? It only has numerator. So I don't have any denominator, so I don't have any singular points. Sorry, I don't have any denominator, so I don't have any poles. But if I don't have any poles, will I not have any singular points? No. So that is this statement telling us that all poles of fz, if I have a pole of fz, definitely that will be a singular point, 100%. But if I have a singular point of fz, that may or may not be pole. Similarly here, right, I have a singular point at z equals to 2. But is z equals to 2 a pole? Pole is the value of the function where the function blows up, basically goes to infinity. No. At z equal to 2, I don't have any pole. So there are multiple poles, like there are different types of singular points. One is the isolated singular point, another one is the non-isolated. Isolated meaning which can be separated out and you can tell them they are distinct. I will discuss what is isolated. Non-isolated meaning they are covered in a whole region. We'll discuss about that. Simple pole whose multiplicity is only one. Basically, the poles that are there only once. So here at z equals to 1, I have only a single pole. So this will be a simple pole singular point. Let's say I have a function like z minus 2 whole square. Now I have two poles at z equal to 2 and obviously z equal to 2 will be my singular point. So this z equal to 2 singular point is a repeated pole. Then we have removable pole. We can remove the pole like this. Let's say I have a function z minus 1 or z minus 1 by z square minus 1. So I can definitely see that at z equals to 1 denominator is breaking. But if I observe carefully, z minus 1 and z minus 1 will be cancelled. So this will be z equals to z plus 1. So at z equal to at z equal to plus 1, I have a pole, yes, but that pole is removable. And then ultimately I have a essential pole. It is getting repeated infinite times, which are non-removable, and that is getting repeated infinite times. So I can take a very simple example, e raised to power z. So if I write expand e raised to power z, it is basically, okay, this is not the correct way. E raised to power 1 by z, yeah, that would be 1 plus 1 by z by 1 factorial plus 1 by z whole square by 2 factorial plus 1 by z whole cube by 3 factorial. I see that at z equal to 0, of course I have a pole, and that pole I can never remove, and that is a repeated pole infinite, like this series is an infinite series. So these are called as essential singular pole. What are isolated poles? These are my isolated poles. Z equals to minus 1, z equals to plus 1. I see both of them have a defined region and they are not touching each other. What are non-isolated poles? Let me find non-isolated poles. Do I have any non-isolated poles? Yeah, let me go to this example here. So there exists large number of singularity points at the neighborhood of the singularity point. So tan pi by z. If I say tan pi by z, how many singularity points I have? Tan pi by z can be written in terms of sin pi by z by cos pi by z. So cos pi, like whenever this goes to 0, that will be my singularity point. So cos pi by z equal to 0, it goes to 0 at 2n plus 1 pi by 2. So when my pi by z will be 2n plus 1 pi by 2, this term will go to 0. So from this I get the value of z, z is equals to 2 by n plus 1, where n is integer. So you can see, if I put n equals to 1, z is 2 by 3. If I put n equals to 2, z will be 2 by 5. You can put all these values, you will see this function is blowing up basically. If I put z equals to 2 by 7, it is 2 by, sorry, if I put n equals to 3, it is 2 by 7. So I have a lot of poles near z equal to 0, lot of poles. So I make a circle of radius 0, like almost radius 0, epsilon, whose radius is almost tending to 0. So I have a lot of poles here. So these are non-isolated, these are like together, clubbed together. So that's why these are called non-isolated, because they are in the near neighborhood. So that is what we mean by non-isolated poles. So there are a few questions. Let me show you. I have already explained repeated poles, all those things. So comment about the nature of singularity of fz. So is this a repeated pole? Do I have repeated pole? Do I have repeated singularity point? Do I have non-essential singularity point? Or if it is repeated, what is the multiplicity? Like how many times is the pole repeated? Or if it's a simple pole, or it's a non-isolated or a isolated pole. So pause the video and try to solve it. Now I will solve. So I will first of all write my e raised to power z in terms of series. So e raised to power z would be z 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial plus z raised to power 4 by 4 factorial and so on. I'm dividing and I'm dividing by z cube. So that would be 1 by z cube, 1 by z cube plus 1 by z square plus 1 by 2 factorial into z plus 1 by 3 factorial, and now I don't have any poles. This will be z upon 4 factorial and so on. So I see I have poles that is repeated at z equal to 0, and I will choose obviously the maximum highest order term, because if I club these terms together, what will I get? If I club these terms together, this will be z cube, this will be 1 plus z plus 1 by 2 z square. If I club all these three terms together, all of them have pole at z equal to 0. So of course, we will always choose the maximum order of the denominator. So I have a repeated singularity pole at z equal to 0 of multiplicity 3. Repeated singular pole of multiplicity 3. That is the nature of my pole. So I hope that this part is clear. I hope we have discussed. So let's solve few more questions regarding the nature and location of my singularity point. So here, what are the location of my singularity points? So here if I see at z equal to 0, I have a singularity point. Z equals to plus 1, I have a singularity point. Z equals to minus 1, also I have a singularity point. So mostly, yes, you are correct. Here, most cases, right, by directly seeing the function, and whenever the function is going to infinity, basically at the poles, you will comment about the singularity points. But there will be 1-2 cases where you are not able to observe the rational version of the function, where you are not able to see do I have a poles or not. Sometimes, like how to observe. So whenever you are directly seeing the poles, so the poles will be directly your singularity points. Sometimes in the function will not have any poles. In those cases, just be careful, be attentive, and then you differentiate the function and then check the poles of the derivatives. So what did I say? If you're directly by observing the function, you're able to observe the poles, then you directly comment where are my singularity points. But if I see the function and I don't observe any pole, because here I'm not able to see any pole, so now I will differentiate my function. So that is the next step. But most cases in gate examination, what will happen is they will give you the simple examples where you don't have to differentiate directly. By just by seeing fz, you can comment what kind of singularity point you have and what are the locations of my singularity point. So here if I see the locations of my singularity point are at z equal to 0, z equals to minus 1 and z equals to plus 1. These are my locations of my singularity point, and these are all simple pole. Here if I see at z equal to 0, I have definitely a pole. At z equal to 0, I have pole. At z equal to 2 pi, I have pole. At z equal to 4 pi, I have pole. At z equal to actually pi also, I have a pole. 2 pi, 3 pi, 4 pi, and so on. So z equals to n pi, where n is any integer, I have poles. So all these are simple poles only. Of course, I have minus, like it can be minus pi as well, right? Minus pi, minus 2 pi. So all these are simple poles. All these are simple poles. Although I have infinite number of poles, but all these are simple poles. So yeah, these are all simple poles. What about this one? This one is pretty interesting. Whenever this denominator goes to 0, that would be my location of poles. So sec x will be equals to cos x. When does it happen basically? So basically cosec x, when your cos x is equals to sin x. So cos x equals to sin x, so x would be n pi by 4, where n is belonging to an integer. Okay, not n pi by 4 actually, sorry, n pi by 4 plus pi, because minus 1 also will be correct, right? Whenever your like x will be equals to pi by 4, that is a valid point, that is the first valid point. Then if again it will be 3 pi by 4, in 3 pi by 4 both your sec x and your cosec x is -1, that is also valid. Again in 5 pi by 4, that is also valid, right? In 3 pi by 4 is it valid? In 3 pi by 4, what is your, just give me 1 second. So I have my cos sine here, so pi by 4 cos x is plus, and yeah, sin x is plus. If I shift here another pi, that would be okay, so not 3 pi, not 3 pi by 4, sorry, because what is 135, 3 pi by 4 would be pi, if I add pi by 2, so I'm shifting by 90 degrees. That also would be, no, that is not correct actually, because the ratio would be different. Just give me 1 second. Wherever your tan x is equals to 1, whenever your tan x is equals to 1, when is your tan x 1? Tan x is 1 at every pi by 4, then if I add another pi, then again it will be 1, right? Because yeah, if I just like, I also forget the trigonometry. So pi tan of, so pi 3 pi by 4, 3 pi by 4 would be 135, yes, 135 tan minus 1, yeah, it is tan is negative in 135, tan is positive in, I guess, 225, yes. So pi by 4, 5 pi by 4, then again minus 3 pi by 4, so basically at every pi by 4 plus n pi, where n is belonging to any integer. So again these are all simple poles. So although it seems like I have essential pole and these fancy terms, but mostly these are all simple poles. So now we will discuss a bit about Taylor series, which we have already discussed in the integral calculus portion. So Taylor series, the definition is the Taylor series of an analytic function expanded about z equal to z naught is the same formula what we already know. It is the Taylor series expanded about x equal to a. Same formula, right? Nothing different, no difference is there. Just one thing is important here. The coefficient of the term z minus z naught raised to the power of n. That part is important. So yeah, we will discuss about that. For now, let's basically do a very basic question. We have to calculate the Taylor series. So one more thing, few important points are there. If fz is analytic inside a circle with center z equal to z naught, then for all z inside C we can write Taylor series. So Taylor series can be written if the function is analytic. Taylor series can't be expanded around a singular point. We cannot expand the Taylor series around a singular point because of course we are differentiating the function, right? So derivative won't exist. So how can you write the Taylor series? And Taylor series only contains the positive power of z minus z naught. Here I have z minus z naught raised to the power of 2 and so on. So let's solve it for this. Let's compute the Taylor series expansion of 1 by z plus 4 at z equal to 2. So how to solve? Like same formula, right? So I will write f of z naught, that is f of 2, plus z minus 2 into f dash of z naught, that is f dash of 2 upon 1 factorial, plus z minus z naught whole square, that is z minus 2 whole square, into f double dash of 2 upon 2 factorial, and so on and so on. So here what I can comment on, so I can find out what is my f dash of z. F dash of z would be simply minus 1 by z plus 4 whole square. I can put the value of 2, that will be minus 1 by 36, and this would be 2 by z plus 4 whole cube. So if I solve all this, so this will be the expression basically. This will be the expression, okay, and this will go on basically. This will go on. Now what am I doing here? Yeah, so I'm just doing reverse Taylor expansion. So you can see how am I writing the expression in Taylor expansion. Now we will actually come to a conclusion, or like uh, we'll come to a conclusion. So before that, let's understand what is Lorentz series expansion. What is Lorentz series expansion? So Lorentz series expansion is basically let fz be a complex function which needs to be expanded at z equal to z naught if fz is analytic in the annulus region A. So this region is my region A, that where it is analytic. Basically it is like my z minus z naught, the radius of the complex plane is greater than r1, that this is my r1, and it is less than r2. So in this region the function is analytic. Then for all z in the region R, this region R is this whole region, this whole region, I can write my function fz as a sum of two parts, because at z equal to z naught, let's say the function is not analytic. At z equal to z naught, the function is not analytic, so I cannot write my Taylor series expansion. So we take help of the Lorentz series. So we write our function as a sum of two parts. One is the analytic part, which is totally valid. Another one is the non-analytic part, which is nothing but the reverse power. That's it. So how to write? I will show you one example. So here, okay, let me show you. Yeah, here. So if I show you this, what are the singular points? So at z equal to 0, I definitely see I have a pole. So if I replace my cosec of z, right, with a proper function, this will be 1 by z sine of z. So basically I have a pole, I have a repeated pole at z equal to 0 definitely of multiplicity 2, multiplicity factor 2. And also I have poles at z equals to n pi, where n is any integer, positive or negative. So here, right, you can break this down. Now this will be a bit difficult, just follow along, just follow along. So I will have 1 by z, sin z can be represented like this. It will be z minus z cube by 3 factorial plus z raised to power 5 by 5 factorial minus z raised to power 7 by 7 factorial, and so on. Correct? So actually I will do one thing. Sorry, this is yeah, 1 by sin z. Yes. Yeah. Now what I can do is I can take z common, because I know at z equal to 2 I have a repeated pole, so I can take that repeated pole common. So z square I will have, this will be 1 minus z cube by 3 factorial plus z not cube, sorry, 4 2 by 3 factorial 4 by 5 factorial minus z raised to the power 6 by 7 factorial, and so on. Now I can write all this as x, because all these are not actually to be precise contributing to my pole at z equals to 0. So this will be z square 1 minus capital X, or I can write this to be 1 by z square into 1 minus x inverse. So this would be equals to now we can do the series expansion. So for the students who know, this will be good. If you don't know, then now you know. So there is an expansion formula basically. So my expansion is this 1 by z square into 1 minus x raised to the power of minus 1, that will be equals to 1 by z square. This will be 1 plus x minus x square divided by 2 factorial plus x divided by 3 factorial, and so on. Sorry, not factorial will not be there, right? 1 plus sorry, for negative terms, this will be plus actually. So basically your formula is this 1 plus x, if I take the inverse, correct, this will be 1 minus x plus x square minus x cube plus x raised to power 4 and so on. So if I replace this x with minus x, so this simply x will be replaced with minus x, so this will be plus x, this will be minus x whole square is plus x whole square, same only, this will be plus x cube and so on. So that's how the series is. I think I have mentioned about this series in the integrals calculus portion. So on. Out of this, what is my interest? So basically the rest, now we got the location of the pole and this is my Lorentz series. Okay, Lorentz series. So without even knowing Lorentz series, you have to just do a bit of theorem. Don't worry, like we'll learn more about Lorentz series. So this will be 1 by z square. And what is x? X is nothing but like 1 minus z square by 3 factorial plus z raised to the power 4 by 5 factorial minus z raised to the power 6 by 5 factorial. So this will be what my like x is, right? So 1 plus x divided by this, x is this value, right? This is my x. So if I divide 1 plus, this is 1 x by z square, so x is this value, that is minus z square divided by 3 factorial. Other terms are not of my concern. Why? Other terms are not of my concern because here I see that if I divide this by z square, only this term is the problematic, like this term is the term which has no z. Other terms are like I have z at the numerator, I don't have z in the denominator, so they are of not my concern. So basically, right, one more thing, what is the residue? Residue is the coefficient of the pole at my singularity point. So basically, what is my pole? My pole is z equal to 0. So residue would be the coefficient of my pole, that is 1 by z. So at z equal to 0, I have a simple pole, like I have repeated pole, right? Z equal to 0, I have a repeated pole. So residue would be coefficient of this 1 by z square. What is the coefficient of 1 by z square? That is 1. So that is my residue. Residue will be used later on. So like this is the first one, is the toughest example. I took the toughest example. Let me choose bit simple example. So one more thing, I just told you a wrong thing. So if I see that I have a pole at z equal to 0 here. That is for certain. I have a pole at z equal to 0. So your residue, like I have not come, what is the residue? Residue, I think here, the residue will be the coefficient of that particular term at that particular pole. So if let's say I have a singularity point at z equal to 0, the residue would be, I don't care if it is a repeated, if it's an essential pole, I don't care what kind of, if it's a simple pole, the residue would be the coefficient of 1 by z term in the expansion of Lorentz series. So here I just told you one thing wrong. Here, what is the expansion of my Lorentz series? This was the expansion, correct? So in the expansion, if I see in the expansion, what is the coefficient of 1 by z term? Because after this, like this will be plus x square will be even more higher order. So there I will never get a 1 by z term. So 1 by z term is not present here. 1 by z term is also not present here. This is 1 by 6. This is 1 by z square minus 1 by 6. So 1 by z term is not present everywhere. So basically it is 0 into 1 by z. So the residue for this particular function is 0 at z equal to 0. Similarly, like I will take a simpler example, this one, sin z upon z. So I see that what kind of pole I have? I have a repeated pole. What is the order? You will say repeated pole with order 4. I will say you're wrong, because one of the pole is removable. One of the pole is removable. How? So if I expand this about the Lorentz series, or sorry, if I just expand the sin z function, that is z minus z cube by 3 factorial plus z square by 5 factorial minus z, sorry, not z square, sorry, z raised to power 5 by 5 factorial minus z raised to the power 7 by 7 factorial and so on. This divided by just give me 1 second. This divided by z raised to power 4. So you see one z is automatically getting cancelled. So actually in reality I have only 3 poles at z equal to 0. So it does not matter. Once I will expand this function, I will get this will be 1 minus 1 by z 3 factorial plus z square, sorry, z divided by 5 factorial, and it will go on. What I'm concerned is the residue. Residue would be, because I have a pole at z equal to 0, so I need to find out the coefficient of 1 by z. What is the coefficient? This is my coefficient, right? 1 by z is this, and coefficient of 1 by z is this, 1 by 3 factorial, that is minus 1 by 6. So the residue of this particular function would be minus 1 by 6, as I have done over here. If you see, I have done over here minus 1 by 6. You can see, like, I have done it properly here. So you can see. Similarly, if I take this sin z upon z, what is the singularity point? Z equal to 0. Z equal to 0 is definitely a singularity point. Okay, z equal to 0 is definitely a singularity point. That is for certain. But if it is it a removable type? Yes, it's a removable type singularity point. So again, if I expand, because sin z, if I put limit as z tends to 0, then sin z upon z is simply 1. So it's a removable type. But if I expand my Lorentz series, this will be again z minus z cube by 3 factorial plus z raised to power 5 by 5 factorial, and it will go on. I will divide this by z, so I will get 1 minus z square by 3 factorial and higher powers of z. So nowhere I am getting a 1 by z term. So residue is simply 0. That is what I have done over here. Residue is simply 0, and it's a removable type singularity point. This one, last one, is very interesting. This one, z square e raised to power 1 by z. So expansion of e raised to power 1 by z will be this, 1 by z 1 factorial, 1 by z square 2 factorial, 1 by z cube 3 factorial, and so on. Now I will multiply z square. If I multiply z square, this will be z square plus z plus 1 by 2 plus 1 by 6z. Now again, what is my singularity point? The singularity point would be whenever my function is blowing up. So at z equal to 0, this will be e raised to power infinity, and e raised to power infinity is a very large number. So like I see, like at z equal to 0 something is happening. So of course z equal to 0 would be a singularity point. How can you further understand? So you can differentiate this function, right? If I find out the derivative of this function, I will see this will be 2z e raised to power 1 by z. Anyways, at z equal to 0, this function is not continuous. That is the first thing. And if you find out the derivative, you will see this will be minus 1 by z square into e raised to power 1 by z. Okay, z square is getting cancelled. Yeah, this will be 2z minus 1 into e raised to power 1 by z. Again, if you see, if you put z equal to 0 here, right? If you put z equal to 0, this part is what? Minus 1. So minus 1 into e raised to power infinity, that is infinity. So your derivative is blowing up. So whenever your derivative is blowing up, that means that point is my singularity point. So z equal to 0 would be singularity point. So now if I distribute this series, I will see that I have z square z, then 1 by 2 plus 1 by 6z. So basically after this, what will happen? I will have 1 by 3 factorial into z, z 1 by 4 factorial into z square, and so on. But what is the residue? Residue will be just the coefficient of 1 by z term. Coefficient of 1 by z term is 1 by 6. That's it. You don't have to consider the other terms, 1 by z square, 1 by z cubes, 1 by z raised to power 4. I was wrong previously. Just you have to consider 1 by z. So at z equal to 0, I have pole. So you will consider just 1 by z. You will not consider 1 by z square, 1 by z cube, 1 by z raised to power 4. So Lorentz series, right, mostly you will use some technique, like these kind of techniques, like series. Remember the series of sin x, remember the series of cos x, remember series of expansion, remember this expansion, 1 plus x raised to the power of minus 1. So these things you remember, that should be enough. No need to go through all this, right? These are not that important. Just understand how to calculate the residue. Yeah, we have another, this log you can ignore, because I like there is a series of log as well. You can ignore the log. Okay, don't need to remember, because I'm expecting they will not ask you series question from log. Okay, they will not go into that depth. So these are the functions where your function was not rational, it was something weird, trigonometric or exponential. But if I have rational function, then there is a very easy, simple step to calculate the residue. If I have rational function, then you have to check whether your poles are repeated or simple poles. If you have let's say I have a function like this. So these are all weird functions, right? Sin z upon z, or sin z upon z raised to power 4, cos x z upon z, sin z upon z. So these are a bit weird. Okay, not exactly rational. So I have trigonometric functions, I have exponential. Whenever you have only polynomials, you have polynomial over polynomial. Both your numerator and denominator are polynomial, like z square plus 1 upon z minus 1, like this. Then you have a very simple step. Yeah, sorry for the interruption. Actually, there was a bit of work going on, so I had to pause the video. As I was saying that there are two ways to solve for residue, and residue is very important. Okay, finding out the residue is very important. So first we learned about singularity points. Then we discussed about type of singularity points, poles. Now we are discussing about residue. To compute residue, you can compute the residue with the help of Lorentz series or with the help of this method that I will teach you right now. Okay, this method is also valid. Mostly we use it for these kind of functions, polynomial over polynomial, and Lorentz series we will use for these kind of functions, sin z upon z or these kind of functions. But we can also use this method that I will teach you to calculate the residue here as well. That is also possible, but mostly we'll use whenever there is some nz upon dz, this kind of format. Sometimes like Lorentz series is always valid, but sometimes what happens, finding out the Lorentz series, like in this case ln z, right, is very difficult. So in those kind of cases we have to use this method. What is the method? Here in this case you have to identify the nature of the pole. So previously in case of Lorentz series, if I have got a singularity point, it does not matter whether it's repeated or it's simple, it's essential. The coefficient of that particular term, that is 1 by z minus z naught. If let's say z naught is 1, singularity point is at z equals to 1, z minus 1, that would be my coefficient, would be my singularity point. Yeah, sorry, I had a bit of throat issue. So that is very simple. It does not matter if it's repeated, singularity does not matter for Lorentz series. But for this method, right, it will matter. So let's first discuss about simple poles. So these are all simple poles. So let's find out the residue for these poles. Either you can use Lorentz series or you can use your normal method. What is the normal method? If I have a simple pole, what you will do is you will first of all multiply. So your residue would be residue of f of z at that particular point z equal to z naught. Let's say at z equal to 2, because at z equal to 2 I have a singularity point. So what I will do, I'll multiply by z minus z naught. That is, I'll multiply by z minus 2 with my fz. Then I will differentiate my function with respect to z. Then I will put the value of z equals to 2. So this will be 3z square, and I will put the z equal to 2. So my residue would be 12. That is my residue. Hold on a second. Sorry. I will not differentiate, right? No, we don't differentiate. We differentiate for repeated poles. Yeah, whatever. No, sorry. We'll not differentiate. We'll just multiply by z minus z naught, that is z minus 2, and then I will put the value of 2. Sorry, we'll not differentiate. Differentiation will come in the next method. Sorry about that. Yeah, z cube, and I will put z equal to 2. This will be 8. So 8 is the residue. So let us try to find it using Lorentz series. So again, using Lorentz series, if I try to find it, this is z cube. So where is the pole? Pole is at z equals to 2. So the coefficient of z minus 2 would be my residue. The coefficient of z minus 2 would be my residue. So what is the coefficient of z minus 2? It is z cube. So you put the value of z equals to 2 here, that is 8. So that's how simple it is. Correct? So you just put the value of z equal to 0, that's it. Okay. So yeah, let's solve it for this one. So here, what will be my residue? I have poles, singularity points at z equal to 1, z equal to 2, z equal to 3. So the residue at z equal to 1 would be residue of fz at z equal to 1 would be, first I will multiply by that term, that is z minus 1, with fz. Fz is z upon z minus 1 into z minus 2 into z minus 3. So z minus 1 will be cancelled. So this will be equals to z upon z minus 2 into z minus 3. So this will be equals to Yeah, now we put the value of z equals to 1. If I put z equals to 1, that will be basically minus 1 into minus 1 into minus 2, that is 2. So 1 by 2. That is the residue. Simply you can find out. Lorentz series also is the same only, right? So what is the coefficient of 1 by z minus 1? It is z upon z minus 2 into z minus 3. For simple pole, Lorentz series and this is same. Very easy. But the problem will come for repeated poles. The problem will come for repeated poles. So yeah, I will come to the repeated poles part. So if I show you here, okay, this is also sim chord z. Chord z, what are my residues? So I can break my chord z as cos z upon sin z. So when does my sin z go to 0? At z equals to n pi, and all of them are basically uh, isolated. So yeah, what I can do is I can multiply by the residue. I can multiply by the residue basically. So yeah, so I have to multiply by z minus z naught. So at, let's say I have a pole at z equal to 0, at z equal to pi, z equal to 2 pi. So I will multiply by what? What will be my residue at z equal to 0? What will be the residue of my function at z equal to 0? So I will multiply by z minus 0 with the function into fz. Fz is cos z upon sin z. So now this will be z upon sin z cos z. So now I will do z equal to 0. I cannot simply do z equal to 0. I will use help of limit. Actually here, right, also I should, like, proper formula is limit. There is limit actually. Previously I did not mention that this should be limit, but I was skipping few things because this is rank improvement. So limit is there. Limit as z tends to the particular pole, that is z equal to 2. So limit will be there. Okay. So limit as z tends to 0. So if I do limit as z tends to 0, what is sin z, x upon x or sin z upon z? It is 1. And what is cos z? If z tends to 0, it is 1. So this will be simply 1. Residue will be 1 always. So you can check for other poles as well. For pi to pi, you will see that residue is coming out to be 1. Okay, this was for a simple pole case where pole is not repeated. But now if my poles are repeated, then, like, this is some weird formula. I'll break it down. So mostly, maximum what they will do, they will ask you a pole that is repeated twice. That is the maximum they can ask you. That is my guess. If they ask beyond that, then the question will be very lengthy because you will have to differentiate more than that. So basically, if my pole is repeated twice, then I will differentiate my function once. What do I mean by it? So the formula remains the same. So I have a pole, like I have a simple pole at z equal to 3. That is very easy to calculate. But at z equal to 1, I have a repeated pole. So which is repeated twice. So what I have to do, I have to multiply by the z minus z naught, that z minus 1, with the fz, that is z cube upon z minus 1 whole square into z minus 2 into z minus 3. And I have to multiply by the like same amount of time, same amount of product, z minus 1 whole square. Okay. Now I will multiply by this z minus 1 whole square. Then I will differentiate my function. Then I will put limit as z tends to 2. Okay, that is the difference here. So here this will be z cube upon z minus 2. So I can yeah, let me write this properly. This will be z square minus 5z plus 6. I will differentiate this function ddz. Then I will put this limit as z tends to 2. Same thing I am doing. Actually, this is only for z equal to 3, z equal to 2. I am not calculating. So this will be, if I differentiate this function, this will be yeah, pretty difficult. So let me differentiate. This will be 3z square into the following z square minus 5z plus 6. Now here I will have minus this will be z cube into the differentiation of the denominator, that is 2z minus 5 upon z square minus 5z plus 6 whole square. So now I will put z equal to 2. If I put z equal to 2, this value would be like this is the same value that I have calculated here. So if you put z equal to 2, you will get e residue to be 9 by 4. That's how you calculate basically. That's how you calculate. So if you want to use your Lorentz series, will be a bit difficult. It will be a bit difficult to solve using Lorentz series. That's why you have to use this method. And mostly they will ask you till this order 2, pole repeated twice. If let's say this pole instead of 2, this was 3, then here instead of once differentiation, I would have had to differentiate twice. Also, there will be an additional term. I have to divide by 1 by 2 factorial. So basically, whatever is the power here, that factorial I have to divide. If it was 4, then I would have had to make this 3, and I would have had to divide by 3 factorial. And this will repeat basically. But if they are giving you a pole that is third order, right? Either your function will be very simple to differentiate, or they will never give you. Okay, so that is a formula. You can decode the formula basically, how to remember. So basically, what is the order of repetition? If the order of repetition is n, then you will differentiate n minus 1 times. Also, you will divide by n minus 1 factorial, and at the end, of course, you will write limit as z tends to z naught. So that's how you solve for repeated poles. Okay, so I have taught you Lorentz series and this method to calculate residue. Why is the residue so important? We will come to that to solve complex integration. So let's come to this one, compute the residue for this. So again, the residue, like I have a pole at z equal to 0, so I will just find out the Lorentz series, that is 1 plus 1 by z plus 1 by z square upon 2 factorial and so on, and I will decode the coefficient of 1 by z, that is 1. So the residue of this function would be 1. You don't need to use that method. You can use Lorentz series. Similarly here, z sin z, I have discussed how to solve using the method that I have taught you. Okay, because I have two poles at z equal to 0. I have mentioned this previously. I have two poles at z equal to 0. So the method how to solve for repeated poles I have taught you. You can go through that, or you can use Lorentz series that we have already done. Either way, you will get back to the same answer. Okay, but it will be very difficult for you to solve actually. This limit will be very difficult for you to solve. So you have to actually use mostly this method to Lorentz series. So don't worry, they will not give you these difficult things. Okay, they will give you easy things only. So there is a question which yeah, you can go through, you can have a read about the residue of the question. I will directly move on to the Cauchy integral theorem. So what does Cauchy integral theorem state me? If fz is analytic inside a closed curve C and no poles of fz lie in C, that is basically fz is analytic in the given curve, then the closed line integration will be 0 of fz. So along the given curve, if the function is analytic, then the closed line integration will be 0. Isn't that what we already know? Yes, just Cauchy told you more clearly. So that's why it became a Cauchy integral theorem. So this we already know. So what is the integration along the circle z equals to mod z equal to 1, that is this circle of radius 1 of this particular function. This function is entire function. So I don't even have to lift up the pen. The answer will be simply 0 with the help of Cauchy residue theorem. Here also, again, I have to integrate about this circle z equals to mod of z equals to 1 of this particular function. Now, this function is not simple polynomial, it is rational function, and at z equal to 2, function is definitely not analytic because I have a singularity point. But my required curve does not contain mod z equals to 2. So I will never write z equal to 2. I will never reach the point z equal to 2. So in the given region or the curve, function is analytic. So I don't have to worry about it. So the answer will be 0. Here again, fz equal to sec z. So is my function analytic? So sec z basically means 1 by cos z. So when does cos z goes to 0? When z is equals to pi by 2 and pi by 2 basically, not pi by 2, minus 3 pi by 2 also it is 0, right? Yeah, minus 3 pi by 2 it is also 0. So pi by 2, 3 pi by 2 and so on. Yeah, 3 by 2, 3 pi by 2. So this will be basically pi by 2 plus n pi, correct? Yes. So I see that it is mod z equals to 1. So what is the lowest value of my singularity point? Lowest value is pi by 2, that is 1.57. Sorry for the noise, background noise. 1.57, and negative pi by 2 also it will be going 0, that is minus 1.57, right? So pi by 2 is here, minus pi by 2 is here. and all the other poles are lying outside my required region, right? Basically, this is the real part. Z equals to real pi by 2 plus pi by 2, that is real part, right? Real x, y is 0, imaginary part is 0 basically. So my required region does not even contain the singularity point. If my required region does not contain the singularity points, then simply answer will be 0. Okay, but here now there is a problem. Now if I contain the required region, so if I contain the required region, then what will be my answer? Then function first of all is not analytic in the given region. Then you have to identify the residue of the function at the singularity point. If that singularity point lies within my given region, because now my region is mod z equal to 3, so I have a circle of radius 3. So radius 3 will include this z equals to 2 point, that is 2 comma 0. This point will be included here, right? So if this point is included, which is a singularity point, that means the answer will not be 0 anymore. Function will not be analytic in the given region. At a particular point, function is not analytic. Everywhere else, it is analytic. So what I will do, I will find out the residue wherever the function is not analytic. So at z equal to 2, what is the residue? Residue is z minus 2 will multiply, it's a simple pole. So it will be 2 square, that is 4 plus 2, that is 6 plus 5. So it is 15. 15 is my residue. So my answer would be everywhere else it is analytic except z equal to 2. So it will be 2 pi I into sum of the residues of whichever singularity points are lying inside my curve. So here z equals to 2 is lying inside the curve, so residue would be 15. I will take another example. Let's say I have z minus 3 as well as the pole, or not z minus 3, z minus 1 as the pole location. So now 15 is 15 residue. So what is the residue at z equal to 2? At z equal to 2, this would be 15 divided by 1. Yeah, 15 is a residue. Also, I will add the residue that is present at z equals to 1. So whichever poles are lying inside my required region, I have to add all those residues. And remember, your curve should be in the anticlockwise. By default, nothing is mentioned. You will assume it to be anticlockwise. Then this will be plus 2 pi I. If it is clockwise, then this will be minus 2 pi I. Just be careful. If it is clockwise, it will be minus 2 pi I. If it is anti-clockwise, it will be plus 2 pi I. This thing you have to remember, the most important part. Here I have written the same thing. Just go through the statement and understand it. So just read this statement and understand. Whatever poles or residues are lying inside, I will have to compute the residues of, whatever poles or singularity points are lying inside my required region, I will have to calculate the residue of all those points which are lying inside my required region. There can be a pole that is z minus 5, but that is lying outside my required region. So I don't need to calculate the residue for this. Okay, so I will calculate the residue which are lying inside the required region which I am integrating, and then I will add all the residues and I have to multiply plus 2 pi I. I is the complex number. This is my Cauchy residue theorem. Very, very important 5-star theorem. Remember it no matter what. This is by default. If nothing is mentioned, you will assume your curve to be anti-clockwise, but sometimes what happens, your curve can be in the clockwise direction. They will mention it. So if it is in the clockwise, then you will not multiply plus 2 pi I, you will multiply minus 2 pi I. So let's begin by solving this question. So we have to evaluate this line integration about the curve mod z equal to 3. Basically, I have a circle. If I choose, I have a circle whose center is at origin and whose radius is 3. What is fz? Fz is this function. What are my poles here? I have a repeated pole at z equals to minus 1. That is x equals to minus 1, y equal to 0. So at this point, I have a pole which is lying inside my curve. So definitely, I will have to calculate the residue. So what will be my answer? My answer, because nothing is mentioned, I will assume anti-clockwise direction. So my answer would be 2 pi I and the residue due to z equals to minus 1. So z equals to minus 1 is a repeated pole of order 4. So do you remember what do I have to do? First, I have to differentiate thrice. Because it is 4, I have to differentiate thrice and divide by 3 factorial into z plus 1 raised to the power 4 into fz, that is e raised to power 2z upon z plus 1 raised to the power of 4, limit as z tends to minus 1. So this will be my residue. So let me compute the residue here. Now whenever they will give you repeated poles, right, you will see the differentiation will be something very easy, because differentiating a rational function thrice will be very difficult, quotient basically. But here you have to differentiate e raised to power 2z thrice. That's very easy. It will be 2 into 2 into 2 and e raised to power 2z. That's it. 2 cube into e raised to power 2z. That's it. That's how simple it is. So this will be 1 by 3 factorial, that is 6 into 8 into e raised to power 2z, and z will be equals to minus 1. So this will be e raised to power of minus 2 into 4 upon 3. Okay, 4 by 3 e raised to power minus 2. So that is my residue. So what is the answer? Answer is 2 pi I into 4 e raised to power minus 2 upon 3. That is your answer basically. And that's it. So this will be 8 pi I by 3 e square. This is your answer. Like, it will be imaginary because the terms are complex. So that's why the answer also will be a complex term. Let's solve this one. This came in EC 2008. This question is pretty interesting. So we see the contour C is given in the complex plane, z equals to x plus jy. The value of the integral dz z square minus 1. So they are asking me the closed line integral upon j is just a complex number, right? J is just a complex number. J and I are interchangeable. So they are asking me this complex integration. So let me first write the function. What is my fz? Fz is 1 by z square minus 1, or it is 1 by z plus 1 into z minus 1. So definitely z equals to minus 1 and z equals to plus 1 both are lying inside my contour. If they are lying inside my contour, then definitely I will have to calculate the residue for them. So what will be the residue for them? So residue r of 1 and r of minus 1. So r of 1 would be due to z equals to 1 and r of minus 1 would be due to z equals to minus 1. So r1 would be basically, because it's a simple pole, it's very easy. I will multiply, this is due to z equal to 1, that is z minus 1 term, right? So z minus 1 into fz, that is z square minus 1, that is z plus 1 into z minus 1, and then I will obviously put the value of z, limit as z tends to 1. This will be 1 by 2. That is my r1. What about r of minus 1? R of minus 1 would be limit as z tends to minus 1, z plus 1 into 1 divided by z plus 1 into z minus 1. This will be equals to minus of 1 by 2. Now the residue comes negative of each other. So overall your answer would be the answer of the integration. Answer of the integration would be dz z square minus 1. This will be equals to 2 plus 2 pi I, because you see, like, it is going in the anticlockwise direction. You will say plus 2 pi I or 2 pi j into sum of the residue, that is half minus half, so 0. Now your final answer is, this is the integration answer, I have to divide by pi j. So this is anyway 0, so 0 divided by pi j would be simply 0, and you will say 0 is the answer, which is wrong. So what went wrong here? So when I was adding the residue up, right, this was the part where I messed up, because you cannot simply add. So actually I moved very fast during discussion of the orientation of the curve. So at when my this singularity point z equals to minus 1, Actually the orientation is in the clockwise direction. Actually that is a good thing to observe, right? Because you see here there will be the arrow, this will be the arrow basically, correct? So actually the orientation is clockwise, and at z equals to 1 the orientation is anti-clockwise. So we at z equals to 1 the orientation is anti-clockwise, so here there will be plus sign, but at z equals to minus 1 the orientation is clockwise. So actually I should not add the residues, I should subtract the residues. This will be a minus. Residue itself is minus of half and I should subtract the residues. So actually this will be uh, this will be 2 pi j. This will be the result will be 2 pi j. So now the result of the integration is 2 pi j, but the what I have to find out, I have to calculate the integration divide by pi j. So result of this is 2 pi j, and if I divide by pi j, this would be 2. So 2 will be your answer for the question. This was a very good question that came in EC 2018. Very recent question. So these kind of questions are getting asked. So yeah, just be careful. Don't mess this up. What is the orientation of my curve at the residue? At the residue, the orientation of curve C is clockwise. At this particular residue, the orientation of the curve is anti-clockwise. So just be careful regarding these things. Don't mess it up. So we have another question like this. Compute the integration fz, where fz is sine of 1 by z minus 2. So at z minus 2, right, I have a singularity point, correct? So curve is mod z 3. So basically the curve is a circle whose radius is 3 and center is 0 comma 0 origin, and I have a and what is the singularity point? So the singularity point is nothing but a essential singularity point, because if I expand my series, this will be z, that is 1 minus z raised to the power 2 minus 1 by z minus 2 3 factorial plus cube will be also there, 1 by z minus 2 5 factorial and so on. This will go on. So yeah, this will go on. So basically this is already in the Lorentz series format. So I know I have a pole or singularity point at z equal to 2. So I just have to find out the coefficient of 1 by z minus 2, that is simply equals to 1. So the residue is 1. So if the residue is 1, right, what will be your answer? Your answer will be simply okay. So we have to find out this, right? Residue is 1. So your answer will be 2 pi I into the residue, that is 1. So your answer of the integration would be 2 pi I. Nothing is mentioned. You will assume clockwise. Sorry, in the clock they have mentioned clockwise. Sorry, anti-clockwise. You will assume anti-clockwise, but they have mentioned in the clockwise direction. So your answer would be minus of 2 pi I, because clockwise is negative. So your answer would be minus of 2 pi I. So now let's solve few gate PYQs. So we have this first question where we haven't given this integration. Where C is the counterclockwise oriented circle defined by x minus I 2. So let me first plot the curve C. So if I plot the curve C, this, right, x minus I, okay, x minus I mod of 0. So y is not even here, okay, circle x minus I, okay, that's interesting. Okay, actually what they're telling us that x is a complex number. So instead of z, right, they have written x just to confuse you. Just to confuse you, they should have mentioned actually z is a complex number. So z is a complex number, okay, z is a complex number, sorry, x is a complex number. So don't worry, we will not get confused. So can you tell by observing, if here it was written z minus I mod of z minus I mod equals to 2, then could you comment what is the center of the circle? The center of the circle would be 0 comma 1. right? Because the imaginary part is there, right? So z will be x plus iy, so y minus 1 into I and x minus 0. So center would be x 0 comma 1, and what is the radius? Radius is 2. So don't be afraid by seeing this x is a complex number. So center is basically here in the imaginary part, imaginary of x and the real of x, real part, because the imaginary part is 1. So center is here 0 comma 1, and I have a circle whose radius is 2. So if its radius is 2, so the circle would be somewhat like this. Let me bring this. Here. So if its radius is 2, this would be 0 comma minus 1. This would be 0 comma 3. Okay, so what are the location of my singularity points? So I see I have a repeated singularity point at the origin here, right? So definitely it will lie inside the curve, and I have a singularity point x square equals to 4, that is x will be equals to plus minus 2i. So plus minus 2i plus minus 2i. So minus 2i would be lying here, minus 2i, and plus 2i would be lying here. So I have actually these two poles, that is 2y and 0 0, that are lying inside my uh, curve, and this pole is lying outside the curve. So I will only compute the residue due to, so I will compute residue, two residues. One residue will be due to 2y, other residue will be due to origin. Or at origin I have repeated pole. So what will be my residue at the origin? This will be limit as x tends to 0, then I will write this to be equals to, I have to differentiate. If it is repeated twice, I have to differentiate only once. How can I remember? Like if the pole was repeated only once, like if it was only a simple pole, no repeated, then do I need to differentiate? No. So for a pole, if it is repeated twice, then I have to differentiate once. If it is repeated thrice, I have to differentiate twice. So like that you can remember. For simple pole, you remember that you don't need to differentiate anything. So for repeated pole, you have to differentiate once. So like that you can keep on increasing. So there will not be any division of factorial, because you have to only differentiate once. So 1 factorial into z minus z naught. Z minus z naught is x square, like z minus z naught whole square, raised to the power n, that is x square, into fz. Fz is sin x upon x square into x square plus 4. So that is my r naught. So this will be like ddx now, because this time my complex variable is not z, it is x. So they have given you the equation in terms of x, not z. So this will be sin x. I have to differentiate this function. So if I differentiate sin x, it is cos x into x square plus 4, cos x into x square plus 4, minus this will be 2x into sin x upon x square plus 4 limit as x is tending to 0. So that would be equals to 1 into 4 upon 4. So this will be 1. So your r naught residue would be 1. Now what about the other residue? What about the other residue? So other residue, that is r of plus 2i. Minus 2i I don't have to worry. Also I think they have mentioned it is counterclockwise. Okay, it is counterclockwise. So orientation is mentioned, it is counterclockwise, so it will be plus 2i, plus 2 pi I, plus 2 pi I. So r of 2i would be equals to limit as x tends to 2i. Now it is a simple pole. It is a simple pole. Let me break down my fz. Otherwise you will be so I will break down my fz. So this will be x minus 2i into fz. Fz is sin x upon x square into x minus 2i into x plus 2i. So I can break down my x square plus 4 like this. So x minus 2i, x minus 2i will be cancelled. I will put x equal to plus 2i. That would be equals to, so this will be sine of 2i upon, this will be 2i whole squared, that is minus 4, and x minus 2i is cancelled, into 4i. Now what is sine of 2i? That is actually pretty interesting. What is sine of 2i? So sine of 2i, if I solve, right, it will not be something as usual. So what is sine of x? Sine of x is e raised to power minus x minus ix, sorry, plus ix minus e raised to power minus ix upon 2i. Actually for this question was MTA, if I remember correctly. This question was MTA. So if I put x equal to 2i, this will be e raised to power minus 2, yeah, 2i, yeah, I square minus 2 e raised to power plus 2 upon 2i. Yeah, that will be sine of 2i actually. So overall, yeah, this is the first thing. So what is the sum of residue? So overall residue is r naught plus r 2i, that is equals to some very weird values. Okay, sine of 2i is this value. So if I replace over there, this will be e raised to power minus 2 minus e square upon 2i, that is already 16. 16 into 2, that is minus, yeah, 32. Yes. Okay. Yeah, it is 32. So actually none of the options here will match. Okay, sine 2i is there. Okay, sine 2i is there actually. Okay, sorry. We don't have to actually derive the sine 2i. We can keep the sine 2i as it is. If I keep the sine 2i as it is, still options will not match. So it will be basically 2 pi I into 2 pi I into r naught, that is 1 plus your uh, the other residue, that is sine 2i upon 16. So I can go at the top, right? I can go at the top, the sign will just reverse. So here this will be minus, so plus 2 pi I will be there, and minus pi sine 2i by 8. Actually, yeah, minus pi by 8 sine 2i is there. Actually what I think what happened, like here none of them will be correct, it will be MTA, because of course you have this particular thing, right? 2 pi I, 2 pi I is there, correct? Let me just, okay, one small error from my end here. This will be x square plus 4 whole square. I've missed this. This will be x square plus 4 whole square. So if it is x square plus 4 whole square, this will be 4 by 16 actually. So this will be 1 by 4 actually. Yeah, that's a mistake on my behalf. This will be 1 by 4. So if this is 1 by 4, then this will be 1 by 4 here. This will be pi I by 2. So an additional term of pi I by 2 will be there. Although like you are saying this is matching, but I think they've either they consider the curve to be something else that should not be included in the residue, but something they have done. So this question was empty, if I remember it correctly. This question was empty. Okay, that's it. So yeah, with that we end this question was empty basically. This will be the official answer. None of the options were matching. Let's solve the next question. So the simple curve C is shown if this is equals to I pi into a. What is the value of a? And where z is the complex number, they should have mentioned also. Z is a complex number. So I see what is the location of my uh, poles. My poles are simple. At z equals to 1 and z equals to -1. They have even marked the poles. How convenient. So I see, of course, z equals to 1, this pole is outside and this pole is inside the curve. So of course, I only have to compute the residue due to this particular pole. So the residue due to this pole, it is a simple pole, that would be z plus 1 into 2z, 2 raised to power z upon z minus 1 into z plus 1 limit as z tends to -1. This will be equals to, this will be cancelled, z equals to -1, this will be 2 raised to power -1 upon -2. So this will be basically -1 upon 4, that is the residue. So your answer would be, remember what is the orientation, anti-clockwise. So your answer would be plus 2 pi I into the residue, only one residue is inside, so it will be -1/4, which is minus pi I by 2. So minus pi I is there, 1/2 is not there, so a will be equals to 1/2, that is 0.5. So your answer for this question would be 0.5. That's it. Let's solve the next question. So here if I solve this question, w raised to the power 4 equals to 16j, which cannot be the value of w. Now they are asking questions from basics. That's why I always try to teach basics, because this is a 2023 question from EC, but still they are asking question from basics of complex number. That's why I have spent around 1.5 hours even in crash course in basics, because they will ask you questions from basics, and trust me, 50 or 60% of the students who have studied complex variable, they will not be able to solve this. They know all this, but they will not be able to solve this basic question. Then what's the point? So yeah, that's why I focus a good amount on basics. So yeah, let's like w is a complex number, w raised to power 4. So what is 16j? Here I see exponential, right? So let me first convert my complex number into exponential format. So this will be w raised to power 4 equals to 16j, which is 16 e raised to power j pi by 2, right? I can write my j plus j to be pi by 2, e pi by 2. That is possible. So what cannot be the value of w? What cannot be the value of w? So it can be e raised to power j pi by 2. What else can it be? It can be any value, e raised to power pi by 2 plus 2k pi plus 2k pi, right? J into pi by 2 plus 2k pi, because if I rotate a whole 360 degrees, I will come back to the same place. So because I am seeing here larger angles, so I have to consider that. Okay. So if I raise both sides to the power of 1/4, so this will be 16 raised to the power of 1/4, and I have to raise this a power to be to the power of 1/4, so I have to multiply 1/4 plus 2k pi 1/4. So this will be 2 into e raised to power j pi by 8 plus k pi by 2. So when k is 0, my w would be 2 e raised to power j pi by 8. So this is valid, right? So this will not be my answer, because they are asking which cannot. So if I put k equals to 1, oh sorry, this is 2 pi, right? Sorry, this is 2 pi. So 2 pi, I have to check. This is definitely one of the answer I am getting, so this cannot be my answer. If I put k equals to yeah, let me put k equals to 1. If I put k equals to 1, this will be pi by 8 plus pi by 2, that is basically 5 pi by 8. So 5 pi by 8 is also observed. So this is also not one of my possible answers. Let me put k equals to 2. If I put k equals to 2, this will be pi by 8 plus pi. That will be 9 pi by 8. So 9 pi by 8 I can see in the option D. So yeah, these are all possible values, right? Because of course I've told you, right? If I move 2 pi, it's the same thing. I'm reaching the same point. So because argument is unique, but this angle can keep on changing. So definitely I see only option A I will never be able to make. I'll never be able to make option A. So definitely option A is not a valid solution for W. So option A will be the correct answer for this question. So they will ask you question from basics. This was a nth root of unity, basic question, but still you have to solve it. So let's find out this. Mostly they ask from control integral, or they will ask you question from basics only. So we have to find out the value of this contour integral, where C is the this contour taken in the counterclockwise direction. So when sometimes they also say that the curve, right, that I've shown you, that it say C is the curve, C curve. Sometimes it is also called as contour. So don't be scared. So the curve is also called as contour. That's it. Don't be scared by it. It is in the counterclockwise direction. So what is my C? So if I see, right, what is the center? Center is minus 1 comma plus 3 by 2. So this will be minus 1 is here and plus 3 by 2 is here. So center of the circle is here. Now the radius of the circle is 1. Radius of the circle is 1. That is interesting. So if radius is 1, now radius is 1, correct? And this distance from the y-axis is also 1, because this was minus 1, right? So the circle would be something like this, and this distance is 3 by 2. Actually this distance is quite large, so it will not touch my x-axis. So I will have a circle that will be just like this. It will just touch the y-axis because this distance is 1, right? X coordinate distance is 1 and its y coordinate distance is much higher, so it will not touch the y-axis. That is the thing. Now what are my residue points? Sorry, what are my poles? So for that I have to find out when this function goes to 0, that like when the denominator goes to 0. So if I calculate, when does my denominator goes to 0? So that would be basically, so let me find out the roots of this equation. Minus b plus minus b square minus 4ac, 4ac, that is 8 upon 2a. So this will be minus 1 plus minus, this is 2i, so I. So minus 1 plus minus 2i. So minus 1 minus I. Minus 1 minus I is somewhere here, and minus 1 plus I is somewhere here, because what will be this point? So this overall distance is, sorry, this overall distance is 3 by 2, and this distance is 1 actually. So this point would be half. Okay, this point will be half, because overall the y distance, because the center is at 3 by 2, so and the radius is 1, so overall this distance would be half, and this pole will definitely lie inside my circle, right? Because this is minus 1 plus minus I, so it will just be along this line in between the circumference and the center. So definitely this particular pole, right, the pole that is minus 1 plus I will definitely lie inside the contour, but the other pole will not lie inside the contour, and it is in the counterclockwise direction. So I just have to find out the residue of what? I have to find out the residue of minus 1 plus I. So what will be that? So that would be limit as z tends to minus 1 plus I into z of plus 1 minus I, z minus z naught, into fz. Fz is z plus 2 upon, now I will break my function down. So I can write this as product of two poles. z plus 1 minus I into z minus 1 plus I. Sorry, hold on a second. This will be plus 1 only. Yeah, z plus 1 plus I. Yeah. So basically, I have written it in terms of two poles. Basically, if I have a pole alpha and beta, so I can break my polynomial as z minus alpha into z plus beta, z minus beta. That is what I have done. So this would be, if I put z equals to z tending to minus I plus I, minus 1 plus 1. So this will be minus 1 plus I plus 2. This will go away. This will be again minus 1 plus I plus 1 plus I. Okay. So here this would be 1 plus I upon 2I. So this will be, okay. So this is my residue. So my answer, because it is in the counterclockwise direction, so I'll multiply 2 pi I into my residue, 1 plus I upon 2I. So this will be pi into 1 plus I, or sometimes I is written as j, so don't be scared by that. So your answer would be pi into 1 plus j, pi into 1 plus j, that is present in option B. So option B is correct for this question. Let's solve the next question. So mostly they will ask you from integral, this integral like Cauchy residue theorem mostly. So let's solve this question. Let z be a complex variable where c is the circle in the complex plane mod z equals to 3. I think we have already solved these kind of question. So again the same thing, it's mod z equal to 3, and of course I have singularity point at z equal to 0 and at z equal to 2, and both of them are inside my circle. So you will have to solve it. So z equal to 0 is a repeated pole. So yeah, so if it's a repeated pole, you will do this z square into sine of pi z upon z square into z minus 2 d of dz into 1 by 1 factorial basically. So here if I solve this, this is the residue due to 0. I will also solve the residue due to I, and it is in the they have not mentioned in what direction, they should have mentioned, but by default I'll assume it to be in the counterclockwise direction. So yeah, and of course don't forget the limit, right? Limit as z tends to 0. So this will be sine of pi z upon z minus 2 derivative. Okay, I have to find out the derivative. That will be, this will be z minus 2 into pi into sine of pi z, and minus, first I am putting the derivative, limit as z tends to 0. First I am calculating the derivative, and this would be sine of pi z upon z minus 2 whole square. So if I put now z equal to 0, this will be minus 2 pi, and sine of like sine of 0 is 0 only, so this will be 0 only. This also will be 0. Okay, so overall your residue comes out to be 0 upon 2 square, that is 4, which is 0 only. So the first residue comes out to be 0, that is quite simple. What about the second residue? Second residue, that is at z equals to 2. That is a simple pole. So limit as z tends to 2, z minus 2 into sine of pi z upon z minus 2 that would be equals to simply sine of 2 pi. Sine of 2 pi is again 0. Okay, z turning to sine of 2 pi. Sorry, z square is also there, but that would not matter actually, because this is coming out to be something I'm messing up. Okay, it is a repeated pole, closed line integration, mod z equals to 3. Yeah, it includes all of it. So if I'm calculating this, oh, so yeah, this is correct, this is correct. So this will be, I will differentiate this, and z equal to 0, that is 0 only. This is also 0 only, and this is 4, so this is 0 only. Okay, somewhere it seems like I'm messing up. I have to yeah, I have to check where am I messing up here. So yeah, where is it going wrong? Here the residue is 0, that is for certain, because if I put z equals to 2, this will be 2 pi. Yeah, that is 0. Here let me just check once. I'm multiplying by z square, that is going away, and if I differentiate the numerator, that will be pi sine pi z, and z minus 2 will be there. But if I put z equals to 0, that is anyways gone, minus sine pi z, that is 0 again, right? Like, what am I doing? I just figured out like I'm differentiating. I differentiated the inside function. I use the chain rule, but I forgot to differentiate the outside function. This will be cos of pi z. That is what I was thinking, like what am I doing wrong? Sorry about that. What am I doing wrong? So this will be cos of pi z. This will be cos of pi z. So yeah, now if z is equals to 0, this will be actually minus 2 pi. Minus 2 pi would be here. Yeah, that is 0 only. Anyways, that it does not matter. So this will be minus 2 pi by that is minus pi by 2. So yeah, now your residue, your overall answer of fz dz would be 2 pi I into the residue, that is minus pi by 2, or like sometimes I is written as j, both the same thing, complex numbers, like imaginary complex number, which is minus pi square into j. So minus pi square into j is present in option D. So option D will be your correct answer for this particular question. So yeah, let's move on to the next one. Which of the following statements involving control integrals evaluated in the counterclockwise direction on a unit circle is or are true? So I am evaluating in the counterclockwise direction. So here, right, anyways I don't have any pole, and this function is always, no, actually yeah, I have a essential singularity at z equal to 0. Do I have? No, I don't have any, sorry, I don't have any singularity points here. I don't have any singularity points. So this function is entire function. So anyways, without even Cauchy residue theorem also, I can say like the closed line integration along any curve will be 0. So which is or are true? So option A is definitely correct. This one, closed line integration of z raised to power n dz equals to 0, where n is a even integer. N is an even integer. So n is a even integer. N can be positive and negative. Remember that. So for n positive, definitely it is a polynomial. So it will be differentiable, and it will be basically the residue will definitely like it will be entire function. For n greater than 0, it will be entire function. Now what about n less than 0? So n is a even integer. They have not told that whether n will be positive or negative. So n can be negative, that is minus 2. N can be minus 2. So if n is minus 2, then what will happen? Then it will be 1 by z square. So what is the, like I have a repeated pole at z equals to 0. What is the residue? This is in the Lorentz series format only. The residue is simply 1. sorry, it should be residue is 0 actually. Residue is 0, huh? Residue is coming out to be 0. Okay. Residue is coming out to be 0 for 1 by z square, because I have to find out the coefficient of 1 by z. Correct? Yeah, residue will be 0. For 1 by z raised to the power 4 as well, I have to find out the coefficient of 1 by z. For that also, residue is like the coefficient, like it does not have any. If n is 4, minus 4, sorry, it comes out to be 1 by z raised to the power 4. Again, I have to search for the 1 by z term. For that, the coefficient is again 0. I don't have any 1 by z term. How can you verify? So what do you do? Let's say I have this function, right, 1 by z square. What would be the residue if I use my simple method for repeated poles? So for repeated poles twice at z equal to 0, what do? We do z minus z naught raised to the power n, that is square, into the fz, that is 1 by z square. Then I differentiate once. For twice repeated, I will differentiate once and divide by 1 factorial, and then I will write limit as z tends to 0. So this will be cancelled. Derivative of 1 is simply 0. So ultimately your residue comes out to be 0. Similarly, for any even number, actually, luckily, any even number, your residue will come out to be always 0. So actually, for when n is even, this is actually valid. Luckily, you are very lucky. Although my function is not analytic always, but this will be valid because the residue is 0. What if instead of even, they would have only told you n is an integer? If n was only an integer, then it would have been wrong, because I can choose n equals to minus 1. If I choose n equals to minus 1, then what will happen? Then it will be 1 by z. I have a pole at z equal to 0, and what is the coefficient of the Lorentz series? It is 1. So definitely this time the residue is non-zero. So my answer will be 2 pi I actually. So 0 will not be answer. How can you verify? Like this, that is simple, right? You write z into 1 by z, limit as z tends to 1. So that is my residue, that is simply equals to 1 without even doing that complex calculation. So yeah. So that is a interesting fact. So this option B will be correct. What about option C? So integration of cos z over a unit circle is not equals to 0. It is not 0. Okay. If is cos z a entire function. So if I see for cos z, if I expand my cos z, expansion of cos z would be z 1 plus z square by 2 factorial. I think there would be minus, yeah, minus z square by 2 factorial plus z raised to power 4 by 4 factorial, and so on. So actually there are no singularity points here. There are no singularity points. So this is a this is a polynomial, right? This is just an polynomial. Correct? If it is just an polynomial, so it will be an entire function. So this is not true actually. Not equal to 0 is incorrect. This is a entire function. So and the closed line integration of an entire function will be 0. Not true. What about this one? Closed line integration of sec z will not be equal to 0. So for sec z, I have to check what are my singularity points. So option D, sec z is nothing but 1 by cos z. So 1 by cos z, what are my singularity points? So at z equals to pi by 2 minus pi by 2, I have a singularity point. And of course at 3 pi by 2, 3 pi by 2 I have a singularity point. At minus 3 pi by 2 also have a singularity point. But one thing you notice, this is 1.57, this is minus 1.57, but my circle is a unit circle, right? My circle is an unit circle. So the smallest singularity points are lying outside my circle. So none of the singularity points are actually lying inside my circle. So if none of the singularity points are lying inside my circles, definitely residue will be 0. There will not be any residue. So the closed line integration will be 0 again. But here the limit is not equal to 0. So this option is also incorrect. This option is also incorrect. One more thing, if you tend to forget what will be my cos z, although I have derived this, like how to write the series in terms of cos. So your answer is AB. Your question is done. Your answer is AB. Now, like sometimes what happens is you will have that you will forget like how to write my sin x and cos x. So one thing you remember actually, first of all, your cos x, right? Cos x will never be more than 1. So you have to write this alternating sign plus minus. If I write all plus, this will be a problem, because this will go, if for z something 0.1 or some very low value, this will go more than 1, but cos z will never be more than 1. Cos, right, the range of cos is always between -1 to +1. That is how you can remember. Also, your cos function is even function. So you see, if I replace z with minus z, this function will not change. Your sine function is an odd function. There also alternating sign will be there, because sin x will not be greater than 1. Okay, the range will be between -1 to +1. But yeah, that's the thing over here. So yeah, that's how you can remember. Obviously you have the basic thing. You can expand e raised to power ix, cos z is e raised to power iz plus e raised to power minus iz by 2. You can expand your exponentials e raised to power iz and e raised to power minus iz. From that also you can get the same series. I have already derived this in the, I guess, integral calculus part. Okay, so yeah, now let's solve this next question. This one, I have this polynomial p of z, where z is a complex number, conjugate of p of z. So they're asking conjugate of p of z is equals to p of conjugate of z. Okay, this is interesting. For all z, okay, the sum of roots of p of z is equals to 0. The sum of roots of p of z is equals to 0. That is not correct actually. The sum of root of p of z, right, sorry, is a real number. The sum of roots of p of z is a real number. That is incorrect, because this term, right, always remember, right, if I have, let's say, ax square plus bx plus c, do you remember what was my sum of root in this quadratic equation? The sum of root was equals to minus b upon a, correct? So always the first term after the highest order represents the sum of root. So here what will be my sum of root? This term, minus b upon a, that is minus 1 plus j upon 1, minus 1 plus j upon 1. So yeah, sum of root is not a real number, it is a complex number. So this option is incorrect. The complex roots of the equation p of z equal to 0 come in conjugate pairs. That is, which of the following is true? Actually only they are asking is true, is not is. So it is a single correct answer. So this option is incorrect. The complex root, all roots cannot be real. All roots cannot be real. If the sum of the roots is a complex number, yeah, this statement actually seems correct, right? Because if the sum of roots is a complex number, okay, if the sum of roots is a complex number and if all roots are real, then I will never be able to get a, like, I will never be able to add all the real roots and get a complex number. That is not possible. If all the roots are real, then if I add all the roots, I will never be able to get a complex number, because that is what the equation is telling me, that the sum of roots is a complex number. So this option, all roots cannot be real, is correct. At least one of them has to be complex conjugate. So actually the complex roots comes in conjugate pairs. This is incorrect actually. This happens whenever your coefficients are real. I'll just say you, of course there is a proof. The proof is basically this, right? If I solve for this, what is the root? That is minus b plus minus b square minus 4ac upon 2. So this plus minus, and if this term is less than 0, then this will be a complex number. This will be a complex number. So yeah, if this is less than 0, this will be complex number. So I will get plus minus I into b square minus 4, something like that, 4ac minus b square. So I will get a complex conjugate. But if my all these terms are not real, these are complex terms, then things are bit different. So yeah, they may or may not come in conjugate pairs. Now conjugate of p of z is equals to conjugate of z. Now this will be bit difficult to, like, this will be lengthy. You can solve this. So what you have to do, you have to change your z x plus iy, okay, and you find out conjugate of p of z. What will be conjugate? So your you will replace your z with x plus iy. So your p of z will be some u plus iv. So both of the u and v will be functions of x and y, because I have replaced, like, this will be x plus iy whole cube, then x plus iy whole square. Like, then after sorting out, your function will be u plus iv, where u will be the real part and v would be the imaginary part. And what will be the conjugate? Conjugate of p of z would be u of minus iv. You have to say this will be equals to the conjugate of p of conjugate of z. So p, what does p of conjugate of z means? Basically, if I replace my z with x minus iv, x minus iy. So here, everywhere, if I replace this with x minus iy, you will see, you will get a function that will be some m plus in. They are saying that this u minus iv and m plus in are same. You will see after putting that they are not same. So this is incorrect. So only option D will be correct. Let's solve the next question. Let minus 1 minus j 3 are the vertices of a rectangle. So let me first of all write down the vertices of a rectangle. Minus 1 minus j, minus 1 minus j, uh, plus 3 minus j, plus 3 minus j, plus 3 plus j, and minus 1 plus j. So actually this will be more closer. Now I have to calculate the integration along this curve. This is 3 comma 1. This is 3 comma minus 1. This is minus 1 comma minus 1. This is minus 1 comma 1. So now in the counterclockwise direction. So what are the pole locations? So I have a repeated pole at origin, and I have a pole at z equals to 4, which is definitely lying outside. This point is z equals to 3, right? That is definitely lying outside my contour. So I have to only consider the repeated pole at the origin. So if I solve for the repeated pole at the origin, so I have to do dz 1 by 1 factorial limit as z tends to 0 z square into 1 upon z square z minus 4. This would be my residue, and it is in the counterclockwise direction. So of course it will be like the residue will be positive, plus 2 pi I into the residue. So residue would be yeah, z tending to 0 would be minus 1, sorry, not minus 1 by 4. This will be minus of 1 by z minus 4 whole square. So this would be minus of 1 by 16. So 2 pi I minus of 1 by 16, that will be minus pi I by 8, or j. Sometimes they write I as j, so don't get confused with j and I. So minus pi j by 8, that is present in option C. So option C would be your correct answer for this question. Let's solve the next question here. So I hope you're, like, mostly they will ask you this simple question only. Sometimes they ask this CRE questions. They like, they're asking less CRE questions, but they can ask CRE questions. So CRE questions are also very, very important. Which of the following functions is or are analytic in the complex plane? So fz equals to j of real of z. So z is equals to x plus iy, and fz is real of z, j, like, or j, I can write here j. So real part is x basically, so it is j into x, fz is j into x, and whenever my function is purely imaginary or purely real, we know our function is never analytic. CR equations will not satisfy, so this is definitely not analytic. What about imaginary? Again, fz is imaginary of z, that is uh, simply y. Again, your function is purely real. If your function is purely real, it will not be analytic. Your fz is e raised to power mod of z. Again, in this case, what does e raised to power mod of z mean? Mod means the modulus, the magnitude, that is x square plus y square under root. Again, this thing is purely real. If your function is purely real, it will never be analytic. You can check. You will see ux is not equals to vy and uy is not equals to minus of vx. You can check. For all these three options, you can check. They will not satisfy. For the last option, it will satisfy because it is a polynomial in z. And we know if I have a polynomial in z, function is definitely analytic. So option D will be correct for this question. Let's solve the next question. Consider the complex function this. The coefficient of z raised to power 5 in the Taylor series expansion of fz about the origin. So like, yeah, finally they have asked the Taylor series expansion about the origin. So what you can do, see, simply if you expand the series, right, simple series expansion is the Taylor series expansion about the origin. So you don't have to remember the formula, but it's a good practice to remember what was the formula. So what was the Taylor series expansion about a point z naught? So it would be f of z naught plus z minus z naught into f dash of z naught plus z minus z naught whole square into f double dash of z naught upon 2 factorial, and this will go on. So I can bring the Taylor, this is my Taylor series expansion of a function fz about z naught. Okay, we can because I've shown you, we have done Taylor series expansion like in differential integral calculus as well, if you remember. So yeah, where is the Taylor series expansion? So that is like quite yeah, here, yeah, fz naught z minus z naught. Yeah. The formula is simple, it is not that difficult for you to remember. So yeah, we will solve it. So you don't have to even do this, right, because you have to expand about the origin. So you can simply expand the function, that should also be enough, but we can also follow this as well, that is not a problem. Okay, so we will do it both ways. So if I expand the function, simply expand the function, right, what is the expansion of cos z? It is 1 minus z square by 2 factorial plus z raised to power 4 by 4 factorial and so on. Okay, I have to write till and minus z raised to power 6 upon 6 factorial and so on. Okay, because I have to consider the z raised to power 5 coefficient. And what is the expansion of e raised to power z square? It will be 1 plus e raised to power, so not e raised to power, 1 plus z square by 1 factorial plus z raised to power 4 by 2 factorial plus z raised to power 6 by 3 factorial. Like it is, I hope you know the expansion of e raised to power z. So I am observing that there is no term of z raised to power 5. So the coefficient of z raised to power 5 would be simply 0. We can do the same thing. We can do the Taylor series expansion as well. So I have to expand about z equal to 0. So z naught is 0 in our case, origin. So f of 0 is what? Cos 0 is simply 1 and this is 1. So this will be 2. F of 0 is simply 2. Z minus z naught into f dash of z naught. So what is f dash of z naught? F dash of z is sine, so it is minus sine of z plus 2z into e raised to power z square, and I will put this value basically z equal to 0. If I put z equal to 0, this is 0, this is 0. So f dash of z naught is 0. So this term is simply 0. Okay. What about f double dash? Sorry, this term is simply 0. What about f double dash? F double dash would be, this will be minus of cos z and this will be some function. So you can keep on doing it, right? You will see always the odd derivative is 0. You can continue and you will observe this. You will observe this trend that the odd derivative will always come out to be 0. So if the odd derivative is 0, that means the odd power will always be 0, right? Coefficient of odd power would be 0 because this coefficient was z minus 0 raised to 1. Basically, coefficient of z is 0. Coefficient of z cube would be 0. Coefficient of z raised to power 5 would be 0. So always the odd power would be simply 0. So answer will be simply 0. Yeah. So let's move on to the next question. This one. Let's see be a clockwise oriented closed curve in the, so it is a clockwise curve. Remember, it is a clockwise curve. Mod z equals to 1. So I have a circle of radius 1 and it is a clockwise curve. And function fz equals to j into z. But z is a basically complex number. They should have also told this. So what will be the integration of this closed line integration about this circle? What will be the closed line integration about this circle? So of mod z. Now this, right, is this function analytic? This function actually is analytic. This function actually is analytic because again it is polynomial in terms of z. Do I have any singularities? No, no singularity. So of course, as the function is analytic, I don't have any singularities. So answer will be simply 0. But I can prove it. Sir, prove karo analytic hai ki nahi. Let's prove it. So z is equals to x plus jy. So this will be j into x plus jy. This will be equals to jx minus y. So let's calculate u of x, that is equals to 1. U of v of y is, hold on a second, हो जाएगी ना, अभी गलती हो जाती. This will be minus y plus jx. So properly write the real part and the imaginary part. So what is my u of x? It is 0. What is my v of y? It is also 0. So 0 is equal to 0. Correct. What is my u of y? It is minus 1. What is my v of x? It is 1. So is u of y equals to minus of v of x? Yes, 100%. So function is analytic. This j is just a constant number. Like this could have been 3 into z. You could have said, yeah, this is analytic. But just because they have kept this j, you are scared. This is just a constant number. So don't be scared. This will be always analytic. So if you have been given a closed curve, the integration will be simply 0. That's it. And whenever in a complex integration, right, they are asking you this kind of direct integration. You know, even if there is some residue, it will be 2 pi I into some real number. Sometimes here can be imaginary number as well. So be careful. There can be imaginary, but mostly this number is real. Residue is real. So mostly you will get a complex number. So you cannot type that in the exam day, because here you can only input real values. But one day this can be imaginary as well. So just be careful. Just I'm telling you. But this is also another trick to confirm that yeah, you can only input real numbers. So mostly residue will be 0. Otherwise, like you cannot put either you cannot input 2 pi I into 1. You cannot input this, right? Residue has to be 0. So yeah, that is another way. Let's move on to the next question. So let fz equals to 1 by this, defined by this closed line integration over the contour circle of unit radius, center at the origin, and like direction they have not mentioned, radius of 1 unit circle. So yeah, if I can find out the singularity points for this particular function, minus b plus minus b square minus 4ac, this is also 36 only upon 2a. So singularity point is minus 3 only. Like I have two poles at z equals to minus 3, and z equals to minus 3 is lying outside. So it is outside, so answer will be 0. So mostly like complex questions are very simple. Like if it is lying outside, you would have no calculation, 0 calculation. Answer is 0. So let's solve the next question. So here, although I have not explained you basically the series expansion, but you can solve it still without understanding how to do series expansion. You can just Google bit Lorentz series expansion, but still without that also you can solve it. One thing you have to understand is the series expansion of 1 minus x or 1 plus x inverse. This I have already discussed. What is a series expansion? I have told you to remember it. So this would be 1 minus of x. Why it would be minus x? Because I am doing 1 plus x, where x is a positive number. So x has to be a positive number. Then only this series will be valid. So if I am dividing by, let's say, 1 plus 0, x is very small positive number, 0.01, right? So 1 plus 0.01, which it will be something less than 1, correct? So that's why I am subtracting from 1 with x, not adding. So that's why first minus will come, then the signs will definitely alternate. This will keep on alternating. This will be infinite series and it will keep on alternating. That's a minus. Also 1 minus x inverse, this will be plus 1 plus x. I can just replace my plus x with minus x. If I replace my x with minus x, this will be plus x square plus x cube and so on. Now why this will be always plus? Because if I divide 1 by 1 minus x, so let's assume that x is again a positive number, that is 1 minus 0.1. This will be something more than 1. That's why I will always keep on adding up the numbers. I hope that part is clear. Why am I adding here? That is one part. And remember, for this series to be valid, your mod of x should always be less than 1. The magnitude of x should always be less than 1 for this series to be valid. Previously, I forgot to, I think, mention this. This series is only valid if mod of x is less than 1. Otherwise, it is not valid. So, I see that here I have this term, that is 1 by z minus 1 minus 1, then plus z minus 1 minus z minus 1 whole square, and so on. So, I see I have this z minus 1 everywhere. So, what can be the reason this z minus 1 came into action? So, here this will be always my x, right? You see, this is x square, x square minus 1. So, my z minus 1 is actually equals to my x. That's why this series came into action. For now, I'm just decoding the series. So if this is x, so mod of x must be less than 1, that is mod of z minus 1 must be less than 1. So I see in all the 4 options, everywhere they have written it, mod of z minus 1 is less than 1. So I'm 100% sure that they are using this series where x is z minus 1. That is clear. Now which one will be my solution? That is the interesting part. So this, right, let me first decode this particular series. So if I decode this particular series, this is simply minus 1 divided by this. I have to write this z is, so this is my x basically. Z minus 1 is x. So how can I write this in terms of this series? That would be a bit difficult for me to write, correct? Yeah, the expansion of this series will be simply 1 by x. There is no expansion here. Okay, 1 by x, there is no expansion. There is also 1 by x square. There is no expansion. So these are definitely not my series. But here something interesting will happen. So if I replace this with x, correct? If I replace this with x, so my z minus 1 is x. So what is my z? Z is equals to 1 plus x. Z is equals to 1 plus x. So I can replace my z with 1 plus x. Yes, if I replace my z with 1 plus x here, this will be simply 1 plus x, and this will be 1 plus x, this will be x, okay, and this will be minus 1 plus x and x. So definitely one of them will be answer, like one is the negative of the other. So I'll just check for the sign, that's it. So let me first solve this one, the positive one, because I like positive things. Okay, let me delete these things. So if I solve the positive part, that is equals to 1 by 1 plus x into x. So this expansion would be what? This is 1 minus x inverse divided by x, correct? Yes. So this will be, sorry, 1 plus x inverse, 1 plus x raised to the power minus 1. So this will be 1 minus x plus x square minus x cube plus x raised to power 4 minus x raised to power 5 and so on, divided by x. So this will be 1 by x minus 1 plus x minus x square plus x cube minus x to raised to power 4 and so on. So what is x? X is z minus 1. So this will be 1 by z minus 1 minus 1 plus z minus 1 minus z minus 1 whole square plus plus z minus 1 whole cube and so on. So yep, so that is the case over here. So yeah, I see that one this is 1 by z minus 1 minus 1 z minus 1 z minus 1 whole square and so on. Like of course it is matching, so option B will be correct. Option A was just the negative sign. So without even understanding Lorentz series, still we were able to solve it. So in Lorentz series, this is what you have to take in keep in mind. That's it. Okay, or you can watch a spot video of Lorentz series. I did not feel that is required. Without that also you can solve it. So that's how you can solve. In Lorentz series, you just have to use bit of trickery. That's it. Okay, and brain. So yeah, let's move on to the next question. This is the next question. Consider the function whose residue at the residue of fz at z equals to minus 1. So z equals to minus 1 is basically a simple pole. So I will do this. So z plus 1 into 1 by z plus 1 z plus 2 z plus 3 limit as z is minus 1. So this would be equals to my z plus 2 by z plus 3 so this would be z minus 1, so this will be 1 into 2 half, so 0.5 would be your answer for the question. Let's move on to the next question. For the complex function this, which of the following is correct? The phase is 2 tan inverse b upon a. So what is the phase basically? So the phase of the numerator, like overall phase of this complex number, right? We can write this to be some e raised to power I theta 1 and this to be e raised to power I theta 2. So overall your phase would be e raised to power I theta 1 minus theta 2. So what is the phase of the numerator? Remember a and b both are positive. So the term in the numerator, both a and b are positive. So I am lying in the first quadrant. If I am lying in the first quadrant, the angle is simply positive. Tan inverse imaginary upon the real part. So tan inverse b upon a. That is my theta 1. What about theta 2? So theta 2, if b and a are both positive and it is minus jb, so I am lying here. So the angle here is minus tan inverse b upon a. This has been taught to you in network theory. This has been taught to you in network theory, how to calculate the angle in different quadrants. I am in the quadrant 4. I am in the quadrant 4. So minus tan inverse b upon a. So overall your this result, right? Overall your phase theta 1 minus theta 2 would be 2 into tan inverse b upon a, which is correct. So option A is definitely correct. Let's read the other option. The phase is tan inverse 2b upon a. No, incorrect. The magnitude is 1. Yeah, magnitude is definitely 1. What is the magnitude? Magnitude, it will be magnitude of the numerator. Let's say that is magnitude of z1 upon magnitude of z2, right? That is the like polar Euler transformation. It is z1 into e raised to power theta 1 divided by z2 into e raised to power theta 2. Now it is magnitude of z1 divided by magnitude of z2. Magnitude of z1 is simply under root of a square plus b square, and magnitude of z2 is under root a square plus b square as well. Both are same, so both are same, so it will be 1. So magnitude of your this complex number will be 1. That is correct. So option A and C are my correct answers for this question. A and C. Yeah. Let's move on to the next question. So they are asking questions from basics. So I have this function fz when expanded in as a power series around z equals to 2 would result in this coefficient. The region of convergence ROC when mod of z less than 1, the coefficients of AK would be. So like very complex terms, let me simplify it. So they want to expand around z equals to 2, right? That is basically z minus 2. So they want to, this is nothing but similar to the Lorentz series expansion, right? So basically my z minus 2 is equals to x. Okay, z minus 2 equals to x. They want to expand around this value. When expanded as a power series around z equal to 2. So what you can do is you can write the Taylor series expansion of this same function around z equals to 2. So what will be the Taylor series expansion around z equals to 2? So it will be f of 2 first of all plus f dash of 2 into z minus 2 into f dash of 2 plus z minus 2 square by 2 factorial into f double dash of 2 plus z minus 2 whole cube upon 3 factorial into f triple dash of 2 and so on. So yeah, what is f of 2? It is simply minus of 1 plus f dash. What is f dash of z? First of all, f dash of z would be minus of 1 by z whole square, and differentiation of minus z is minus 1, so this will be plus. And here I will put z equals to 2, so this will be 1 by 1 square, that is simply minus 1 whole square, that is 1 only, so that is 1. So this will be 1, so this will be z minus 2 into 1 plus z minus 2 whole square upon 2 into f double dash. So if I differentiate this function again, this would be 2 into minus 2 into 1 minus z whole cube, and of course another minus 1 will be multiplied due to chain rule. So this will be 2 by 1 minus z cube. So 2 by 1 minus z cube. So 1 minus z is basically minus 1 whole cube, right? Minus 1, z equals to 2 minus 1 whole cube, that is minus 1 whole cube, that is minus 1 only. So this will come out to be 2 will be cancelled. This will be z minus, so this coefficient would be z minus 2 whole square minus, basically there will be minus, and this will follow, basically this will be plus z minus 2 raised to the power of 3 and minus z minus 2 raised to the power of 4, and this will keep on happening. This will keep on happening basically. So what are the what I can write? So this is some sum of AK, because they are writing in this form, sum of AK z minus 2k, sum of AK z minus 2k, and k is going from 0 to infinity. So when my yeah, when my k is 0, so that is a of 0, a of 0 is minus 1. When my k is 1, a of 1 is simply plus 1, a of 2 is minus 2. So I can see, of course, your a is minus 1 raised to the power of k. So when k is 0, it is 1. Sorry, it is actually, oh sorry, it will be some odd multiple. It will be k raised to the power plus 1, k plus 1. So when k is 0, it is -1, when k is 1 it is +1. So yeah, option B would be your correct answer for this question. Now is there any easier way to solve this? Of course there will always be an easier way. So mod of z minus so z minus 2 is my x, correct? So I can write what is my z. Z is basically 2 plus x. Z is 2 plus x. So I can change my function. This will be 1 by 1 minus z. Z is 2 plus x minus x. So this will be 1 divided by -1 minus of x. I can take minus in common. So minus 1 divided by 1 plus x. So I hope you know what is the Taylor series. So what is the expansion basically? This will be 1 minus x plus x square minus x cube plus x raised to power 4 and so on. So minus sign is there at the outside. So you will take the minus sign inside. This will be -1 plus x minus x square plus x cube and so on. So yeah, what is my x? X is my z minus 2. So this will be -1 plus z minus 2 minus z minus 2 plus z minus 3. So z minus 2 raised to the power 3. Like this is the same series that I have written here. How simple it is, right? Without even writing the Taylor series, you can directly use Lorentz series. Okay, so now the step is same, answer would be same. So let's solve the next question. So we have this complex number variable and conjugate. The equation, this represents what? So yeah, let me first solve it. So z bar whole square, z bar whole square. So z bar whole square would be basically x minus iy whole squared plus x plus iy whole square equals to 2. So from this will be x square minus y square minus 2i xy plus x square minus y square plus 2yxy equals to 2. So 2yxy will be cancelled. 2 I can take common. So x square minus y square equals to 1. This is the equation of a hyperbola. Okay, equation of ellipse is x square by a plus y square by b equals to some constant c. This is the equation of ellipse. Equation of circle is x square plus y square equals to r square. That is the equation of circle. Equation of parabola is y equals to 4ax square, something like that. And yeah, equation of hyperbola would be negative. It will be x square by a minus y square by b. So yeah, this will be the answer. Hyperbola would be the answer for this question. Okay, yeah, that's all. The next question. The complex functions fz equals to this and f bar, basically it is the conjugate, are both analytic in the given domain. So they both of them are analytic in the given domain. Then which of them is correct? So if both of them are analytic, okay, both of them are analytic. So what can I comment? So I can say that if this function is analytic, so u of x would be equals to v of y, that is for certain, and my u of y would be equals to minus of v of x, that is for certain. This function is analytic. Now if this function is analytic, because f bar is analytic, so this function is also analytic. So here what is my u and v? Just be careful. Your u is u, but your v is actually minus of v. Be very careful here. So you can write this in terms of a real part and an imaginary part. Let me write this m plus in. Okay, so m is equals to u, that is a real part, and n, the imaginary part, is equals to v minus v. So again Cauchy-Riemann equation will be satisfied. So mx will be equals to ny. So what is mx? ux. What is ny? Minus vy. So ux equals to minus vy. So I can put this value over here. So minus vy is equals to plus vy. So I can take the Vy on the other side. So Vy would be equals to 0. So Vy would come out to be equals to 0. Okay. So here, right, Ux equals to Vy. Ux is equals to Vy, that is correct. Definitely Ux equals to Vy, correct. Also Vy is 0. If Vy is 0, Ux is also 0. So this is correct actually. So choose the correct option. So option A is definitely correct. What about option D? Uy equals to minus of Vx. So let me again use the second equation, that is My equals to minus of Nx. So what is My? It is Uy. And what is Nx? It is minus of Vx. So this will be plus of Vx. So again I can replace my Uy with plus Vx here. Again you will see that you are getting your Vx equal to 0. So your Uy is also equal to 0. So Uy equals to minus of Vx equal to 0. It should be 0. So this two things are correct, but this is incorrect. It has to be equal to 0. It is not equal to 0. It has to be equal to 0. Now your both Uy, Ux, Vy, Vx all are 0. Okay, all are 0. So your Ux is 0. So how can I, so Fz equals to U plus IV, and you know if I differentiate this function with respect to x, it will be 0 because Ux and Vx both are 0, right? And if I if I differentiate my function with respect to x, this will be Ux plus I Vx, that will be 0. This is 0. If I differentiate my function with respect to y as well, this will be 0. Okay, so can I conclude anything? I'm thinking something. So you have to differentiate your function with respect to z. So yeah, one more thing is there. If all of them are 0, correct? If all of them are 0, that means if I'm differentiating my v with respect to x, that is also 0. If I'm differentiating my v with respect to y, that is also 0. That means my v has to be a constant function. See, like any 2 value or 3 value, v has to be a constant function. And if I'm differentiating my u with respect to x, that is also 0. And I'm differentiating my u with respect to y, that is also 0. So u also has to be constant function. That is the only possible chance. Let's say u is equals to 3. So if I differentiate this 3 with respect to x, 0. If I differentiate this 3 with respect to y, 0. But let's say u is equals to x or u is equals to y, you will see that one of the derivative is non-zero. So u has to be a constant function. V also has to be a constant function. So u and v both are constant function. So if both of them are constant function, 3 plus any constant c1 plus ic2. So if I differentiate a constant with respect to z, that is x plus iy, it will be 0. So this derivative will be 0. So this option is also correct. Option D is incorrect. It will not be non-zero, it will be 0. So option A and C will be my correct answer for this particular question. Let's move on to the next question, this one. Consider the function this, where z is a complex variable, sum of the residues at singular point of fz. So what are the singular points? 2z plus 1, z into z minus 1. So at z equal to 0 I have a residue, and at z equals to 1 I have a residue. So if I put z as the residue of z equal to 0 would be 2 into 0 plus 1 upon 0 minus 1, and residue at z equals to 1 would be 2 into 1 plus 1 upon 1. So this will be basically minus 1 plus 3, that is 2. So 2 would be your answer. Like I'm just solving this in a fast manner. So 2 would be your answer. Let's move on to the next question. So this is the next question. Choose the correct option for the following statements of closed line integration, where C is a simple path in a simply connected domain. Okay, it is a simple closed path, whatever path, I don't care. The Cauchy theorem cannot be directly applied. Integration of fz dz when your fz is equals to 1 by z square and C is a unit circle. Okay, if C is a unit circle, Cauchy's theorem cannot be directly applied to conclude. Yeah, it cannot be it cannot be directly applied to conclude. Yeah, you cannot directly apply it. You have to find out the residue. So Cauchy's theorem is not applicable, but Cauchy residue theorem is applicable. Okay, so you will find out the residue at z equal to 0, and residue at z equal to 0 is definitely 0. The Lorentz expansion is 0, no coefficient of 1 by z, so it is 0. But directly Cauchy theorem will not be able to directly conclude, because Cauchy theorem just states that the regarding Cauchy's theorem. So regarding Cauchy's theorem just states that the closed loop integration will be 0 if my function is analytic. Okay, here my function is not analytic, so I have to use the Cauchy residue theorem. So yeah, this statement is correct. If fz is analytic in D, then it can be concluded this for any simple path C in D. Yes, in the domain C, if I choose any simple path, and if fz is analytic in the given path, then this will be always 0. That is the Cauchy theorem. That is the Cauchy theorem. The function fz must be analytic in D to conclude this for any simple path D. No. It must be analytic for the closed line integration to be 0. No. Residue can also be 0, correct? If residue is 0, then also this closed line integration will come out to be 0. We have seen this actually. So only if the function is analytic, then only this will be 0 integration. No, not the case. This is not equal to 0 when fz is equals to 1 by z square, since function is not analytic at z equal to 0. So this is the perfect example, right? So here, even though the function is not analytic at z equal to 0, but the residue at z equal to 0 is 0, which we have already computed in today's lecture. So yes, residue is 0, so answer will be 2 pi into the residue, that is 0. So answer would be 0. So answer will still be 0. It will not be equals to not 0. It will be 0. So this option is again incorrect. So option A and B will be my correct answers for the question. Let's now solve the last question. This last question came in gate BM. So which of the following is /r correct about the value y equals to log e of minus exponential? Okay, that's interesting. Minus exponential. So I can solve this further. This can be written like this. It is log or ln, like log of base e and ln are same thing, into minus 1 into e raised to power x. So this is a product log m into n. So this will be log minus 1 plus ln e raised to power x. Now minus 1 can also be written in the complex format, polar format, Euler format. It will be e raised to power I pi, because e raised to power I pi will be lying here in the negative real axis. So this will be ln of e raised to power I pi plus ln of e raised to power x, that is x. So this will be I pi. Now this I pi, right, this can be I pi k actually, or n, where n is any integer. Okay, no, n cannot be any integer actually. N has to be even integer, because this will be e raised to power I pi, e raised to power 3 I pi, because I can again go around another circle, that is 2 pi. So this will be basically e raised to power I pi, e raised to power 3 I pi, 3 pi, 5 pi, so on. So basically this, let me write this e raised to power n pi, where n is a odd integer. Just keep this in mind. N has to be an odd integer. So this will be n pi. So this will be I n pi, because I can take the power outside and ln of e is simply 1. So this will be x plus e raised to power I n pi, where n is any odd integer. So x minus can also be there, like basically negative odd integer. So minus 3 pi, minus 5 pi, minus of pi, e raised to power minus pi is also minus 1, e raised to power minus 3 pi is also minus 1. So negative numbers are also totally valid over here. So it has to be odd integer, and plus minus is valid, and x plus minus I n pi. So this will be your answer. Also, y is a complex valued. Yes, y is not real valued. It has a real component and it has a imaginary part. So it is both complex. So B and C will be your correct answer. So with that, we have finished with complex variables part. So if you have enjoyed the complex variable part, like just hit the like button, put in the comments below if you have understood the complex variable. In about 11 and a half hours, I think around 11 hours or 11 and a half hours, we are able to complete the whole vector calculus and complex. These are two topics which If you study from full course, it will take you around 30 hours to cover. So we have comprised that in less than 12 hours. So if you're enjoying this R-PYQ series, yeah, please comment down below. Please like the videos. That's it. That's the only demand from my end. So with that, I will see you in the next video. Until then, happy learning.